83 senior and staff DevOps incidents that separate real experts in 2026, and beyond interviews. Only 1% of engineers can solve these.
DevOps is not about tools. It is about survival.
Most DevOps tutorials show you how to build a pipeline or deploy a cluster. This is not that video. In the real world, senior engineers do not get paid to write YAML. They get paid to solve the impossible when the YAML turns against the system. When the logs are empty, the dashboard is green, but the business is losing $10,000 every minute. That is when your career as a senior engineer truly begins.
The Senior or Staff DevOps Masterclass. The 80-plus real-world incidents that actually matter in 2026-plus interviews.
Most DevOps content teaches you how to build. This series teaches you how to survive when everything you built is burning down. We are moving beyond basic tutorials and entering the world of high-stakes architecture, kernel-level failures, and distributed system catastrophes. This is a reference-grade deep dive into the engineering intuition that separates a junior from a staff engineer.
The difference, junior versus senior thinking.
There is a fundamental psychological shift in how top-tier engineers approach a production failure. Junior approach reactive. They restart the pod, hope for the best, and blame the code. Mid-level approach diagnostic. They check the logs, follow the alerts, and fix the symptom. Senior approach systemic. They ignore the noise, look for the decision tree signal, and fix the architectural flaw that allowed the failure to exist in the first place. In this two-part series, we are breaking down over 80 high-scale, real-world incidents using our debug framework.
The two-part roadmap.
We have divided these 80-plus incidents into two massive volumes to maintain maximum technical depth. Part 1, 34 incidents, the platform and automation nightmares, focuses on Kubernetes orchestration, CI/CD delivery pipelines, and infrastructure as code failures. Part 2, 49 incidents, the distributed systems and kernel catastrophes, focuses on deep networking, database consensus, and Linux kernel-level bottlenecking. In this video, we start with Part 1, the platform and automation nightmares.
Part 1, the 8 chapters of incidents.
We are breaking down these 34 incidents across the following critical domains. 1. Systemic leadership, managing technical debt and legacy inheritance. 2. Orchestration layer, deep internals of the K8 scheduler and control plane. 3. Network edge ingress, L7 routing and admission control failures. 4. Scaling and state, HPA logic flaws and persistent data integrity. 5. Delivery engine, CI/CD pipeline traps and environment parity. 6. Infrastructure as code, GitOps loops and Terraform state corruption. 7. Release engineering, API contracts, schemas and feature flag coupling. 8. The human factor, observability gaps and incident response culture. Every scenario uses our 9-step debug framework with staff-level follow-up challenges.
The 9-step incident framework.
To ensure this remains a reference-grade asset, every incident follows this strict blueprint. 1. The panic moment, the real-world symptoms and alerts. 2. The hypothesis, the senior-level heuristic thinking. 3. The 6-step investigation, the forensic debugging process including the root cause. 4. The smoking gun, literal code and log proof. 5. The fix, production-ready architectural solutions. 6. Guardrails, automated prevention strategies. 7. The follow-up stack, 4 elite interview curveballs for every scenario. We are not just fixing bugs, we are masterclassing the architecture of failure. Let's start with Category 1, Management and Systemic Leadership.
Category 1, Management and Systemic Leadership.
Focus, the soft skills that require hard technical knowledge. In this section, we examine the systemic failures that occur at the intersection of business demands and infrastructure neglect.
Incidents in this category.
We will be performing deep dives into the following scenarios. 1. The black box inheritance, managing 60-plus undocumented servers without breaking production. 2. The overnight delivery gap, why code is ready on Wednesday but does not ship for 2 weeks. Let's begin with the architectural forensic work of the black box inheritance. The hardest problems in DevOps are not technical, they are human and organizational. We begin Part 1 by looking at the incidents that occur when documentation is missing, platform investment is ignored, and you inherit a system you do not yet understand. This is where senior leadership is truly tested. Let's start with Incident 1, The black box inheritance.
The Senior DevOps Incident 1. The Black Box Inheritance.
You just inherited a production environment with 60 servers. No documentation. No infrastructure as code. The previous engineer quit abruptly. The CTO wants you to modernize the stack immediately. You find a random, seemingly idle T2 microserver and shut it down to save costs. 20 minutes later, the entire checkout system crashes, and customers stop receiving order confirmation emails. You just triggered a cascading failure by touching a black box.
Symptoms, the panic moment.
Here is what the observability stack was showing us during the outage. 1. Core application metrics. The main website is returning 200 OK responses. 2. Database CPU is normal, queries are executing successfully. 3. Alerts. The checkout microservice is suddenly throwing massive 504 gateway timeouts. 4. Logs. The application logs show connection refused to an internal hard-coded IP address. The checkout service is alive, but it is fatally hanging while trying to reach a phantom destination.
Hypothesis, thinking like a senior.
The temptation is to start reverting application code. As a senior, I formulate hypotheses based on infrastructure state. Hypothesis 1, external email API is down, ruled out. The logs show a failure to reach an internal 10.x.x.x IP, not an external provider like SendGrid. Hypothesis 2, security group or network ACL change, ruled out. CloudTrail shows no recent network firewall modifications. Hypothesis 3, shadow dependency. The checkout service relies on an undocumented legacy server that was just taken offline. Decision tree signal. If application code is frozen, third-party APIs are healthy, and legacy infrastructure was recently altered means, then always suspect an undocumented shadow dependency. Investigation. The 6-step debugging masterclass.
Step-by-step legacy system discovery.
I need to understand what this server was doing before I try to replace it. We execute the following discovery steps. 1. Trace the failure first. We extract the dead internal IP from the checkout service logs and map it back to the AWS console. 2. Identify the instance. Second, we realize it matches the idle T2.micro server we just shut down. 3. Emergency boot. We power the instance back on and SSH directly into the machine to observe its state. 4. Process mapping. We execute SS-TLNP to list all listening TCP sockets and the processes bound to them. 5. Scheduled tasks. We run crontab-L and inspect the /etc/cron.d directory for hidden batch processes. 6. Root cause identified. The idle server is actually a hard-coded legacy SMTP relay and a critical database backup node. Let's look at the exact commands that prove this root cause. The proof server forensics. The socket statistics command reveals a process called master listening on port 25. This is the master daemon for postfix. This idle server was actually the central SMTP relay for the entire company. Furthermore, the crontab reveals a hidden bash script that runs every night at 2 a.m. If we had terminated this instance permanently, we would have silently destroyed the company's database backup synchronization process.
The fix, observe before you control.
We need to take ownership without breaking production. Senior warning, the temptation is to immediately rewrite this server into Terraform. Automating a system you do not fully understand means automating your misunderstanding. That will cause a catastrophic outage. Our immediate fix is to establish visibility first. Emergency visibility rollout. Instead of writing infrastructure code to rebuild the servers, we write configuration management code to install metrics agents across all 60 unknown servers. By installing Datadog, Prometheus, or OS Query everywhere, we map CPU, memory, network connections, and open ports. We let the monitoring run for 2 weeks to generate an accurate architectural map.
Prevention and guardrails, the post-mortem.
We survived the outage, but we must eliminate the black box entirely. Here are our guardrails. 1. VPC flow logs. We enable AWS VPC flow logs and query them with Athena to mathematically prove which internal IPs are communicating, ensuring no shadow dependencies are missed. 2. Tagging strategy. We mandate that every single AWS resource is tagged with owner, environment, and function. Untagged resources trigger a daily Slack alert. 3. Phased IAC import. We document the servers first, then slowly use Terraform import to bring the existing infrastructure under state management without destroying it. The lack of documentation was the previous engineer's fault. Keeping it undocumented is your fault. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. How do you safely intercept and analyze the traffic going through this legacy postfix server to see who is using it, without interrupting the active connections?
Answer: we cannot restart the service or install heavy proxies. Instead, we use TCP-dump-IF0 port 25-N to capture the packet headers in real time at the kernel level. This shows us the exact source IPs of every microservice relying on this SMTP relay, completely transparently to the applications.
Senior Follow-up 2 The Scale and Trade-off Trap. You want to manage these 60 legacy servers with Terraform. Importing them into one massive state file seems efficient. What is the risk, and what is the trade-off?
Answer: a monolithic state file creates a massive blast radius. If someone makes a typo in the Terraform code, a single Terraform apply could accidentally destroy all 60 servers simultaneously. The trade-off is management complexity versus safety. We must split the state files into bounded contexts, one for network, one for databases, and one for the application tier.
Senior Follow-up 3 The Day 2 Migration Reality. Now that you understand the SMTP server, you want to migrate its workload to a managed service like AWS SES. 30 legacy applications rely on it. How do you migrate with zero downtime?
Answer: we use the Strangler Fig pattern. First, we provision AWS SES. Second, we update the legacy apps one by one using a feature flag to send traffic to both the old server and SES, dual write. We monitor SES for rejected emails. Once we verify 100% success on the new system, we flip the flag to exclusively use SES and finally decommission the old server.
Senior Follow-up 4 Curveball. You are mapping the remaining servers. You find a massive, expensive bare metal server with port 80 open, but your metrics show zero inbound network traffic and zero CPU usage for 30 straight days. Can you safely decommission it?
Answer: before hitting delete, a senior engineer asks, why is it idle? Is this a passive disaster recovery node waiting for a failover? Or is it a batch processing server that only runs quarterly tax calculations? Never kill an idle server without reviewing at least 12 months of crontab history, system log rotations, and consulting the business financial calendar.
Pro tip: the fallacy of the scream test.
Juniors joke about the scream test, turning off a server and waiting to see who screams. This is a career-ending move in enterprise environments. Professionals use network telemetry. By analyzing cloud provider flow logs, you can build a mathematical, perfect dependency graph of every byte of traffic in your network before you ever touch a single server.
Senior DevOps Incident 2 The Overnight Delivery Gap.
On Monday morning, the CEO walks into your office. A competitor launched a highly requested AI-driven recommendation feature over the weekend, capturing massive market share. The CEO demands to know how fast we can match it. The development team works overtime and finishes the code by Wednesday. But 2 weeks later, the feature is still not in production. The CEO is furious. The developers are frustrated and the business is losing money. The code is done, but the delivery system is paralyzed.
Symptoms: the panic moment.
Here is what the value stream map showed us during this critical delay. 1. Pipeline queues. The CI pipeline takes 4 hours to run because it builds the entire monolith for a one-line change. 2. Environment contention. The code is stuck waiting for staging 1, which is currently locked by another team testing a different feature. 3. Ticket ops. Developers opened a Jira ticket for the database schema update 6 days ago, but the DBA team backlog is full. 4. Manual gates. The deployment requires manual sign-off from QA, security, and a weekly change advisory board meeting. Think of the flow versus wait time funnel. Code is written, moves to CI, enters a waiting state, requires manual approval, enters waiting again, and finally deploys. The flow is entirely choked.
Hypothesis: thinking like a senior.
A junior engineer tries to optimize the Docker build cache to shave off 5 minutes. As a senior, I formulate hypotheses based on systemic flow. Hypothesis 1, developer incompetence, ruled out. The pull request was approved and unit tests passed within 48 hours. Hypothesis 2, architectural complexity, ruled out. The change is isolated and backward compatible. Hypothesis 3, platform sclerosis. The delivery pipeline relies on manual human intervention, shared mutable environments, and ticket ops. Decision tree signal. If PRs merge fast but deploy slow, and the pipeline is mostly waiting, then always suspect human gates and shared environments. Investigation. The 6-step debugging masterclass.
Step-by-step value stream discovery.
We need to mathematically prove where the time is being lost. We execute the following discovery steps. 1. Measure DORA metrics. First, we query our CI/CD tool to measure lead time for changes. We find it averages 14 days. 2. Trace pipeline execution. Second, we look at the pipeline logs. We notice it spends 90% of its lifecycle in a pause state. 3. Identify environment bottlenecks. We check the staging cluster and realize 50 developers are fighting over a single static staging database. 4. Audit infrastructure provisioning. We review the ITSM tool Jira or ServiceNow and find infrastructure requests take an average of 5 days to fulfill. 5. Map the approval chain. We trace the required manual clicks in GitLab or Jenkins and identify 3 different departments required to push a button. 6. Root cause identified. At this point, it became clear. This is not a technical bottleneck. It is a human one. The competitor deployed overnight because of their platform, while our code sat waiting for permission. Let's look at the pipeline data that proved this systemic failure. The proof: pipeline bottlenecks. The pipeline data is undeniable. The actual compute time for compiling and testing the code is 20 minutes. But the code sits completely idle for over 144 hours waiting for a database administrator to manually review a schema change. Following that, it waits another 48 hours just to get access to the shared staging environment. This is a workflow design catastrophe.
The fix: self-service and ephemeral environments.
We must eliminate ticket ops and shared environments. We will implement ephemeral environments that spin up dynamically for every pull request. Senior warning: ephemeral environments introduce massive new risks like cost explosions, cluster control plane pressure, and noisy neighbors. Every architectural fix has consequences. Furthermore, do not just buy an expensive portal like Backstage immediately. Automating a broken, bureaucratic process just makes broken things happen faster. Fix the workflow first. Ephemeral environment automation. By using an Argo CD pull request generator, we eliminate the need for Jira tickets. The moment a developer opens a pull request on GitHub, the platform detects it automatically. It dynamically provisions a completely isolated, full-stack Kubernetes namespace specifically for that PR. No more staging contention. Queue a contest instantly. When the PR merges, the environment is automatically destroyed.
Prevention and guardrails: the post-mortem.
To keep delivery velocity high permanently, we enforce these platform guardrails. 1. Feature flags. We decouple deployment from release. Code is merged and deployed to production behind a feature flag immediately, allowing business teams to turn it on without CAB meetings. 2. Automated database migrations. We integrate tools like Liquibase or Flyway directly into the CI pipeline to execute schema changes without manual DBA tickets. 3. DORA dashboards. We put a Grafana dashboard in the engineering area tracking deployment frequency and lead time, making the delivery speed visible to the entire executive team. A senior engineer builds roads so developers can drive fast without hitting pedestrians. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. When you spin up an ephemeral environment for a PR, how do you dynamically route QA engineers to that specific pod without manually editing DNS records?
Answer: we use a combination of external DNS and a wildcard ingress controller. The pipeline automatically generates an ingress rule with a host name like pr123.staging.ourcompany.com. External DNS watches this ingress object and automatically creates the Route 53 DNS record on the fly, pointing to the cluster load balancer.
Senior follow-up 2, the scale and trade-off trap. You solve the staging bottleneck, but developers are opening 50 PRs a day. Replicating the entire database and application 50 times just caused your AWS bill to triple. How do you handle this trade-off?
Answer: ephemeral environments are expensive. To control costs, we implement two controls first. We use a tool like Keda to scale the PR environments to 0 pods outside of business hours. Second, we implement a strict TTL or time to live controller. If a PR environment is untouched for 48 hours, it is automatically destroyed, forcing the developer to actively rebuild it.
Senior follow-up 3, the Day 2 migration reality. This works great for modern microservices. But 40% of the codebase is a legacy Java monolith that takes 16 gigabytes of RAM to run. You cannot fit 50 copies of it in your cluster. How do you test without breaking the bank?
Answer: instead of full-stack duplication, we use request-level routing with a service mesh like Istio. We run only one copy of the heavy legacy monolith. When a PR environment needs to test its new microservice, the service mesh injects a custom HTTP header. Istio routes traffic with that header exclusively to the PR pod, but falls back to the shared monolith for everything else.
Senior follow-up 4, Curveball. You successfully removed the bureaucracy. Developers are now deploying to production 100 times a day. But suddenly, your MTTR or mean time to recovery spikes. When an outage happens, the team spends hours trying to figure out which of the 100 deployments caused it. How do you stop the chaos?
Answer: before throwing process and CAB meetings back at the problem, a senior asks, why are fast deployments causing blind spots? We lack deployment markers. We must configure our CI/CD pipeline to inject a deployment event marker directly onto our Datadog and Grafana timeline graphs. This visually overlays every deployment on top of the error rate graphs, instantly revealing exactly which commit triggered the crash.
Pro tip: selling platform engineering.
Never use the words Kubernetes, Argo CD, or platform engineering when talking to the CEO or CFO. They do not care about your tools. Speak the language of the business: lead time, time to market, and developer productivity ROI. If you promise to cut feature delivery time from 3 weeks to 3 hours, they will write you a blank check for any tool you want.
Category 1, wrap up, the senior engineer's takeaway.
When we look back at our management and systemic leadership incidents, it proves one undeniable truth in our industry. Technical debt is a silent business killer. Remember that visibility must precede modernization. You cannot safely accelerate a system you do not understand. Internal developer platforms are not just nice-to-have tools. They are the competitive edge that allows teams to ship safely at lightning speed. Finally, tribal knowledge is a single point of failure. If your infrastructure is not defined in Git, it simply does not exist. Being a senior engineer means recognizing that human and process bottlenecks are just as solvable as application bugs.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Now that we have addressed the systemic and leadership traps, it is time to go deeper. Even with perfect documentation and a blank check for platform investment, the technology itself has limits. We are moving from the world of human decisions into the world of the machine.
Category 2. Kubernetes Orchestration and Control Plane.
Focus the deep internals of the K8 scheduler and core cluster components. In this section, we are looking at the brain of your infrastructure. We will explore what happens when the scheduler fails to pack pods, when the etcd consistency layer freezes, and when gRPC multiplexing breaks your load distribution. When the orchestrator fails, every application, regardless of its code quality, fails with it.
The orchestration incidents.
We will now perform deep dives into these 5 critical orchestration failures. 3. Intermittent pod restarts, solving the no-log silent killer and the OOMC group trap. 4. Resource fragmentation, the Swiss cheese cluster and the logic of bin packing. 5. Autoscalar oscillation, fixing the scale-up and scale-down logic loops. 6. Uneven load distribution, solving the gRPC and HTTP/2 hot pod problem. 7. etcd quorum loss, when disk IOPS latency freezes the entire cluster API. Let's start with the most common and most frustrating Kubernetes mystery, the silent pod restart.
The Senior Dev Ops Incident 3. The Silent Kubernetes Killer.
It is Tuesday at 10 a.m. You get a PagerDuty alert that the payment microservice is experiencing intermittent 502 bad gateway errors. You check Kubernetes, and you notice the pods are continuously restarting. The development team swears they did not deploy any new code. The worst part, you run kubectl logs on the crashed pods and the logs are completely empty. The application is dying in total silence.
Symptoms, the panic moment.
Here is what our observability tools showed us during the incident. 1. Pod restarts. The restarts column in kubectl get pods is climbing rapidly. 2. Application logs running kubectl logs pod -- previous returns absolutely nothing. 3. Node metrics. The underlying EC2 or GCP worker nodes have plenty of available CPU and RAM. 4. Grafana dashboards. The pod's memory graph shows a slow climb, then suddenly drops to 0 over and over. The application is not crashing gracefully. It is being violently executed by the system.
Hypothesis, thinking like a senior.
Juniors usually blame the developers for a bad code push. As a senior, I formulate hypotheses based on system behavior. Hypothesis 1, liveness probe failure, ruled out. Failed probes leave unhealthy events in the Kubernetes event log. We have null. Hypothesis 2, unhandled application exception, ruled out. An unhandled exception in Java or Node.js would print a stack trace to stand out before exiting. Hypothesis 3, container runtime execution. The Linux kernel's OOM killer is terminating the process instantly for violating boundaries. Decision tree signal. If pods are restarting, application logs are empty, and the node is healthy means, then always suspect the Linux kernel OOM killer. Investigation. The 6-step debugging masterclass.
Step-by-step container debugging.
We need to prove that the kernel is assassinating our application. We execute the following steps. 1. Check pod events. We run kubectl describe pod and look at the bottom events section for scheduling errors. 2. Inspect previous state. We inspect the exact exit code of the dead container using the -o YAML output flag. 3. SSH to worker node. We locate the specific worker node hosting the dead pod and SSH directly into it. 4. Query kernel logs. We run dmesg-t to search the host Linux kernel logs for memory-related interventions. 5. Analyze JVM settings. We check the Docker file to see how the Java virtual machine is allocating its heap memory. 6. Root cause identified. The Java application thinks it has access to the full 32 GB of node RAM, but Kubernetes restricted it to 2 GB. When Java tries to use its heap, Linux instantly kills it for violating the cgroup limit. Let's look at the exact outputs that prove this root cause. The proof state in kernel logs. Exit code 137 is the universal Linux signal for sigkill 9 plus 128. This proves the application did not crash on its own. It was forcefully terminated by the operating system without a chance to write logs. The kernel log confirms it. Kubernetes uses Linux C groups to enforce memory limits. The Java virtual machine did not respect the container boundaries, so the kernel acted in self-defense.
The fix, aligning the boundaries.
We need to align the application's memory awareness with the infrastructure limits. Senior warning: do not just increase the Kubernetes memory limit. If the application has a memory leak, increasing the limit only delays the crash and wastes expensive cloud resources. You must fix the application's boundary awareness. Container memory tuning. First, we ensure Kubernetes has a strict limit set. This protects the rest of the node from noisy neighbors. Second, we pass the max RAM percentage flag. This forces Java to calculate its heap size dynamically based on the 2 GB container limit, rather than the 32 GB host node limit. The crashes stop instantly.
Prevention and guardrails, the post-mortem.
Here is how we ensure OOM kills never take down production again. 1. Quality of service, QoS. We ensure critical applications have guaranteed QoS by setting memory requests exactly equal to memory limits. 2. Metrics alerting. We create a Datadog alert triggering if container_memory_working_set_bytes reaches 85% of container_spec_memory_limit_bytes. 3. CI/CD linting. We add a tool like kubelinter or confdesc to our pipeline to automatically block any deployment that lacks resource limits. A senior engineer does not just fix the pod, they systemize the prevention of the error. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How exactly does Kubernetes enforce these limits at the OS level?
Answer: Kubernetes does not actually limit memory itself. It talks to the container runtime, like containerd, which configures Linux control groups C groups. C groups create a virtual fence in the kernel's memory management system. When the process inside the C group asks for 1 byte more than the limit, the kernel's OOM killer is invoked, targets the highest memory consumer in that C group, and sends a SIG kill.
Senior follow-up 2, the scale and trade-off trap. You fix the OOM kill by setting requests equal to limits, giving the pod guaranteed QoS. What is the financial trade-off of this architecture?
Answer: the trade-off is massive cost inefficiency. By guaranteeing resources, we sacrifice bin packing. If the app only uses 500 megabytes on average but is guaranteed 2 gigabytes, we have 1.5 gigabytes of stranded, wasted memory per pod. At a scale of 10,000 pods, we are paying millions of dollars to AWS for unused RAM just to buy stability.
Senior follow-up 3, the day 2 migration reality. You realize 400 legacy microservices across the company are missing memory limits. How do you roll out limits without breaking production?
Answer: you cannot enforce them blindly. First, we deploy a vertical pod autoscaler, VPA, in recommendation mode across the cluster. We let it observe actual memory usage for 2 weeks. Then, we write a script to automatically generate PRs for all 400 repositories, applying the observed baseline limits plus a 20% buffer.
Senior follow-up 4, curveball. You check a crashing pod. It was OOM killed. You look at the Grafana dashboard, and the application was only using 20% of its memory limit when it died. How is an OOM kill possible when memory is free?
Answer: before assuming the metrics are broken, a senior engineer asks, what else consumes memory inside a Linux container? The answer is the Linux page cache. If the application is reading or writing massive files to disk, Linux uses available RAM to cache those files. This cache counts against the C group memory limit. The fix is not tuning the application heap. It is tuning how the app interacts with the file system.
Pro tip, the exit code cheat sheet.
Memorize container exit codes. If a pod restarts with exit code 0, the application completed its task and shut down. If it is 1, it threw an application error. If it is 137, it was OOM killed by the host. If it is 143, it received a SIG term, meaning Kubernetes intentionally asked it to shut down for scaling or node draining. Reading the code saves you hours of digging.
Senior Dev Ops Incident 4, the Swiss cheese cluster.
It is the end of the month, and the data science team kicks off a critical machine learning batch job. The job requires a single pod with 16 gigabytes of RAM. You have a massive Kubernetes cluster with over 500 gigabytes of total free memory across 50 nodes. Yet, the pod gets stuck in the pending state. The CTO looks at the Datadog dashboard showing the cluster at only 40% utilization and asks, "Why are we stuck when we have hundreds of gigabytes of free RAM?" You are experiencing Kubernetes resource fragmentation.
Symptoms, the panic moment.
Here is what the cluster state showed us during the stalled deployment. 1. Pod state: the critical batch pod has been in pending for 45 minutes. 2. Global metrics: kubectl top node shows average node memory utilization is well under 50%. 3. Node autoscaling: the cluster autoscaler is completely silent. It refuses to spin up a new node. 4. Developer complaints: the data team is threatening to bypass Kubernetes and spin up raw EC2 instances. Think of the cluster like a block of Swiss cheese. You have a massive amount of total cheese, but it is entirely full of holes. You cannot fit a 16 gigabyte solid block into a bunch of 2 gigabytes holes.
Hypothesis, thinking like a senior.
A junior engineer assumes the autoscaler is broken and tries to manually scale the autoscaling group. As a senior, I evaluate scheduler mechanics. Hypothesis 1, taints and tolerations. Ruled out. The pod manifest has no node selectors and the worker nodes have no restrictive taints. Hypothesis 2, persistent volume zone constraints. Ruled out. The pod does not mount any zone-locked EBS volumes. Hypothesis 3, bin packing failure. The free memory is highly fragmented and the cluster autoscaler is hitting a maximum node limit. Decision tree signal: if pods are pending for resources, global free resources are high, and autoscaler is silent, then always suspect scheduler level resource fragmentation. Investigation: the 6-step debugging masterclass.
Step-by-step scheduler debugging.
We need to prove exactly why the kube scheduler is rejecting our pod. We execute the following steps. 1. Check pod events. We run kubectl describe pod and read the failed scheduling event. 2. Analyze node allocatable. We use a custom JSON path query to find the maximum contiguous free memory on any single node. 3. Check autoscaler logs. We query the cluster autoscaler logs to see why it is not provisioning a new node to solve the problem. 4. Review autoscaler limits. We discover the autoscaler has hit its max node ceiling set in the AWS autoscaling group. It is forbidden from scaling out. 5. Evaluate scheduler profile. We review the kube scheduler scoring algorithm. At this point, the true architecture flaw reveals itself. 6. Root cause identified. The default Kubernetes scheduler uses the node resources least allocated plugin. It intentionally spreads pods out as evenly as possible across all nodes for high availability. This ruined our bin packing, leaving 50 nodes with exactly 10 gigabytes of free RAM each, making it impossible to schedule a 16 gigabytes pod. Let's look at the exact scheduler outputs that prove this root cause. The proof: scheduler and node states. The scheduler evaluates nodes independently. Even though we have 500 gigabytes of RAM free globally, a single pod cannot span multiple nodes. The scheduler correctly determines that 0 out of 50 nodes can fit the 16 gigabytes request. The node query proves the fragmentation. Because the default scheduler spreads workloads perfectly evenly, every single node has roughly 10 gigabytes of free RAM. It is a perfectly balanced, utterly paralyzed cluster.
The fix, descheduling and compaction.
We need to clear a contiguous block of RAM without taking the cluster offline. We will deploy the Kubernetes descheduler to safely evict smaller pods and force them to repack onto fewer nodes. Senior warning: extreme bin packing heavily increases your blast radius. If you pack 100 microservices onto a single dense node to save money, and that underlying EC2 instance dies, you instantly lose 100 pods. Furthermore, dense packing can lead to intense CPU cache contention and network I/O bottlenecks. Executing the descheduler. We configure the descheduler with the low node utilization strategy. This explicitly targets the Swiss cheese problem. It finds nodes utilizing under 20% of their memory, safely evicts those pods, and reschedules them onto nodes approaching 80% utilization. Within 3 minutes, 5 nodes are completely emptied, allowing our 16 gigabytes batch job to finally schedule.
Prevention and guardrails, the post-mortem.
To prevent this from becoming a recurring nightmare, we implement the following guardrails. 1. Custom scheduler profiles. We update the Kube scheduler configuration to prioritize the node resources most allocated scoring plugin, forcing Kubernetes to natively bin pack workloads going forward. 2. Node provisioning. We transition from the legacy cluster autoscaler to Carpenter. Carpenter bypasses auto-scaling groups entirely and provisions the exact right-sized EC2 instance, for example, an R5.X large, instantly based on the pending pod's specific requirements. 3. Continuous compaction. We run the discheduler as a cron job every night at 3 a.m. to actively defragment the cluster during low traffic hours. Efficiency at scale is not about having resources. It is about how tightly you can pack them. The senior follow-up stack.
Senior Follow-up 1, Mechanism Deep Dive. Exactly how does the Kube scheduler decide where a pod goes?
Answer: it is a two-phase operation, filtering and scoring. First, filtering predicates, eliminates nodes that fundamentally cannot host the pod, for example, out of memory, mismatched node selectors, or taints. Second, scoring priorities, ranks the remaining nodes from 0 to 100 based on plugins like image locality or least allocated. The node with the highest score wins the pod.
Senior Follow-up 2, the Scale and Trade-off Trap. You reconfigured the scheduler to use node resources most allocated to enforce tight bin packing. What non-compute bottleneck will you hit first?
Answer: network limits and IP exhaustion. AWS EC2 instances, for example, have strict elastic network interface, any limits. A T3 large might have plenty of CPU and RAM left, but it can only attach 3 ENIs, meaning it physically cannot host more than 35 pods. You will start seeing failed create pod sandbox errors because the node ran out of assignable IP addresses, even though memory is free.
Senior Follow-up 3, the Day 2 Migration Reality. You need to run the discheduler in production during the day to clear space. How do you guarantee you do not accidentally take down a critical customer-facing microservice during the eviction?
Answer: the discheduler natively respects Kubernetes Pod Disruption Budgets, PDB. Before running any compaction, we must ensure every critical deployment has a PDB configured with min available, 80%. The discheduler will physically skip evicting any pod if it would cause the service to drop below its defined high availability threshold.
Senior Follow-up 4 Curveball. You run the discheduler. It successfully evicts 50 small pods to make room. But a minute later, you watch the cluster state, and the pods reschedule themselves right back into the exact same fragmented Swiss cheese layout. Why?
Answer: before blindly running the tool again, a senior diagnoses the constraints. Why is the scheduler refusing to bin pack? The answer is pod anti-affinity. The developers explicitly wrote pod anti-affinity rules in their manifests, stating that no two pods of the same service can share a node. The discheduler kicks them off, but the scheduler is legally bound by the manifestation rules to spread them back out. You must negotiate high availability rules with the dev team.
Pro tip, the request versus limit illusion.
Fragmentation is drastically worsened by sloppy developer configurations. If a developer sets a memory request of 4 GB but a limit of 8 GB, the scheduler only uses the 4 GB to find a node. However, the node must physically retain the capacity for the 8 GB limit. Use Vertical Pod Autoscaler, VPA, in recommendation mode to force developers to set requests exactly equal to limits, creating predictable, tightly packed clusters.
The Senior Dev Ops Incident 5, the Autoscaler Oscillation.
It is 3 p.m. on a heavy traffic day. Your cluster starts behaving like a heartbeat monitor. Nodes are spinning up, running for 3 minutes, and then being terminated, only for new nodes to spin up again immediately. This flapping behavior is causing massive scheduling churn, intermittent latency for users, and a terrifying spike in your cloud bill. The cluster is trying to find an equilibrium that does not exist.
Symptoms, the panic moment.
Here is what the cluster state showed during this unstable loop. 1. Node churn kubectl get node shows new nodes joined 2 minutes ago while others are in scheduling disabled. 2. Pod instability, pods are stuck in a terminating to pending loop as nodes vanish underneath them. 3. Autoscaler events, the cluster autoscaler is firing scale up and scale down events in the same 5-minute window. 4. Cloud Console. The AWS Auto Scaling Group is constantly triggering, terminating, and launching EC2 instances. The cluster is caught in a logic loop, where adding a node makes the cluster too empty, but removing it makes it too full.
Hypothesis, thinking like a senior.
A junior might try to increase the min nodes to stop the churn. As a senior, I analyze the threshold logic. Hypothesis 1, insufficient instance capacity, ruled out. Nodes are successfully launching, proving the cloud provider has capacity. Hypothesis 2, pod disruption budgets, ruled out. PDBs are configured correctly and are not blocking evictions. Hypothesis 3, threshold oscillation. The scale-down utilization threshold is too close to the scale-up request logic, causing a mathematical race condition. Decision tree signal. If nodes are flapping under constant load and pods are rescheduling frequently means, then always suspect an overlapping scale-down utilization threshold. Investigation. The 6-step debugging masterclass.
Step-by-step oscillation debugging.
We need to see the internal logic of the cluster autoscaler. We execute these steps. 1. Check autoscaler logs. We search for decision logs in the cluster autoscaler pod to see why it thinks a node is unneeded. 2. Monitor node utilization. We run kubectl describe node on a node marked for deletion and calculate its total resource requests. 3. Identify the trigger pod. We find the specific pod that is triggering the scale-up event. It is a large pod with high memory requests. 4. Trace the rescheduling. We watch where that pod goes. When the new node launches, the pod moves there, leaving the old node underutilized. 5. Check scale-down timers. We check the -- scale-down unneeded time setting. It is set to a dangerously low 2 minutes. 6. Root cause identified. We have a resource gap conflict. The scale-down threshold is set to 50%. When a large pod moves to a new node, it leaves its original node at 45% utilization. The autoscaler instantly kills that node, forces the pods back to pending, which triggers a new scale-up. The cycle repeats forever. Let's look at the logs that revealed this mathematical logic failure. The proof cluster autoscaler decision logs. The log shows the node is at 42% utilization. Because the threshold is 50%, the autoscaler marks it for death. But the reason it is at 42% is because the ML pod just moved to a different node.
The fix, stabilizing the control loop.
We need to introduce hysteresis, a delay that prevents the system from reacting to short-term state changes. Senior warning, increasing the unneeded time will stop the flapping, but it will keep your nodes running longer than necessary, increasing costs. You must balance stability with your cloud budget. Autoscaler configuration tuning. We lower the threshold to 35%. This creates a buffer zone where nodes that are partially full are not immediately killed. Crucially, we tell the autoscaler to wait 15 minutes after any scale-up event before it is allowed to perform a scale-down. This breaks the oscillation loop.
Prevention and guardrails, the post-mortem.
1. Pod priority. We implement priority classes. This ensures that if the cluster is tight, less important pods are evicted first, keeping critical pods stable. 2. Carpenter migration. We plan a migration to Carpenter. Unlike cluster autoscaler, Carpenter does not rely on static auto-scaling groups. It makes sub-second provisioning decisions based on the current pod shape, virtually eliminating oscillation. 3. Alerting. We create a Datadog alert for rate of node deletions. If more than 5 nodes are deleted in 10 minutes, we trigger a high-severity alert. A senior engineer does not just tune the thresholds, they change the engine that evaluates them. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is a scale-down utilization threshold, and why is it dangerous in heterogeneous clusters?
Answer: it is the sum of CPU and memory requests on a node divided by its total capacity. In a cluster with different instance types, for example, small and large nodes, a 50% threshold on a large node might represent 32 gigabytes of free RAM, while on a small node it is only 2 gigabytes. This inconsistency makes it impossible to set a single global threshold that works for all workloads.
Senior follow-up 2, the scale and trade-off trap. You set the unneeded time to 15 minutes to gain stability. What happens when your traffic drops by 90% at midnight?
Answer: you will suffer from ghost cost. Because the cluster waits 15 minutes per node to scale down, you will be paying for dozens of empty EC2 instances long after the traffic has vanished. Over a month, This cool-down cost can add up to thousands of dollars in wasted spend.
Senior Follow-up 3, the Day 2 Migration Reality. You want to move to Carpenter. How do you prevent it from terminating nodes that contain long-running batch jobs that do not support checkpoints?
Answer: we use the carpenter.sh/ do not disrupt annotation on the specific pods. Carpenter respects this annotation and will skip any node containing such a pod during its consolidation or drift cycles, ensuring the batch job finishes successfully.
Senior Follow-up 4 Curveball. You have a perfect autoscaler setup, but suddenly AWS Spot instances in your region hit 0% availability. Your cluster cannot scale up. How do you protect the existing traffic from being crushed?
Answer: a senior engineer never relies solely on Spot. We configure our node groups with a base capacity of on-demand instances and use priority-based expander in the autoscaler. If Spot is unavailable, the autoscaler is configured to automatically fall back to more expensive on-demand nodes after 2 failed Spot attempts, ensuring availability at the cost of budget.
Pro tip: the bin packing paradox.
If you use very large nodes, for example, M5.16x large, fragmentation and oscillation are much more common. Smaller, more numerous nodes, for example, M5. large, allow for smoother linear scaling. Always match your instance size to your largest pod's request plus a 20% buffer to ensure the scheduler always has a place to land.
The Senior DevOps Incident 6, the Hot Pod Paradox.
Your service has 10 replicas. Your dashboard shows the average CPU across the service is a healthy 15%. Yet, 10% of your users are experiencing extreme latency and 504 errors. You dig deeper and find a nightmare. One single pod is pegged at 100% CPU and 0% memory availability, while the other 9 pods are sitting completely idle. Your load balancer is sending 90% of the traffic to a single container.
Symptoms: the panic moment.
Here is the data that revealed the load imbalance. 1. Individual pod metrics: pod 0 is at 100% CPU, pods 1 through 9 are at 2% CPU. 2. Network traffic: the bytes in metric for pod 0 is 50 times higher than its siblings. 3. Connection count: the number of active TCP connections is roughly equal across all pods. 4. Application type: the service is a high-performance gRPC or HTTP/2 backend. The load balancer thinks the traffic is balanced because the connection count is equal, but the actual work inside those connections is not.
Hypothesis: thinking like a senior.
A junior might assume there is a large request hitting that pod. As a senior, I analyze the protocol behavior. Hypothesis 1: sticky sessions, session affinity, ruled out. The service manifest has session affinity null. Hypothesis 2: uneven pod scheduling, ruled out. The pods are spread across different nodes perfectly. Hypothesis 3: L4 versus L7 balancing. We are using gRPC HTTP/2, and our load balancer is operating at layer 4, causing long-lived connection multiplexing issues. Decision tree signal: if average CPU is low, one pod is hot, and you are using gRPC or HTTP/2 means, then always suspect layer 4 load balancing multiplexing. Investigation: the 6-step debugging masterclass.
Step-by-step load balancing discovery.
We need to prove that the load balancer is blind to the internal requests. We execute these steps. 1. Check service type. We check the Kubernetes service definition. It is a standard type, cluster IP. 2. Verify proxy mode. We check kube proxy. It is running in IP tables mode, which is a pure layer 4 TCP load balancer. 3. Analyze protocol. We confirm the app uses gRPC. gRPC uses a single, long-lived TCP connection to send thousands of multiplex streams. 4. Trace a client. We identify a single heavy client like an internal batch job. It opened one connection to pod 0 at startup and has never closed it. 5. Simulate scale. We scale the service from 10 to 20 pods. The new 10 pods receive 0 traffic because the existing clients never rebalance their old connections. 6. Root cause identified. L4 sticky connections. Standard Kubernetes services balance connections, not requests. Because gRPC reuses one connection for its entire life, the first pod to receive a connection from a heavy client becomes a hot pod forever. Let's look at the gRPC traffic patterns that prove this architectural mismatch. The proof: connection versus request metrics. The pod metrics show the massive disparity. Pod 0 is nearly at its one-core CPU limit, while the others are practically sleeping. The Layer 7 metrics reveal the truth. Even though connection counts are equal, Pod 0 is processing 500 times more requests per second, because of the long-lived HTTP/2 streams.
The fix: implementing Layer 7 balancing.
We must move from balancing connections to balancing requests. This requires an L7 proxy that can look inside the HTTP/2 frames. Senior warning: introducing a service mesh like Istio or Linkerd to fix balancing adds significant latency overhead, usually 1 to 3 milliseconds per hop, and massive operational complexity. Only do this if your traffic volume justifies the cost. Fixing the balance with Istio. By moving to a least_request algorithm at the service mesh level, Envoy will look at the actual active request count inside the gRPC streams. If Pod 0 is busy, it will immediately route the next request to Pod 1, regardless of where the TCP connection originated.
Prevention and guardrails: the post-mortem.
1. Max connection age. We update the application code to set a max connection age, for example, 5 minutes. This forces gRPC clients to reconnect periodically, naturally rebalancing traffic even without a service mesh. 2. L7 ingress. We ensure that all external traffic enters through an L7 ingress, like Nginx or ALBs, that is configured for gRPC, ensuring traffic is balanced before it even reaches the pods. 3. Standardized monitoring. We mandate that all gRPC services must export request per second metrics, and we alert on coefficient of variation across the pod fleet to detect hotspots automatically. A senior engineer does not trust the load balancer. They verify the distribution. The senior follow-up stack.
Senior follow-up 1. Mechanism deep dive. Why does Kubernetes kubeproxy in IP tables mode fail to balance gRPC traffic?
Answer: IP tables is a packet-level, connection tracking firewall contract. It makes a load balancing decision exactly once, when the TCP/SYN packet arrives. Once the connection is established, all subsequent packets in that connection follow the exact same NAT rule to the same pod. Since gRPC reuses one connection for many requests, IP tables never gets a second chance to rebalance.
Senior follow-up 2. The scale and trade-off trap. You implement a service mesh to fix balancing. What is the sidecar memory tax?
Answer: every pod now has an Envoy sidecar. At 1,000 pods, if each Envoy consumes 150 megabytes of RAM, you are spending 150 gigabytes of cluster RAM purely on the network layer. This can increase your cluster cost by 10 to 20% just to solve a load balancing issue.
Senior follow-up 3. The day 2 migration reality. You cannot afford a service mesh. How do you implement look-aside load balancing for your gRPC clients?
Answer: we use a gRPC headless service in Kubernetes. This allows the client to receive the full list of pod IPs via DNS. The client then implements its own load balancing logic, like round robin, and opens simultaneous connections to every pod. This puts the complexity on the developer but removes the need for a proxy.
Senior follow-up 4. Curveball. You have a perfectly balanced L7 mesh, but suddenly one pod becomes a hot pod again. You check the logs, and it is not a traffic flood. It is a single, massive list user's API call that takes 30 seconds and consumes 100% CPU. No amount of load balancing can fix this. What is the pattern to solve a single heavy request?
Answer: this is a work stealing or job queue pattern problem. If a single request can crush a pod, synchronous HTTP is the wrong architecture. We must offload the heavy work to a background worker via a message broker like SQS or RabbitMQ. The API should return a 202 accepted with a job ID, and the client should poll or wait for a webhook once the heavy processing is done.
Pro tip: the connection drain maneuver.
When you see a hot pod in gRPC, do not restart it immediately. Use kubectl exec to send a sigquit or sigterm to the process. Most gRPC servers will stop accepting new streams on that connection, but finish the active ones. This forces the client to open a new connection to a different, less loaded pod without dropping the current user's request.
The Senior DevOps Incident 7, the heart of the machine etcd quorum loss.
It is Monday morning. Suddenly, your entire Kubernetes cluster becomes a ghost ship. Developers report that kubectl commands are timing out. The CI/CD pipeline is stuck in pending because it cannot create new namespaces. Existing applications are still running, but the cluster's brain is paralyzed. You are experiencing a quorum loss in etcd, the distributed key value store that holds the entire state of your universe.
Symptoms, the panic moment.
Here is the state of the cluster during the control plane paralysis. 1. API server latency. Calls to the kube API server take over 30 seconds or return 500 for gateway timeout. 2. Command timeouts. Any kubectl write operation like creating a secret or config map fails completely. 3. Controller failures. The kube controller manager is failing to perform leader election, leading to stalled deployments. 4. Master node metrics. CPU and memory usage on the master nodes are low, but disk I/O weight is spiking. The cluster is technically alive, but it has lost the ability to reach consensus on any new state changes.
Hypothesis, thinking like a senior.
A junior engineer might try to restart the kube API server. As a senior, I look at the underlying consistency layer. Hypothesis 1, network partition, ruled out. Master nodes can ping each other with sub-millisecond latency. Hypothesis 2, API server OOM, ruled out. Metrics show the process is stable and not hitting cgroup limits. Hypothesis 3, etcd disk latency. The WL or write-ahead log of etcd is failing to sync to disk fast enough, causing the Raft consensus protocol to fail. Decision tree signal. If kubectl is timing out, API server logs show etcd errors and disk I/O weight is high, then always suspect etcd storage latency. Investigation. The 6-step debugging masterclass.
Step-by-step etcd forensics.
We must prove that the brain is suffering from disk-induced amnesia. We execute these steps. 1. Check API server logs. We search for etcd server, request timed out or context deadline exceeded messages. 2. Inspect etcd health. We use etcdctl endpoint health to see if any member of the 3-node cluster is responding. 3. Monitor fsync metrics. We query Prometheus for ect_disk_ while _fsync_ duration_ seconds_ bucket. We see 99th percentile jumps to over 500 milliseconds. 4. Analyze disk performance. We run iostat-xz1 on the master nodes to check for await times and disk saturation. 5. Check leader elections. We search etcd logs for lost leader or failed to send out heartbeat events. 6. Root cause identified. The master nodes are running on slow, burstable EBS volumes. A heavy logging process on the master node consumed the disk IOPS burst balance, causing etcd disk syncs to stall. This prevented the leader from sending heartbeats, triggering endless failing elections. Let's look at the etcd metrics that revealed this hardware-level bottleneck. The proof, etcd latency metrics. This is the most critical metric for etcd health. The 99th percentile of fsync duration is 550 milliseconds. For etcd to be stable, this must be under 10 milliseconds. The disk is physically too slow to commit the logs. Because the disk sync took so long, etcd missed its heartbeat deadline. Other members thought the leader was dead and started a new election, but those also failed because they could not write to their own disks.
The fix, dedicated high IOPS storage.
We must move etcd from shared, burstable storage to dedicated, low-latency NVMe or provisioned IOPS volumes. Senior warning, never co-locate etcd data with application logs or system swap files on the same physical disk. etcd is extremely sensitive to I/O jitter. A single log rotation or APT update on the master node can take down the entire cluster if the storage is shared. Optimizing etcd disk priority. By slightly increasing the heartbeat and election timeouts, we give the cluster more breathing room to handle disk spikes, but this increases the time it takes to detect a real failure. We use the Ionis command to give the etcd process real-time I/O priority, ensuring the Linux kernel prioritizes etcd disk writes over background system tasks.
Prevention and guardrails, the post-mortem.
To protect the cluster's brain permanently, we implement these guardrails. 1. Storage isolation. We ensure etcd runs on dedicated EBS volumes, GP3 with 3000 IOPS baseline, that are not shared with any other process. 2. Advanced monitoring. We set a critical pager duty, alert on ect_disk_, while _fsync_duration_ seconds bucket, exceeding 20 milliseconds for more than 2 minutes. 3. Regular defragmentation. We schedule a weekly cron job to run etcd cuddle defrag across the members to ensure the internal DB remains compact and efficient. A senior engineer treats etcd like a heart. It needs a clean, dedicated blood supply of IOPS to function. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. Why does etcd use a synchronous fsync for every write? Why not cache it in memory and flush it later?
Answer: consistency over availability. etcd implements the Raft consensus algorithm. To guarantee that a change is truly committed, the leader must wait for a majority of nodes to confirm the data is physically on non-volatile storage. If etcd cached writes in RAM and the node crashed, the cluster state would become corrupted or out of sync, violating the fundamental promise of a distributed key-value store.
Senior Follow-up 2 The Scale and Trade-off Trap. You have 3 master nodes and want to increase them to 5 for higher availability. What is the performance trade-off?
Answer: higher write latency. Because etcd is a consensus-based system, every write must be acknowledged by a majority, 3 out of 5 nodes. By adding more nodes, the leader has to send more heartbeats and wait for more network/disk acknowledgements across the wire, which actually slows down the cluster's total write throughput.
Senior Follow-up 3 The Day 2 Migration Reality. You need to migrate etcd to a new storage class without taking the cluster offline. How do you do it?
Answer: we use the Raft membership change process. We add one new etcd member on the new storage, wait for it to catch up and become healthy, then gracefully remove one old member. We repeat this process one node at a time until the entire cluster has been rotated to the new hardware, maintaining quorum throughout.
Senior Follow-up 4 Curveball. You have perfect SSDs and low latency. But suddenly, etcd RAM usage triples and it starts crashing. You find a single developer has created 50,000 unique config maps in one namespace. How does this data bloat kill the control plane?
Answer: this is the watch bottleneck. The Cube APA server and various controllers maintain open watches on etcd keys. When you have 50,000 objects, the memory overhead for the etcd indices and the CPU cost for serialization becomes massive. You must implement resource quotas at the namespace level to prevent any team from DDoSing the control plane with excessive object creation.
Pro tip: the fsync speed test.
Before you even install Kubernetes, run a tool called Fio on your master nodes. Use the command fio-name equals test-rw equals write-eoengine equals libio-fdatasync equals 1-directory equals /var/lib/etcd. If the 99th percentile fdatasync latency is higher than 10 milliseconds, your cluster is a ticking time bomb. Do not install the control plane until the storage meets this baseline.
Category 2 Wrap-up. Mastering the orchestrator.
The orchestration layer is where the magic of Kubernetes happens, but as we have seen, it is also where the most baffling failures reside. A senior engineer understands that resource limits are not just suggestions. They are hard kernel boundaries that will kill your application in total silence if ignored. You have learned that a cluster is only as healthy as its etcd latency, and that average CPU is a dangerous lie when protocols like gRPC are involved. True stability in the orchestration layer requires a deep respect for bin packing logic, hysteresis in scaling, and the underlying Linux kernel C groups. If you do not master the scheduler, you are just renting compute. Once you master it, you are truly orchestrating infrastructure.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But scheduling a pod is only half the battle. Once that container is running, it needs to talk to the world, and more importantly, it needs to be protected from it. We are now shifting our focus from the brain of the cluster to its immune system and its front gates.
Category 3, Networking, Security, and Admission Control.
Focus: how traffic enters the cluster and how it is restricted. This is the edge. In this section, we deal with the most high-stakes failures in the stack. We will explore L7 buffer overflows that selectively target your most valuable users, YAML formatting errors that create invisible holes in your firewall, and admission controllers that can accidentally lock you out of your own cluster. In a microservice world, the network is the computer, and it is also the most common place for things to go silently wrong.
The edge and security incidents.
We will be performing deep dives into these critical networking and security failures. Incident 8, silent ingress drops, Nginx L7 buffer overflows and the nightmare of JWT header limits. Incident 9, network policy leakage, the fatal -YAML error that creates a massive security breach. Incident 10, mutating webhook failure, when an admission controller downtime blocks all cluster scheduling. Let's start at the very edge of the network with the mystery of the silent ingress drop.
The Senior DevOps Incident 8, the silent ingress drop.
It is Tuesday afternoon. Customer support escalates a critical issue. Enterprise power users cannot log into the platform. Every time they authenticate, they get a white screen and a 502 bad gateway error. Meanwhile, thousands of regular free tier users are logging in and using the system without a single glitch. You check the authentication microservice. It is perfectly healthy. You check the database. It is green. The application is working, but the edge of your network is selectively assassinating your most valuable customers.
Symptoms, the panic moment.
Here is what the observability stack showed us during this selective outage. 1. App metrics: the authentication pod CPU and memory are completely flat. No spikes. 2. App logs: the authentication pod logs show a successful 200 OK login event for the enterprise users. 3. Client experience: the enterprise user's browser receives a 502 bad gateway originating from Nginx. 4. Traffic pattern: the failure only happens to users who belong to more than 20 distinct security groups in the Active Directory. The application thinks the user logged in successfully, but the user receives a catastrophic error. The connection is breaking exactly at the L7 proxy layer.
Hypothesis, thinking like a senior.
A junior engineer looks at the 502 error and immediately restarts the downstream pods. As a senior, I formulate hypotheses based on the proxy to application boundary. Hypothesis 1, application timeout, ruled out. The application processed the login in 150 milliseconds and returned a 200 OK. It didn't time out. Hypothesis 2, upstream connection refused, ruled out. Nginx successfully passed the request to the pod, and the pod replied. Hypothesis 3, response buffer overflow. The proxy is choking on the specific shape or size of the application's response payload. Decision tree signal: if generic traffic is 200 OK, but specific power users get 502s while app logs show success, then always suspect an L7 proxy buffer or header constraint. Investigation, the 6-step debugging masterclass.
Step-by-step edge debugging.
We need to mathematically prove why the Nginx ingress controller is betraying the application. We execute these steps. 1. Trace the request. We generate a trace ID for a failing enterprise login and search it in Datadog/Jaeger. 2. Analyze the app output. We look at the exact payload the authentication service returned. It generated a massive JSON Web Token, JWT, containing all 25 of the user's Active Directory groups. 3. Measure the payload. We measure the HTTP response headers. The set cookie header containing the JWT is over 9 kilobytes. 4. Bypass the proxy. We use kubectl port forward to hit the authentication pod directly from our local machine, completely bypassing the ingress controller. The login works flawlessly. 5. Inspect the proxy. We query the Nginx ingress controller pod logs, specifically looking for the error.log stream, not just the access.log. 6. Root cause identified. The default Nginx proxy _buffer size, which reads the response headers from the upstream application, is strictly limited to 4K or 8K depending on the OS platform. When the backend returned a 9K JWT cookie, Nginx panicked, dropped the connection, and served a 502 bad gateway to the client. Let's look at the exact Nginx error log that proved this root cause. The proof ingress error logs. This log is the definitive proof. Upstream is Nginx terminology for your application pod. The app returned a header, the massive JWT cookie, that physically could not fit into the memory buffer allocated by Nginx. We confirm the default configuration. Nginx allocated exactly 4096 bytes to read the response headers. The 9 kilobytes JWT cookie overflowed this buffer, causing the proxy to abort the connection.
The fix, expanding the proxy buffers.
We need to increase the memory buffers allocated to the Nginx ingress controller to accommodate the enterprise JWTs. Senior warning, do not just blindly set the proxy buffer size to 64K for the entire cluster. Nginx allocates this memory per connection. If you have 10,000 concurrent connections, increasing the buffer drastically inflates the baseline memory consumption of your ingress pods, potentially triggering an OOM kill at the network edge. Apply the fix precisely. Ingress annotation patching. By applying this annotation directly to the specific auth ingress, we increase the header buffer to 16K only for authentication routes. We protect the global memory pool of the ingress controller. We also adjust the proxy buffers, which handle the response body. If the header buffer is larger than the body buffers, Nginx will throw configuration warnings. Traffic instantly recovers.
Prevention and guardrails, the post-mortem.
This incident was a symptom of a deeper architectural flaw. Here is how we prevent it permanently. 1. Payload standardization. We mandate the development team refactor the JWT. Instead of packing 25 group names into the token should only contain a user ID, and the downstream services should query an internal cache RIDIs for group memberships. 2. Edge observability. We configure Nginx to expose Nginx_ingress_controller_ requests metrics with a status label. We set a Datadog alert specifically for 502 errors generated by the proxy, independent of application metrics. 3. Distributed tracing. We inject OpenTelemetry trace headers at the AWS load balancer level. If a request reaches the load balancer but never reaches the application pod, our dashboards instantly flag the edge network as the culprit. A senior engineer treats the network proxy as an application in its own right, deserving the same strict monitoring as the business code. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does Nginx care so much about header sizes? Why not just stream the data directly to the client?
Answer: Nginx is a reverse proxy, not a dumb pipe. To make routing, caching, and filtering decisions, Nginx must read and parse the entire set of HTTP headers before it can begin transmitting data to the client. It must hold these headers in contiguous memory, the proxy_buffer_size. If the headers exceed that memory allocation, Nginx cannot parse the HTTP protocol safely and drops the connection.
Senior follow-up 2, the scale and trade-off trap. You fix the issue using annotations on a specific ingress object. The team loves this and starts adding massive buffer annotations to all 500 microservices. What happens next?
Answer: the ingress controller pods will suffer an out-of-memory OOM kill. Nginx dynamically allocates memory per connection. If you have 50,000 active WebSockets or long polling connections, and every single one is pre-allocating 64K of buffer space instead of 4K, you will exhaust the memory limits of the Nginx pods, causing a cluster-wide ingress outage.
Senior follow-up 3, the day 2 migration reality. You decide to move this configuration from a localized annotation to the global Nginx config map so all namespaces inherit it. You apply the config map. Suddenly, hundreds of users get disconnected from the live chat feature. What went wrong?
Answer: updating the global config map triggers a hot reload of the Nginx worker processes. While Nginx is designed to reload gracefully, long-lived connections like WebSockets or gRPC streams will be forcefully terminated if the worker shutdown timeout is not tuned properly, or if the client applications do not have robust reconnect logic. Global proxy changes must be executed during maintenance windows.
Senior follow-up 4, curveball. You update the Nginx buffers to 32K. The Nginx error logs go totally clean, but the enterprise users are still reporting that they cannot log in. The browser just says connection reset. Where is the drop happening now?
Answer: before ripping apart the Kubernetes configuration again, a senior zooms out to the macro architecture. What sits in front of Nginx? The Cloud Load Balancer, AWS ALB/NLB, or the Web Application Firewall, WAF. AWS application load balancers, for instance, have a hard, non-configurable limit on HTTP header sizes, usually 64 kilobytes. If the WAF or the ALB rejects the massive JWT, the request is dropped before it ever touches your Kubernetes cluster. You must fix the application's token architecture.
Pro tip, the golden metric of proxy debugging.
When debugging edge routing, always compare two metrics: upstream response time versus request processing time. If the upstream time is 50 milliseconds, but the request processing time is 5 seconds, the application is fast, but the proxy is struggling to buffer the data or the client is on a terrible network connection. Use this delta to instantly prove to developers that their code is fine, but the network layer is failing.
The Senior DevOps Incident 9, the default deny delusion.
It is 2 a.m. A high-priority security alert fires from Falco, your runtime threat detection system. A compromised front-end web pod in the public namespace has established a direct TCP connection to the highly sensitive Postgres SQL database in the payments namespace. You check the cluster configuration, and you see a default deny network policy explicitly applied to the payments namespace. The security team demands to know how a hacker bypassed Kubernetes isolation. The firewall is up, but the front door is wide open.
Symptoms, the panic moment.
Here is what the security and network observability tools showed us. 1. Security alerts: Falco flagged an unexpected outbound connection on port 5432 from a public-facing pod. 2. Network logs: Cilium Hubble shows active, permitted traffic flowing between public/frontend pod and payments/Postgres pod. 3. Policy state: running kubectl get network policies-n payments confirms that both a default deny and an allow payment API policy are active. 4. Cluster health: the underlying CNI, Calico or Cilium, is perfectly healthy with no crash daemon sets. The traffic is not circumventing the network plugin. The network plugin is explicitly permitting the breach.
Hypothesis, thinking like a senior.
A junior engineer immediately deletes the compromised pod. As a senior, I formulate hypotheses to understand why the network layer failed to block it. Hypothesis 1, CNI enforcement failure, ruled out. Other namespaces are actively blocking traffic, proving the CNI is enforcing rules globally. Hypothesis 2, host network bypass, ruled out. The compromised pod is not running with host network true, so it is subject to standard pod routing. Hypothesis 3, YAML array evaluation flaw. The explicit allow policy meant for the payment API contains a logical syntax error that effectively whitelists the entire cluster. Decision tree signal. If cross-namespace traffic leaks, the CNI is healthy and default deny is applied, then always suspect a YAML array parsing flaw in the allow rules. Investigation. The 6-step debugging masterclass.
Step-by-step policy discovery.
We need to mathematically prove how the Kubernetes API interpreted our security rules. We execute the following steps. 1. Verify the default deny. We run kubectl describe network policy default deny-n payments to ensure it correctly isolates all ingress traffic. It is intact. 2. Isolate the allow rules. We pull the exact YAML definition of the allow payment API policy, which is designed to let only the internal payment API pod talk to the database. 3. Trace the target. We check the pod selector of the allow policy. It correctly targets the database pods with app postgres. 4. Analyze the ingress source. We inspect the from block, which is supposed to restrict incoming traffic to a specific namespace and a specific pod label. 5. Execute a test. We spin up a dummy pod in the public namespace and run nc-vz postgres.payments.svc5432. The connection succeeds. The policy is utterly broken. 6. Root cause identified. The developer made a microscopic YAML formatting error. They added a hyphen before the pod selector inside the from block. In Kubernetes, array elements separated by hyphens are evaluated as a logical OR. The policy accidentally said, allow traffic from the payment namespace. OR allow traffic from any pod in the entire cluster that has the label app, payment API. Let's look at the exact YAML syntax that caused the data breach. The proof, the fatal hyphen. This is the first element in the from array. It tells the CNI to allow traffic from any pod inside the payment's namespace. Because of the leading hyphen, this is a completely separate array element. It acts as an OR condition. It tells the CNI to allow traffic from any pod labeled app, payment API in any namespace. The hacker simply labeled their public rogue pod with app, payment API to bypass the firewall.
The fix, enforcing logical end.
We must correct the YAML syntax to ensure the namespace selector and the pod selector are evaluated together as a single, strict condition. Senior warning, network policies are additive. You cannot write an explicit deny rule in standard Kubernetes. If even one poorly written allow policy exists, it will completely override your default deny policy. You must audit every single policy in the namespace. Emergency policy patch. By removing the hyphen, the namespace selector and pod selector become properties of the exact same array element. This transforms the logic from an OR into a strict end. Now, the CNI will only allow traffic if the source pod is located inside the payment's namespace, and it possesses the label app, payment API. The rogue public pod is instantly blocked.
Prevention and guardrails, the post-mortem.
Relying on humans to write perfect YAML is a guaranteed path to a security breach. Here are our permanent guardrails. 1. Shift-left security. We integrate kubelinter or Chekhov into our CI/CD pipelines. These tools statically analyze the YAML in the pull request and automatically block deployments that contain insecure OR rules and network policies. 2. Global network policies. We upgrade our CNI to Cilium or Calico Enterprise, which support cluster-wide network policies. We implement a true, non-overridable default deny at the cluster level, completely isolating namespaces by default. 3. Network visibility. We deploy Hubble to visualize dropped versus forwarded packets in real time, mapping a strict dependency graph that alerts us the moment an anomalous cross-namespace connection is attempted. A senior engineer does not trust Kubernetes manifests. They trust automated static analysis and runtime eBPF enforcement. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Kubernetes does not actually enforce network policies itself. How does the CNI practically block the traffic?
Answer: Kubernetes simply stores the network policy as a JSON object in etcd. The CNI, like Calico, has a daemon set running on every worker node. It watches the Kubernetes API for policy changes. When it sees one, it translates that policy into either Linux IP tables rules or eBPF maps at the kernel level. When a packet leaves the pod's virtual Ethernet interface, VETH, the kernel intercepts it and drops it before it ever reaches the physical network.
Senior follow-up 2, the scale and trade-off trap. You decide to enforce a strict default deny on all 50 namespaces. What is the immediate engineering trade-off you face tomorrow morning?
Answer: complete developer paralysis. Standard operations like DNS resolution, talking to core DNS in the Cube system namespace, and metric scraping, Prometheus, will instantly break. To enforce default deny safely, you must also write and maintain dozens of global exception policies for cluster infrastructure, severely increasing operational overhead.
Senior follow-up 3, the day 2 migration reality. You are hired into a 3-year-old cluster with 1,000 microservices and 0 network policies. How do you implement zero trust isolation without causing a catastrophic, company-wide outage?
Answer: you cannot apply deny rules blindly. We must use a CNI that supports audit mode or dry run, like Cilium. We deploy the strict policies in audit mode, which allows the traffic to pass but logs what would have been dropped. We analyze the logs for 30 days to build our baseline allow rules, and only then do we flip the enforcement switch to active.
Senior follow-up 4 Curveball. You have perfect network policies. The syntax is flawless. The namespace is isolated. Yet you see a random pod successfully bypassing the firewall and querying the database directly. How is this physically possible?
Answer: before assuming the CNI is broken, a senior engineer checks the pod spec. Does the rogue pod have host network, true configured? If a pod uses the host network, it bypasses the isolated pod network namespace entirely. It assumes the IP identity of the underlying worker node. Standard Kubernetes network policies do not apply to host-level traffic. You must use Pod Security Standards, PSS, or OPA Gatekeeper to explicitly ban the use of host network in the cluster.
Pro tip, the empty bracket trap.
Be extremely careful with empty curly braces in network policies. If you write pod selector, it does not mean select nothing. In Kubernetes API logic, an empty selector means select everything. A simple typo leaving a selector empty will silently grant cluster-wide access to your most sensitive services. The Senior DevOps Incident 10, the Gatekeeper's Strike, mutating webhook failure.
Incident 10, the admission denied loop.
It is Friday at 4 p.m. A critical security patch needs to be deployed. Developers push the code, the build passes, but the deployment fails with a cryptic error. Internal error occurred, failed calling webhook. You check the cluster, and suddenly no one can create any resource. No pods, no services, no deployments. You have been locked out of your own cluster by a failing security gatekeeper.
Symptoms, the panic moment.
Here is the cluster behavior during the admission lockout. 1. Resource creation, every kubectl apply fails with a 500 error from the API server. 2. Error message, failed calling webhook post https://gatekeeperservice.gatekeepersystem.svc:443, context deadline exceeded. 3. Scaling failure, the horizontal pod autoscaler is trying to scale pods, but the new pods are being rejected by the API server. 4. API server logs, high volume of admission webhook timeouts. The API server is refusing to write to etcd because it cannot get permission from a required external admission controller.
Hypothesis, thinking like a senior.
A junior might think the API server is broken. As a senior, I look at the dynamic admission chain. Hypothesis 1, Istio/service mesh failure, ruled out. Non-mesh resources are also failing to create. Hypothesis 2, etcd lock, ruled out. Kubectl get works perfectly, only writes are failing. Hypothesis 3, blocking webhook failure. A mutating or validating webhook like OPA or Gatekeeper is down, and its configuration is set to fail on error. Decision tree signal. If get works but apply fails with a webhook timeout means then always suspect a misconfigured admission controller failure policy. Investigation. The 6-step debugging masterclass.
Step-by-step webhook debugging.
We must identify which gatekeeper is holding the cluster hostage. We execute these steps. 1. Identify the webhook. We run kubectl get mutating webhook configurations and validating webhook configurations to list all active interceptors. 2. Check failure policy. We inspect the YAML of the suspect webhook gatekeeper or Kyverno. We look for the failure policy field. 3. Verify webhook pods. We check the status of the pods providing the webhook service. We find they are all in crash loop back off. 4. Trace connectivity. We check if the Cube API server can physically reach the webhook service IP on port 443. 5. Analyze webhook logs. We check the logs of the crashed webhook pods. We find they are failing because they cannot reach their own backend database. 6. Root cause identified. The Gatekeeper pods crashed due to a bad configuration update. Because the failure policy was set to fail, the Kubernetes API server is hard-coded to reject all resource creations if it cannot get a response from Gatekeeper. The security gate is stuck in the locked position. Let's look at the configuration error that paralyzed the cluster. The proof fatal webhook configuration. This is the strict mode. If the Gatekeeper pod is slow, crashing, or unreachable, Kubernetes will fail the entire API request. This is great for security, but catastrophic for availability if the webhook is not highly resilient. The scope of this webhook is too broad. It intercepts every single resource in the cluster. When the webhook died, it took the ability to create anything down with it.
The fix, emergency policy override.
We need to temporarily bypass the security gate to allow the cluster to self-heal. Senior warning, setting failure policy, ignore is an emergency measure only. While it restores cluster availability, it means security policies are not being enforced. You are effectively disabling your firewall to let the fire trucks through. Restore fail mode only after the webhook pods are stable. Emergency webhook patching. By changing the policy to ignore, the API server will now allow resource creation even if the webhook does not respond. This unlocks the cluster so we can actually fix the Gatekeeper deployment.
Prevention and guardrails, the post-mortem.
To prevent admission lockouts in the future, we implement these guardrails. 1. Namespace exclusion. We update the webhook configuration to namespace selector exclude Cube system and Gatekeeper system. This ensures the cluster can always manage its own core components even if the webhook is down. 2. High availability. We ensure admission controller pods have anti-affinity rules to spread across nodes and run with at least 3 replicas. 3. Resource requests. We set high CPU/memory requests for webhooks to ensure they are never OOM killed or throttled during traffic spikes. 4. Monitoring. We alert on the metric API server _admission _webhook _rejection_count and API server _admission _step _admission _duration _seconds. A senior engineer never lets a security tool become a single point of failure for cluster availability. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between mutating and validating webhooks in the admission chain?
Answer order of operations. Mutating webhooks run first. They can modify the object, for example, injecting a sidecar. Validating webhooks run last. They can only approve or deny the request. Importantly, if a mutating webhook changes an object, the validating webhooks see the final version. If either one fails with failure policy fail, the request is rejected.
Senior follow-up 2 the scale and trade-off trap. You set timeout seconds, 30 to prevent flaky network timeouts from blocking deployments. What is the side effect?
Answer: performance degradation. Every single apply or create command in the cluster will now potentially hang for 30 seconds if the webhook is slow. This can cause CI/CD pipelines to time out, HPA scaling to lag significantly, and developers to experience a very sluggish cluster feel.
Senior follow-up 3 the day 2 migration reality. You are using a webhook to inject Istio sidecars. How do you ensure that the sidecar is injected into new pods even if the Istio control plane is currently being upgraded?
Answer: this is why we use failure policy, fail for sidecar injectors. If the injector is down and we ignore it, pods will start without the sidecar. They will have no network connectivity and no security certificates, leading to a silent application failure. It is better to fail the pod creation than to spawn a naked pod in a secure mesh.
Senior follow-up 4 curveball. You have failure policy fail set. Your webhook pods are 100% healthy, yet the API server still says failed calling webhook. You check the logs in CX509, certificate signed by unknown authority. What happened?
Answer: certificate desync. The API server talks to webhooks over HTTPS. It requires a CA bundle to verify the webhook certificate. If you rotated the webhook's TLS certificate, but didn't update the CA bundle field in the mutating webhook configuration, the API server will refuse to talk to the webhook for security reasons, triggering the fail policy and locking the cluster.
Pro tip, the emergency breakless.
Always keep a breakless namespace that is explicitly excluded from all mutating and validating webhooks via a label like admission.gatekeeper.sh/ignore equals true. If the cluster locks up, you can still deploy emergency fixes or debugging tools into this specific namespace without being blocked by the failing gatekeeper.
Category 3 wrap up, protecting the edge.
The edge of your cluster is where your architectural assumptions meet the chaos of the real world. As we have seen, networking and security in a senior DevOps role are not about simple firewall rules. They are about understanding that a single character in a YAML file can bypass your entire security posture, and that a default buffer setting in a proxy can silently drop your most profitable traffic. We have learned that admission controllers are powerful gatekeepers, but they must be designed with high availability in mind, or they will become the very thing that takes you offline. A senior engineer treats every networking rule as a piece of production code, requiring the same level of linting, testing, and observability as the application itself.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Now that we have secured the perimeter and mastered the ingress, we need to look at how the applications themselves behave under pressure. We are moving from the external gates to the internal heart of the system, where we deal with the complex intersection of dynamic scaling and persistent data.
Category 4 scaling and stateful workloads.
Focus, data integrity, and reactive scaling logic. This section is about the physics of the cloud. We will explore why standard auto-scaling often loses the race against sudden traffic bursts, and how a simple node failure can lead to a catastrophic data split brain. Managing stateless apps is easy, but managing state and scale at high velocity requires a deep understanding of distributed consensus, cloud storage topology, and the metrics to compute latency triangle. This is where your ability to protect the company's data, its most valuable asset, is put to the ultimate test.
Scaling and state incidents.
We will be performing deep dives into these 2 high-stakes scenarios. Incident 11, HPA scaling lag, solving the metrics to compute latency triangle and beating the cloud boot time. Incident 12, stateful set data drift, fixing the split brain mystery and the dangerous zombie pod identity collision. Let's begin with the race against the clock, the nightmare of HPA scaling lag.
The Senior DevOps Incident 11, the scaling lag triangle.
It is 9 a.m. on Cyber Monday. The marketing team drops a massive push notification to 5 million users. Traffic hits the API gateway, instantly multiplying by 10. You have the Kubernetes Horizontal Pod Autoscaler, HPA, configured to scale up if CPU hits 70%. You expect the system to handle it gracefully. Instead, existing pods immediately peg at 100% CPU and start crashing. The HPA eventually scales up, but it is 3 minutes too late. The users already received 503 service unavailable errors. The autoscaler did its job, but it lost the race against time.
Symptoms, the panic moment.
Here is what the observability stack showed us during the Flash Crowd event. 1. App metrics, existing pod CPUs spiked from 30% directly to 100% in under 10 seconds. 2. Client experience, massive surge of 503 and 504 gateway timeouts. 3. HPA state, running kubectl get HPA showed the target CPU was 350%/70%, but the replica's count was not increasing fast enough. 4. Pod state, when new pods finally spawned, the traffic wave was already dropping, leading to wasted compute. The system is constantly chasing the ghost of past traffic. It scales up after the crash and scales down right before the next wave.
Hypothesis, thinking like a senior.
A junior engineer blames the application for crashing under load. As a senior, I evaluate the control loop latency. Hypothesis 1, metrics server downtime. Ruled out. The HPA is reading metrics, just not acting fast enough. Hypothesis 2, max replicas reached. Ruled out. The HPA had a ceiling of 100 pods, but we only had 15 running when the crash occurred. Hypothesis 3, control loop latency. The cumulative delay of metric ingestion, HPA calculation, and application cold starts is fundamentally incompatible with instant traffic bursts. Decision tree signal. If traffic bursts instantly, pods choke on CPU, and the HPA scales too late, then always suspect the metrics to compute lag triangle. Investigation. The 6-step debugging masterclass.
Step-by-step latency discovery.
We need to mathematically prove why the Kubernetes control plane is reacting in slow motion. We execute the following steps. 1. Analyze scrape intervals. We check our Prometheus/metrics server configuration to see how often CPU metrics are actually collected from the pods. 2. Check HPA sync period. We query the Kube Controller Manager flags to find the -- horizontal pod autoscaler sync period. 3. Audit HPA events. We run kubectl describe HPA and look at the timestamps of the successful rescale events. 4. Measure app cold start. We trace the application startup time. We check how long it takes from container creating to passing the readiness probe. 5. Calculate the lag. We sum the delays. 60 seconds for metric scrape plus 15 seconds for HPA sync plus 45 seconds for pod boot. 6. Root cause identified. The scaling lag triangle. The absolute fastest the system can physically react to a CPU spike is 2 minutes. The marketing push saturated the pods in 10 seconds. The HPA is fundamentally incapable of catching a vertical traffic cliff using default CPU metrics. Let's look at the HPA logs and calculations that prove this fundamental limitation. The proof: event logs and timestamps. The first major bottleneck. The pods were at 100% CPU immediately, but Prometheus only updates the metrics every 60 seconds. The HPA was completely blind to the outage for a full minute. The second bottleneck. Even when the HPA detected the spike, the default algorithm restricts scaling velocity to prevent thrashing. It slowly stepped up the replica count over multiple cycles instead of jumping straight to the required capacity.
The fix, tuning HPA velocity.
We need to override the default HPA algorithm to allow for aggressive, immediate scale outs while keeping scale downs conservative. Senior warning: aggressively tuning the scale-up velocity based on CPU can trigger a thundering herd. If your app connects to a database, instantly spawning 50 new pods might overwhelm the database connection pool, turning a compute outage into a data outage. Ensure your backend can handle the scale. HPA behavior overrides. We inject the behavior block. Setting the stabilization window to 0 allows instant reaction. We configure the policy to allow a 900% increase in pods every 15 seconds, bypassing the slow stepping behavior. We set the scale down stabilization window to 5 minutes. This prevents the HPA from aggressively killing pods during minor traffic dips, ensuring we have a buffer ready for the next wave.
Prevention and guardrails, the post-mortem.
Tuning the HPA is a band-aid. To truly survive flash crowds, we implement architectural guardrails. 1. Predictive scaling. We integrate Keda Kubernetes event-driven auto-scaling to scale based on external metrics like AWS SQ depth or incoming Nginx request rates, rather than lagging CPU indicators. 2. Pre-warming. We write a simple cron job that artificially inflates the min replicas count 15 minutes before any scheduled marketing push, ensuring the compute is already warm. 3. Pod cold start optimization. We work with developers to optimize the Docker images and application boot logic. We reduce the Java Spring Boot startup time from 45 seconds to 5 seconds by migrating to Graal VM. Scaling is not just about adding resources. It is about reducing the time it takes for those resources to become useful. The Senior Follow-Up Stack.
Senior Follow-Up 1 Mechanism Deep Dive. Exactly what mathematical formula does the HPA controller use to determine how many pods to spawn?
Answer: the HPA uses a ratio algorithm. Desired replicas equals seal. Current replicas, current metric value / desired metric value. For example, if you have 5 pods, your current CPU is 100% and your target is 50%. The math is seal. 5 100/50 equals 10 pods. If the ratio is close to 1.0, within a default tolerance of 10%, the HPA skips scaling to prevent thrashing.
Senior Follow-Up 2 The Scale and Trade-Off Trap. You migrated the app from Node.js to a JVM language like Java. Suddenly, every time a new pod boots, the HPA detects a massive CPU spike and spawns even more pods, creating an infinite loop of false scaling. Why?
Answer: this is the JVM warm-up trap. When a Java app boots, the JIT, just-in-time, compiler consumes massive amounts of CPU to optimize bytecode. The HPA sees this boot time CPU spike, thinks it is user traffic, and scales out further. You must configure the HPA to ignore unready pods, or switch your scaling metric from CPU to HTTP requests per second.
Senior Follow-Up 3 The Day 2 Migration Reality. You want to move away from CPU scaling entirely and use Keda to scale based on Kafka QLag. How do you implement this safely without dropping current traffic?
Answer: you cannot run a standard HPA and Keda scaled object pointing to the same deployment simultaneously. They will fight each other and cause severe thrashing. We must deploy the new Keda scaled object alongside a canary deployment of the application. We use an API gateway to slowly bleed 10% of traffic to the Keda managed canary, verifying its behavior before deleting the legacy HPA.
Senior Follow-Up 4 Curveball. You tune the HPA perfectly. Traffic hits, the HPA instantly requests 50 new pods, but you look at the cluster and all 50 pods are stuck in the pending state. The cluster autoscaler is working, but it takes 4 minutes to boot a new EC2 instance. How do you beat the cloud provider's hardware boot time?
Answer: before assuming we can make AWS boot faster, a senior looks at cluster capacity. The hardware boot time is a hard constraint. To bypass it, we deploy balloon pods or pause pods. These are dummy pods that consume minimal CPU but request massive amounts of RAM. They force the autoscaler to keep spare EC2 instances warm. When the real traffic hits, we assign the real pods a higher priority class, forcing Kubernetes to instantly evict the balloon pods and place the real pods on the pre-warmed nodes.
Pro tip: the request metric illusion.
CPU is the worst metric for autoscaling modern web services. It is a lagging indicator. By the time CPU is high, latency is already terrible. The absolute best metric for scaling is concurrent and flight requests. If your app can handle exactly 50 concurrent requests before slowing down, configure your autoscaler to scale on that exact mathematical threshold. You will scale preemptively before CPU ever spikes.
The Senior Dev Ops Incident 12 The Stateful Split.
It is Friday night. Customer support reports a bizarre issue. Users are logging in and seeing account balances from 3 hours ago while others see current data. You check the backend MongoDB replica set deployed as a Kubernetes stateful set. The cluster is active, but the data is completely fragmented. Some reads return new data, some return dangerously stale data. The database consensus is shattered, and data is silently diverging across your replicas.
Symptoms, the panic moment.
Here is what the observability stack showed us during this data corruption event. 1. App metrics read latencies are completely normal, masking the severity of the issue. 2. DB logs, the primary database node logs, show constant election battles and connection resets from the hostname Mongo0. 3. K8 state, running kubectl get pods shows that Mongo0 was restarted 45 minutes ago and is currently running. 4. Node state, one of the AWS worker nodes in the cluster is marked as not ready. The application is successfully querying the database, but the database itself is suffering an identity crisis.
Hypothesis, thinking like a senior.
A junior engineer might assume this is an application caching bug. As a senior, I formulate hypotheses based on distributed state. Hypothesis 1, application cache invalidation, ruled out. Bypassing RIDIs and querying the database directly still yields wildly inconsistent data. Hypothesis 2, network partition between replicas, ruled out. The active nodes can perfectly ping each other via their headless service. Hypothesis 3, stateful identity collision. A zombie pod is corrupting the strict at most one execution guarantee of the stateful set. Decision tree signal. If stateful replicas show diverging data, consensus is flapping, and a worker node recently failed, then always suspect a Kubernetes stateful set split brain via forced deletion. Investigation. The 6-step debugging masterclass.
Step-by-step stateful debugging.
We need to mathematically prove why the database cluster is fighting itself. We execute the following discovery steps. 1. Trace the election first. We query the MongoDB replica set status, rs.status parentheses. We see two distinct IP addresses simultaneously claiming the identity of the Mongo0 pod. 2. Check pod state. Second, we run kubectl get pods-o wide. Kubernetes reports Mongo0 is running happily on node B with IP 10.0.1.50. 3. Check the dead node. We look at the not ready node A. The Kubernetes control plane believes this node has been completely offline for 45 minutes. 4. Verify cloud provider. We check the AWS EC2 console. Node is not powered off. It is passing AWS status checks, meaning it only lost communication with the Kubernetes control plane. 5. Inspect the zombie. We SSH into node out of band and run Crictal PS. The original Mongo0 container, IP 10.0.2.100, is still actively running. 6. Root cause identified. At this point, the catastrophe is clear. 45 minutes ago, Node went not ready. An impatient engineer saw Mongo0 stuck in terminating and ran kubectl delete pod Mongo0 force. This bypassed the safety locks. Kubernetes spawned a new Mongo0 on node B, but the old pod never died. Both pods are now running with the exact same hostname, writing conflicting data, causing a catastrophic split brain. Let's look at the exact cluster states that prove this architectural failure. The proof: the zombie pod. The database logs reveal the truth. The Mongo cluster is receiving traffic from two different IPs simultaneously, both broadcasting the identical internal DNS hostname Mongo0. SSHing into the not ready node proves the container is still running. The kubelet lost its connection to the API server, but the container runtime kept the application perfectly alive.
The fix, fencing and reconciliation.
We must physically sever the zombie pod's access to the network and storage before we can rebuild the database. Senior warning: never use --force --grace period equals 0 on a stateful set pod. When you force delete, you are lying to Kubernetes. You are promising the orchestrator that the pod is physically dead. If you are wrong, you will instantly corrupt your distributed state. Fencing the dead node. Because the Kubernetes control plane cannot communicate with the node, we bypass Kubernetes entirely. We use the AWS API to forcibly power off the underlying EC2 instance. This is known as fencing. With the zombie pod physically eliminated, we connect to the legitimate Mongo0 pod and force it to drop its corrupted transactions and resync a clean dataset from the current primary node.
Prevention and guardrails, the post-mortem.
To prevent human error from corrupting databases in the future, we implement these systemic guardrails. 1. Automated fencing. We deploy the node auto repair NAR or machine health check operator. If a node goes not ready for 5 minutes, the operator automatically terminates the cloud instance, guaranteeing pod death before rescheduling. 2. Storage topology limits. We enforce read-write once RWO EBS volumes. If an EBS volume is bound to a node, AWS physically prevents the new pod on node B from attaching the volume until node A releases it, acting as a hardware-level safety net. 3. RBAC restrictions. We update Kubernetes RBAC roles to explicitly deny developers and mid-level engineers the ability to use the delete pod command on resources located in the stateful namespaces. A senior engineer designs systems where doing the wrong thing is physically impossible. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does a regular deployment easily recover from a not-ready node, but a stateful set gets stuck in terminating?
Answer: a deployment provides at least one semantics. It does not care about identity, so if a node fails, it instantly spins up a replica elsewhere. A stateful set provides strict at most one semantics. It guarantees that Mongo 0 will never exist twice. Therefore, the stateful set controller will permanently block the creation of a new Mongo 0 until it receives cryptographic proof from the kubelet that the old container is completely dead.
Senior follow-up 2, the scale and trade-off trap. You rely on EBS read-write once RWO as a hardware safety net. What is the operational trade-off of this architecture during a legitimate node failure?
Answer: RTO, recovery time objective degradation. If a node legitimately dies, the EBS volume remains attached in the AWS console. The Kubernetes attach/detach controller will wait exactly 6 minutes before timing out and forcing the detachment via the Cloud API. This means your database replica will be offline for a minimum of 6 minutes during every node failure.
Senior follow-up 3, the day 2 migration reality. You want to migrate your databases out of Kubernetes and into a managed service like AWS RDS to avoid this entirely. However, the database is 5 terabytes and must be migrated with 0 downtime. How do you do it?
Answer: we use Change Data Capture, CDC, with a tool like Debezium or AWS Database Migration Service, DMS. We take an initial snapshot to replicate the 5 terabytes of baseline data to RDS. Then, DMS continuously reads the transaction logs, oplog, of the Kubernetes MongoDB to stream real-time changes to RDS. Once replication lag hits 0, we repoint the application's DNS record to the RDS endpoint.
Senior follow-up 4 Curveball. You successfully stop the zombie EC2 instance. The new pod on the healthy node finally spins up. However, the database container instantly crashes. You check the logs and see fatal error, unable to acquire lock on /data/db/mongod.lock. Why is it crashing?
Answer: before randomly deleting files, a senior diagnoses the storage state. The underlying persistent volume, EBS, was forcefully ripped away from the running zombie pod when we stopped the instance. This caused an unclean shutdown. The database engine never had a chance to delete its process lock file. To fix this safely, we must mount the volume to a recovery container, verify the journal file integrity, FSCK, clear the lock file, and only then allow the database to boot.
Pro tip, the power of out-of-band access.
When the Kubernetes control plane says unknown or not ready, it does not mean the server is dead. It just means the kubelet API is unreachable. Always maintain out-of-band access, like AWS Systems Manager Session Manager or direct SSH key access, independent of Kubernetes. During a catastrophic failure, your ability to bypass the orchestrator and inspect the raw Linux host will save your cluster.
Category 4 Wrap-up, the physics of state and scale.
Scaling and state represent the ultimate test of an engineer's understanding of distributed systems. We have seen that the horizontal pod autoscaler is often a lagging indicator that must be architecturally tuned for velocity or bypassed entirely with pre-warmed capacity. More importantly, we have learned that stateful workloads require physical fencing and strict identity locks. A senior DevOps engineer knows that while compute is ephemeral, data is permanent. Protecting that data during node failures and traffic spikes is not just a technical task, it is the primary mission of the platform. If you cannot guarantee data integrity during a scale-out or a failover, your cluster is nothing more than a house of cards.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But even the most resilient cluster architecture cannot save the business if the code reaching it is fundamentally flawed, or if the process of getting it there is broken. We are now moving from the runtime environment to the delivery engine, the CI/CD pipelines.
Category 5, CI/CD and Delivery Engineering.
Focus: ensuring the code that works on a laptop works in production. This is the heart of the developer experience. In this section, we solve the incidents that occur when the green light in your pipeline is a lie. We will explore why artifacts drift across environments, how race conditions in rollouts cause intermittent 500-level errors, and why a successful rollback can sometimes be more dangerous than the original failure. This section is about building a delivery engine that developers can trust with their lives, ensuring that every deployment is a non-event rather than a high-stakes gamble.
The Delivery Engine Incidents.
We will be performing deep dives into these 6 critical delivery failures. 13. The green pipeline false positive, why mocks pass but real data fails due to environment mismatch. 14. Pipeline success but broken production, solving the mystery of environment parity and secret desync. 15. Non-reproducible failures, dealing with the nightmare of environment and build cache drift. 16. Artifact drift, when inconsistent images between staging and production lead to silent bugs. 17. Deployment race condition, fixing parallel rollout timing issues that cause 500-level errors. 18. Rollback-induced failure, the danger of schema and state incompatibility after a revert. Let's start with the most dangerous lie in DevOps, the pipeline that says green while the code is broken.
The Senior DevOps Incident 13, the green pipeline false positive.
It is Tuesday at 2 p.m. A developer merges a critical feature into the main branch. The CI/CD pipeline runs flawlessly. 1,500 unit tests pass, the integration suite is 100% green, and the deployment to production is successful. 5 minutes later, the checkout page starts throwing 500 internal server errors for 20% of users. The pipeline told you the code was perfect, but the real world is proving it wrong. You are dealing with a green pipeline false positive.
Symptoms: the panic moment.
Here is the data that revealed the gap between the laboratory and the real world. 1. CI results: Jenkins and SonarQube report 100% test pass rate and 90% code coverage. 2. Production metrics: a sharp spike in 500 errors specifically on the process payment endpoint. 3. Log analysis. Production logs show database timeout and encoding exception for specific payload types. 4. Environment parity. The staging environment is perfectly healthy, making the bug non-reproducible in the lower environments. The system is passing the logic tests but failing the environment reality. The safety net has a massive hole.
Hypothesis, thinking like a senior.
A junior engineer might suspect the deployment itself failed. As a senior, I analyze the data to code interaction. Hypothesis 1, deployment version mismatch. Ruled out. Container tags in production match the successfully tested CI artifact. Hypothesis 2, infrastructure configuration change. Ruled out. Terraform state shows no changes to the database or network in the last 24 hours. Hypothesis 3, synthetic data fallacy. The test suite uses mocks and fakes that assume ideal data shapes and zero latency network conditions, whereas production has messy data and real-world latency. Decision tree signal. If the pipeline is green, staging is healthy, and production is failing with data-related errors, then always suspect a failure in mock to reality parity. Investigation. The 6-step debugging masterclass.
Step-by-step delivery forensic work.
We need to expose the lie in the testing suite. We execute these steps. 1. Isolate failing payloads. We extract the exact JSON payloads from production logs that triggered the 500 errors. 2. Compare with CI mocks. We compare the prod JSON with the mock data used in the CI pipeline. We find the prod data contains UTF-8 characters and null fields that the mocks never included. 3. Analyze network latency. We check the trace duration of the database call in CI. It is 0.5 milliseconds because it uses an in-memory database. In prod, it is 45 milliseconds. 4. Stress test locally. We feed the production captured dirty data into the local test runner. The tests fail instantly. 5. Trace race conditions. We realize that the 45 milliseconds latency in prod exposed a race condition in the code that 0.5 milliseconds latency in C I completely hid. 6. Root cause identified. Mock poisoning and latency blindness. The test suite was built in a laboratory environment with perfect data and impossible speeds, creating a false sense of security for backward incompatible code changes. Let's look at the code comparison that proved our testing suite was a lie. The proof, mock versus reality mismatch. The production data contains non-standard characters and null values. Because the developer only tested against John Doe, the edge case logic for these characters was never triggered in the CI pipeline. This is the critical part. Because the CI mock was too fast, the second request never arrived before the first one finished. The race condition only exists in the slow, real world of production.
The fix, data-driven testing and canaries.
We need to move away from synthetic safety and move toward reality-based delivery. Senior warning, do not try to make your CI environment 100% identical to production. It is physically impossible and will make your pipelines painfully slow. Instead, use deployment strategies that verify code against real traffic before a full rollout. Here is the YAML implementation for canary analysis, using Argo rollouts to verify production success metrics. Disclaimer, always test code in a non-production environment. We implement an Argo analysis template. Instead of trusting the green pipeline, we deploy the new code to only 5% of users. If the error rate exceeds 1% on that small subset, the system rolls back automatically before the other 95% of users are affected.
Prevention and guardrails, the post-mortem.
To prevent green lies in the future, we implement these systemic guardrails. 1. Property-based testing. We move from unit tests to property-based testing, which automatically generates thousands of random dirty inputs to find edge cases. 2. Shadow traffic. We implement mirroring in Istio. We send a copy of live production traffic to a shadow version of the new code to compare results without affecting the user. 3. Contract testing. We implement packed or postman contract tests to ensure the interface between microservices is verified using real schema expectations, not just local mocks. A senior engineer knows that a test suite is just a theory. Only production is the truth. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why is test coverage often a misleading metric for senior DevOps engineers?
Answer: coverage measures which lines of code were executed, but not which states of data were tested. You can have 100% line coverage but 0% data shape coverage. Coverage is a metric of activity, not a metric of quality.
Senior follow-up 2, the scale and trade-off trap. You want to implement shadow traffic for every microservice. What is the hidden load trade-off?
Answer: shadow traffic doubles your compute and database costs. Every request is processed twice. Furthermore, you must ensure the shadow service is correctly isolated so it does not trigger side effects like duplicate emails or double charging a customer.
Senior follow-up 3, the day 2 migration reality. You are migrating from a monolith to microservices. The monolith tests were all green. Now everything is failing in prod. What is the most likely gap?
Answer: partial failures and retries. In microservices, the network can fail partially. If your tests do not simulate network flappiness or timeouts, you have a false positive. You must implement chaos engineering in your CI pipeline to test how the app behaves when its dependencies are unreachable.
Senior follow-up 4, curveball. You implement canary deployments. The canary is healthy for 30 minutes, so you roll out to 100%. 1 hour later, the whole system crashes with an out-of-memory error. Why?
Answer: memory leaks are cumulative. A 30-minute canary window is too short to detect a leak that takes 2 hours to saturate the heap. For stateful or memory-intensive services, the canary soak time must be proportional to the expected memory growth rate.
Pro tip, the synthetic traffic replay.
To bridge the gap between CI and production, implement a log replay system using tools like GoReplay. This allows you to capture a sample of real, messy production traffic and shadow replay it against your new code in a staging environment. It is the only way to find race conditions and encoding bugs that local mocks will never catch.
The Senior DevOps Incident 14, pipeline success but broken production.
It is Friday at 3 p.m. You push a minor update to the API gateway. Jenkins says success. Argo CD says synced. The Kubernetes pods are all running, but the entire application is effectively down. Every request returns a 403 forbidden. You have not changed the security logic. You have not changed the code. The pipeline says everything is perfect, but the configuration of the environment has silently drifted into a dead state.
Symptoms, the panic moment.
Here is the behavior of the successfully deployed but broken application. 1. Pod status: all pods are in a running state with 0 restarts. 2. Health checks, readiness and liveness probes are returning 200 OK. 3. Error pattern: 100% of user requests are failing with 403 forbidden or access denied. 4. Environment comparison: staging is working perfectly with the exact same container image. The application is technically alive, but it is functionally disconnected. The infrastructure is healthy, but the configuration is toxic.
Hypothesis, thinking like a senior.
A junior engineer might suspect a hacker or a network firewall issue. As a senior, I analyze the context of the process. Hypothesis 1, ingress or WAF blocking, ruled out. Testing via kubectl port forward directly to the pod still yields a 403 error. Hypothesis 2, database permission change, ruled out. The DB logs show no failed login attempts. Hypothesis 3, secret or environment desync. The application successfully booted, but it is using an outdated or missing API key for the identity provider, causing it to reject all incoming tokens. Decision tree signal: if the pod is running, probes are green and 100% of traffic is 403 forbidden means, then always suspect an environment variable or secret mismatch. Investigation: the 6-step debugging masterclass.
Step-by-step context discovery.
We need to see what the application actually sees inside its own container. We execute these steps. 1. Inspect the live config. We run kubectl exec into the running pod and print the environment variables using the env command. 2. Compare with Git. We compare the live OIDC_client_ID with the value in the Helm chart. They match. 3. Check secret mounts. We check the mounted secrets in /etc per secrets and find the file exists with correct permissions. 4. Verify secret content. We read the content of the secret and find it contains an old, revoked key that was rotated in the Cloud Console but never updated in Kubernetes. 5. Audit the pipeline. We check the logs and realize the pipeline only deploys the deployment manifest, but the secret is managed manually by the security team. 6. Root cause identified. Fragmented configuration management. The pipeline deployed the new code requiring a new key, but it had no mechanism to verify or update the external secrets it depends on. Let's look at the secret mismatch that paralyzed the authentication layer. The proof, the descent secret. The pod is running with an old key. It successfully passed health checks because the health endpoint does not require an API key to respond. It is a false positive for the readiness probe. The source of truth in the cloud is updated, but the Kubernetes secret was never synchronized. The green pipeline was completely blind to this external dependency failure.
The fix: unified secret synchronization.
We need to stop managing secrets manually and move to an automated pull model where Kubernetes is always in sync with the cloud provider. Senior warning: do not store secrets directly in Git. If the encryption key is lost, your disaster recovery is impossible. Instead, use a controller that maps external secrets to Kubernetes natively. Here is the YAML configuration for the external secrets operator to automate secret synchronization with cloud providers. Disclaimer: always test code in a non-production environment. By implementing the external secrets operator, we create a self-healing configuration. Every 5 minutes, Kubernetes will poll the cloud provider and update itself automatically if the key is rotated.
Prevention and guardrails: the post-mortem.
To prevent successful but broken deployments in the future, we implement these guardrails. 1. Config hash annotation. We add a checksum of our config maps and secrets to the pod annotations to force a rolling restart when a configuration change is detected. 2. Deep health checks. We update the readiness probe to perform a no-op call to the identity provider to verify that its API key is actually valid. 3. GitOps for everything. We move all infrastructure, including secret definitions, into Argo CD to make desyncs visible on the dashboard. A senior engineer does not just deploy the binary, they deploy the entire operational context. The senior follow-up stack.
Senior follow-up 1: mechanism deep dive. Why did the kubectl apply command succeed, even though the configuration was broken?
Answer: Kubernetes is an asynchronous, declarative system. The API server only validates that the YAML is syntactically correct, and you have permission to run it. Success only means the desired state has been recorded in etcd.
Senior follow-up 2: the scale and trade-off trap. You implement config hash annotations. What is the risk during a massive cluster-wide secret rotation?
Answer: a thundering herd outage. If 500 microservices all detect the change and restart simultaneously, you will lose your entire cluster capacity. You must use pod disruption budgets to ensure the restart happens gradually.
Senior follow-up 3: the day 2 migration reality. How do you handle secrets across multi-cloud, AWS and Azure, without manual copying?
Answer: use a centralized secret vault like HashiCorp Vault. Both AWS and Azure clusters point to the same vault instance. We use the Vault Agent Injector to mount secrets directly into pod memory.
Senior follow-up 4: curveball. You have fresh keys and the pod restarted, but you still get 403 errors. The pod env shows the OLD key. How?
Answer: if you are using a process manager like PM2 inside your container that was not designed to propagate SIGTERM correctly, the old process might still be running. Alternatively, if the variable was hard-coded into the Docker image during the build phase, it will override the Kubernetes manifest.
Pro tip: the secret of immutable config.
Never update a secret or config map in place if you want safe rollbacks. Treat configuration as version artifacts. Append a version suffix to your secret names like auth secret v1. When you need to rotate, create v2 and update the deployment to point to it. This ensures that if the new config is broken, you can roll back instantly, and the pods will still have access to the old working key.
The Senior Dev Ops Incident 15: the ghost in the runner, non-reproducible failures.
It is 11 p.m. A critical security patch is being deployed. The build fails on the CI runner with a segmentation fault during the compilation of a native C++ extension. You try to reproduce it on your local machine. It works perfectly. You try it on a dedicated debug server. It works perfectly. Every time the code hits the shared CI cluster, it fails intermittently. You are chasing a ghost in the infrastructure, and the release is blocked by an invisible environment drift.
Symptoms: the panic moment.
Here is the behavior of the non-deterministic build failure. 1. Local reproduction. The build is 100% stable on developer laptops and standalone build servers. 2. Failure pattern. The build only fails on shared CI runners that have processed hundreds of previous builds. 3. Error logs. The logs show file not found or library version mismatch for dependencies that should be pinned. 4. Cache behavior. Clearing the application level cache, like node_modules or pip cache, does not solve the problem. The build is not failing because of the code change. It is failing because of the residue left behind by previous executions.
Hypothesis: thinking like a senior.
A junior engineer might suspect a hardware failure on the runner. As a senior, I analyze the hermeticity of the build process. Hypothesis 1, flaky unit tests, ruled out. Compilation is failing before the tests even begin. Hypothesis 2, network intermittency during dependency fetch, ruled out. The failure happens during the local linking phase, not the download phase. Hypothesis 3, leaky build environment. The CI runner is not a clean room. Previous builds are leaking global state, shared libraries, or poisoned cache layers into the current process. Decision tree signal. If the build fails only on shared infrastructure and is non-reproducible locally means, then always suspect leaky environment drift or cache poisoning. Investigation. The 6-step debugging masterclass.
Step-by-step build forensic work.
We must isolate the runner and prove it is dirty. We execute these steps. 1. Inspect shared volumes. We check the CI configuration, GitHub Actions/GitLab, and find that /tmp and /var/lib/docker are shared across jobs. 2. Compare environment variables. We run the env command in CI and compare it to our local machine. We find a hidden ld_library_path set by a previous job. 3. Verify compiler versions. We run gcc-- version on the runner. It returns a different minor version than the one specified in our Docker file. 4. Analyze Docker layer cache. We realize the runner is using an old cached version of a base image that was manually updated on the host. 5. Trace system calls. We use trace during the build to see which exact file path is causing the segmentation fault. 6. Root cause identified, global cache poisoning. A previous build on the same runner installed a conflicting version of libssl into a shared host directory. Because the Docker daemon was configured to share the host's network and volumes for speed, our build accidentally linked against the wrong library. Let's look at the trace and configuration that revealed the leaky environment. The proof: the poison path. The trace output proves that the compiler is ignoring the project local library and is instead opening an old version of libssl from a global system path. This library was left behind by a different project's pipeline. We found a poisoned environment variable. A previous job on the same shared runner failed to clean up its environment, and because the runner process was reused, our job inherited this toxic path.
The fix: hermetic builds and ephemeral runners.
We must move away from mutable shared runners and move toward hermetic build environments where every job starts from an absolute zero state. Senior warning: do not just clear the cache as a fix. That is a temporary patch. If your build process relies on global state, it is fundamentally broken. True senior engineers enforce container-in-container isolation, where nothing from the host can leak into the build. Here is the YAML implementation for GitLab CI to enforce hermetic build isolation via ephemeral runners. Disclaimer: always test code in a non-production environment. This prevents image drift. Even if an image with the same name exists on the host, the runner is forced to pull the official version from the registry, ensuring the base environment is always what you expect. By using Docker in Docker with a fresh service container for every job, we ensure that the Docker daemon's internal state, layers, images, volumes, is completely destroyed after the build finishes. No residue can leak to the next job.
Prevention and guardrails: the post-mortem.
To eliminate works on my machine syndrome forever, we implement these guardrails. 1. Bazel and Buck migration. We investigate moving to hermetic build tools like Bazel, which track every single input and environment variable as a hash, ensuring the same input always produces the exact same output. 2. Ephemeral runners. We migrate from static virtual machines to Keta or Actions Runner Controller Arc, which spins up a fresh Kubernetes pod for every single CI job and deletes it immediately after. 3. Immutable build images. We forbid the use of apt get install inside the CI script. All tools must be baked into a version build image that is scanned and immutable. A senior engineer does not trust the runner. They trust the isolation. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. What is a hermetic build, and why is it the gold standard for senior DevOps?
Answer: a hermetic build is one that is insensitive to the host environment. It provides its own toolchains, compilers, linkers, libraries, rather than using what is installed on the OS. This ensures bit-for-bit reproducibility across any machine, anywhere, at any time.
Senior Follow-up 2 The Scale and Trade-off Trap. You move to pull policy, always and fresh runners for every job. Your build reliability is 100%, but your build time increased from 5 minutes to 25 minutes. How do you handle this trade-off?
Answer: this is the cold start tax. To optimize, we must implement remote caching. Tools like GCS or S3 backends for Docker Build Kit or Bazel allow the runner to pull only the specific compiled blobs it needs over the network, rather than rebuilding, while still maintaining the safety of an ephemeral environment.
Senior Follow-up 3 The Day 2 Migration Reality. You are using shared runners for 1,000 different projects. One project needs a custom kernel module for testing. How do you allow this without compromising the isolation for the other 999 projects?
Answer: you do not. You never allow a single CI job to modify the host kernel. Instead, we use infrastructure tags. We provision a specific, isolated pool of runners with that kernel module pre-installed and use node selectors or tags to ensure only that specific project is routed to those high-risk nodes.
Senior Follow-up 4 Curveball. Your build is hermetic, your runner is fresh, and you have no cache. The build still fails in CI but passes locally. You check the CPU architecture. CI is ARM64 Graviton, and your laptop is x86_64. The code is pure Python. How can an architecture change break a non-compiled language?
Answer: native extensions and dependencies. Even if your code is Python, libraries like NumPy, cryptography, or Pydantic use pre-compiled wheels. If the CI runner pulls the ARM64 version of a library that has a subtle bug or different precision logic than the x86 version, you get an architecture-specific failure that has nothing to do with your code logic.
Pro tip: the binary fingerprint check.
When a build fails only on shared runners, do not trust the logs. Run the command LDD against your compiled binary in both environments. This command reveals the exact file path of every shared library the binary is linking against. If the paths differ by even one character, you have found the environment drift that is poisoning your build.
The Senior DevOps Incident 16. The Mirror of Lies Artifact Drift.
It is Friday afternoon. You just approved the promotion of version 1.4 from staging to production. Staging was tested for 48 hours and was 100% stable. The deployment to production finishes, and immediately the new search feature is missing. You check the logs, the app is running, but it is an old version of the code. You check the image tag, it says v1.4. The tag says you are in the future, but the code says you are in the past.
Symptoms: the panic moment.
Here is the behavior of the artifact drift. 1. Version confusion. The application footer says build 1.3, but the Kubernetes manifest says image search service v1.4. 2. Environment inconsistency. The v1.4 image in staging has the new feature, but the v1.4 image in production does not. 3. Registry state. The container registry shows the v1.4 tag was pushed twice in the last 3 hours. 4. Deployment logs. Argo CD or Jenkins reports a successful sync and a successful rollout with no errors. The tag is a lie. The name of the artifact has stayed the same, but the content has changed underneath it.
Hypothesis: thinking like a senior.
A junior engineer might think Kubernetes is stuck and needs a restart. As a senior, I analyze the immutability of the artifact pipeline. Hypothesis 1: image pull policy mismatch. Ruled out. The image was updated, but it contains the wrong code version entirely. Hypothesis 2, caching at the registry. Ruled out. New pods are being created, meaning the registry is serving an image. Hypothesis 3, mutable tag anti-pattern. The pipeline is rebuilding the image for every environment instead of promoting the same binary, causing a race condition, where a newer, broken build overrode the tested one. Decision tree signal. If the same tag contains different code across environments means, then always suspect a build per environment workflow or mutable tags. Investigation. The 6-step debugging masterclass.
Step-by-step artifact forensics.
We must prove that the v1.4 in staging is not the v1.4 in production. We execute these steps. 1. Compare digests. We pull the image from staging and production and run Docker inspect. We find the SHA-256 digests are different. 2. Audit pipeline logs. We check the Jenkins logs. We find that the deploy to prod job actually triggers a Docker build command again with prod environment variables. 3. Identify the drift. We realize that between the staging build and the prod build, a developer merged a tiny typo fix into the main branch. 4. Analyze build args. We see that the build per environment strategy injected a different API underscore URL during the build phase instead of the runtime phase. 5. Check registry history. We see that search service v1.4 was overwritten. The staging nodes are still running the old SHA, but the new prod nodes pulled the poison new SHA. 6. Root cause identified. Violation of artifact immutability. The pipeline was designed to rebuild rather than promote. This allowed untested code to sneak into the production artifact under an existing, trusted tag name. Let's look at the SHA-256 mismatch that proved our tags were lying to us. The proof, the digest dual. This is the source of truth. In Kubernetes, tags are just pointers. The SHA-256 digest is the actual identity of the content. These two environments are running different code despite having the same version label.
The fix: build once, promote many.
We must kill the build per environment pattern. We will move to a strict promotion model where the exact same SHA-256 digest moves through the pipeline. Senior warning: if your application requires environment-specific logic, like different API URLs, you must inject these at runtime via environment variables or config maps. Never inject environment-specific data during the Docker build phase, or you destroy the immutability of your artifact. Here is the YAML configuration for the CI pipeline to implement immutable SHA-based artifact promotion. Disclaimer: always test code in a non-production environment. By deploying using the Git SHA, which is unique and immutable, we guarantee that the exact binary that passed tests in staging is the one that enters production. There is no possibility of a rebuild introducing new code.
Prevention and guardrails, the post-mortem.
Prevent artifact drift forever. We implement these guardrails. 1. Immutable registry. We configure our container registry ECR/GCR to enable tag immutability. This physically prevents anyone or any pipeline from pushing a new image to an existing tag. 2. Digest pinning. We update our GitOps manifests Argo CD/Flux to use the SHA-256 digest instead of the tag name, for example, app@SHA-256. This makes the deployment 100% deterministic. 3. Admission controllers. We deploy an image policy webhook that rejects any pod creation if the image tag is latest or does not follow our strict versioning schema. A senior engineer does not care about the name of the version. They care about the integrity of the hash. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why is the latest tag considered a security risk in senior DevOps?
Answer: non-determinism and lack of auditability. Latest is a rolling pointer. If a pod restarts and pulls latest, you have no guarantee it is the same code that was running 5 minutes ago. Furthermore, if a security breach occurs, you cannot easily roll back to a known good state because latest has already moved forward.
Senior follow-up 2, the scale and trade-off trap. You move to tag immutability. Now, when a developer wants to hotfix a typo in version 1.4, they are forced to create version 1.4.1. This increases the number of images in your registry by 500%. How do you manage the cost?
Answer: lifecycle policies. We implement registry rules that automatically delete any image older than 90 days unless it is tagged as prod stable. We trade storage cost for deployment safety. Storage is cheap, but a corrupted production environment is expensive.
Senior Follow-up 3, the Day 2 Migration Reality. You are using Build Once, Promote Many, but your staging environment is on x86 and your new prod environment is on ARM Graviton. How do you promote one artifact across two different architectures?
Answer: multi-arch manifests. We use Docker builds to create a single manifest list. This manifest points to two different SHAs, one for x86, one for ARM under the same tag name. When the node pulls the image, it automatically selects the SHA that matches its architecture. The artifact is now a logical group, not just a single binary.
Senior Follow-up 4 Curveball. You are pinning by SHA 256 Digest. You deploy to prod. The pod starts, but it crashes because it cannot find its configuration file. You check the image locally, the file is there. You check the staging pod, the file is there. Why is the same SHA 256 failing in prod?
Answer: mount overlays. Senior engineers know the image is not the only source of truth. In production, you might be mounting a config map or a secret to the same directory where the app expects its files. The Kubernetes mount shadows the files inside the Docker image. The artifact is identical, but the runtime environment has blindfolded the application.
Pro tip, the registry as the gatekeeper.
Use image signing, SigStore, or Cosign. In a truly senior environment, the CI pipeline signs the image digest after all tests pass. We then install an admission controller in Kubernetes that refuses to run any image that does not have a valid staging pass signature. This ensures that even if someone manually pushes a v1.4 tag to your registry, it will never run in production because it lacks the cryptographic proof of quality.
The Senior Dev Ops Incident 17, the deployment race condition.
It is Thursday at 11 a.m. You are performing a standard rolling update for the core API. The CI pipeline is green and the health checks are passing. However, during the 5-minute rollout window, your monitoring dashboard lights up with intermittent 502 bad gateway and 504 gateway timeout errors. As soon as the rollout finishes, the errors vanish. This happens every single time you deploy. You are facing a race condition between the Kubernetes control plane and your network ingress.
Symptoms, the panic moment.
Here is the behavior of the network during the rolling update. 1. Error pattern. 500-level errors occur only when a new pod replaces an old pod. 2. Persistence. The errors are highly intermittent, affecting roughly 1 to 2% of total traffic during the update. 3. Readiness state. All new pods are marked as ready in Kubernetes before the old pods begin their termination phase. 4. Ingress logs. The Nginx ingress logs show upstream prematurely closed connection or no live upstreams. The orchestrator believes the transition is safe, but the network layer is still sending traffic to pods that are already dying.
Hypothesis, thinking like a senior.
A junior engineer might suspect the application is crashing on startup. As a senior, I analyze the synchronization of the distributed state. Hypothesis 1, insufficient CPU during startup. Ruled out. Metrics show the new pods have plenty of headroom and are not being throttled. Hypothesis 2, liveness probe failure. Ruled out. The pods are not restarting. They are being terminated intentionally by the deployment controller. Hypothesis 3, endpoint propagation latency. There is a delay between the pod receiving a SIG-term and the ingress controller removing that pod's IP from its active load balancing pool. Decision tree signal. If 500-level errors occur only during rollout and vanish immediately after means, then always suspect a lack of synchronization between SIG-term and endpoint removal. Investigation, the 6-step debugging masterclass.
Step-by-step propagation forensic work.
We must prove the timing mismatch between the pod and the ingress. We execute these steps. 1. Monitor endpoints. We run kubectl get endpoints-w during a rollout to watch the IP addition and removal speed. 2. Trace SIG-term. We check the application logs to see exactly when it receives the termination signal from Kubernetes. 3. Compare timestamps. We compare the ingress 502 error timestamps with the pod termination timestamps. They overlap perfectly. 4. Check connection draining. We inspect the Nginx ingress configuration for worker shutdown timeout. It is set to a default that is too aggressive. 5. Analyze app exit logic. We find the application exits immediately upon receiving SIGTERM without waiting for active connections to finish. 6. Root cause identified. 0-second grace period. The application kills its listener immediately on SIGTERM, but the ingress controller takes 2 to 3 seconds to update its routing table. During that 3-second gap, the ingress sends traffic to a socket that no longer exists. Let's look at the configuration and logs that prove this race condition. The proof, the propagation gap. This confirms the ingress controller had an active connection or tried to open one, but the pod had already dropped the socket. The network layer was not notified fast enough.
The fix, implementing graceful connection draining.
We must force the application to wait for the network layer to synchronize before it is allowed to exit. Senior warning. Increasing the termination grace period seconds alone will not fix this. You must implement a pre-stop hook to keep the container alive, while the endpoints controller propagates the removal of the IP across the cluster. Here is the YAML implementation for Kubernetes lifecycle hooks to ensure graceful connection draining during rollouts. Disclaimer: always test code in a non-production environment. This is the most effective senior-level fix. When Kubernetes decides to kill the pod, it first runs this sleep 10 command. The app stays alive and continues to serve existing traffic. During these 10 seconds, the endpoints controller successfully removes the pod IP, ensuring no new traffic arrives.
Prevention and guardrails, the post-mortem.
To ensure zero downtime deployments forever, we implement these guardrails. 1. Minimum pod age. We set min-ready seconds in the deployment to ensure Kubernetes waits for the new pods to stabilize before killing more old pods. 2. Max surge/unavailable tuning. We set max unavailable 0 and max surge 25% to ensure we never lose capacity during a rollout. 3. Load testing during deploy. We integrate K6 or Locust into the pipeline to run a low-level load test specifically, while the rollout is happening to catch 500-level regressions. A senior engineer understands that ready in Kubernetes does not mean ready in the global routing table. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does Kubernetes have a delay in removing a pod IP from the service endpoints?
Answer: it is a distributed eventual consistency problem. When a pod is marked for termination, the endpoints controller must detect the change, update the endpoint object, and then every kube proxy and ingress controller across the cluster must watch that change and update their local IP tables or Nginx configurations. This propagation takes time, usually between 1 and 5 seconds.
Senior follow-up 2, the scale and trade-off trap. You added a 10-second pre-stop sleep to all 200 microservices. What is the trade-off regarding your CI/CD velocity?
Answer: deployment duration inflation. If you have a rolling update with max unavailable 1 and 10 replicas, you just added 100 seconds of mandatory waiting to every single deployment. At scale, this can frustrate developers. The trade-off is high availability versus deployment speed.
Senior follow-up 3, the day 2 migration reality. You are moving to a service mesh like Istio. Does the pre-stop sleep still apply?
Answer: yes, but it becomes more complex. You also need to ensure the Istio sidecar Envoy stays alive longer than the application container. If the sidecar dies first, the app loses its network path before it can finish its pre-stop sleep. You must use proxy.istio.io/config to set a termination drain duration for the sidecar.
Senior follow-up 4, Curveball. You have pre-stop sleep configured, but during a rollout, you see the pods being killed instantly, ignoring the 10-second sleep. Why?
Answer: constraint scenario. If your termination grace period seconds is set to a value lower than your pre-stop sleep time, Kubernetes will forcefully sig-kill the container as soon as the grace period expires. A senior engineer always ensures the grace period is at least 30 seconds longer than any lifecycle hook or application shutdown time.
Pro tip, the termination grace margin.
Always set your termination grace period seconds to at least 45 to 60 seconds for Java or Node.js applications. A senior engineer ensures that the grace period is the sum of the pre-stop sleep time, the time it takes for the app to flush its internal buffers, and a 10-second safety margin. If the grace period is too short, the kubelet will sig-kill the app before the ingress has finished rerouting traffic.
The Senior DevOps Incident 18, the rollback-induced failure.
It is Friday at 4 p.m. You just deployed version 2.0 of a service. The deployment fails because of a critical bug in the business logic. You immediately hit the rollback button in Argo CD to revert to version 1.0. Instead of fixing the issue, the error rate spikes to 100%. Version 1.0, which was perfectly stable an hour ago, is now crashing on startup. You have entered a state of point of no return failure.
Symptoms, the panic moment.
Here is the catastrophic behavior during the rollback attempt. 1. Rollback state version 1.0 pods are in a crash loop backoff state. 2. Error message fatal error column users middle underscore name does not exist in the application logs. 3. Database state the database schema was successfully upgraded by version 2.0 before it failed. 4. Blast radius the entire service is down, and the automated safety net has just made the outage permanent. The code is being rolled back, but the state of the database is living in the future. The two are no longer compatible.
Hypothesis, thinking like a senior.
A junior engineer might try to roll back the database. As a senior, I analyze the migration strategy. Hypothesis 1, cache corruption, ruled out. Flushing RIDIs does not solve the SQL error. Hypothesis 2, wrong environment variables, ruled out. The rollback reverted the config maps correctly. Hypothesis 3, backward incompatible schema change. Version 2.0 performed a destructive schema migration, like renaming or deleting a column, that version 1.0 requires to function. Decision tree signal. If a rollback of a stable version causes a crash loop backoff with a missing schema error means, then always suspect a backward incompatible database migration. Investigation. The 6-step debugging masterclass.
Step-by-step state forensic work.
We must prove the schema mismatch. We execute these steps. 1. Audit migration logs. We check the logs of the init container or the migration job that ran with version 2.0. 2. Inspect database schema. We run \d users in Postgres and confirm that the column middle underscore name has been dropped. 3. Verify v1.0 requirements. We check the version 1.0 source code and confirm it performs a select star which expects that specific column. 4. Analyze the migration strategy. We realize version 2.0 used a destructive migration instead of a multi-phase expand contract approach. 5. Check backup viability. We check if we can restore only the schema from a snapshot. We realize it would take 2 hours. 6. Root cause identified. Destructive migration path. The team moved the middle underscore name data to a new profiles table and deleted the original column in a single transaction. This created a point of no return where a code-only rollback is impossible. Let's look at the migration code that killed our ability to roll back. The proof, the destructive migration. This is the fatal line. By dropping the column immediately, the team made version 1.0 of the code obsolete. This is a violation of senior-level deployment safety rules.
The fix, the expand contract pattern.
We must never perform destructive changes in a single release. We must follow a multi-deployment sequence to maintain backward compatibility. Senior warning, a rollback is not a strategy. It is a last resort. If you do not test your migrations for backward compatibility, your rollback will fail exactly when you need it most. You must treat database changes as forever forward. Here is the SQL implementation for a safe database migration, following the expand contract architectural pattern. Disclaimer, always test code in a non-production environment. This is the key. By keeping the old column active, version 1.0 remains compatible. If v2.0 has a bug, you can roll back to v1.0 safely because the data it expects is still there.
Prevention and guardrails, the post-mortem.
To prevent rollback catastrophes, we implement these guardrails. 1. Migration linting. We use a tool like Atlas Provider GORM or SQL lint to automatically detect and block drop column or rename commands in CI. 2. Backward compatibility testing. We add a step in the CI pipeline that attempts to boot version 1.0 against the migrated database schema of version 2.0. 3. Decoupled migrations. We stop running migrations in init containers. We run them as separate, standalone jobs that must be successfully completed before the code deployment begins. A senior engineer knows that the database schema is the contract that code cannot break. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. What is the three-phase migration pattern, and why is it essential for senior DevOps?
Answer: it is the expand, migrate, and contract pattern. It ensures that at any given point in time, at least 2 versions of your code are compatible with the current database state. This allows for zero downtime rolling updates and safe, instant rollbacks.
Senior Follow-up 2 The Scale and Trade-off Trap. You follow the expand contract pattern. For 2 weeks, you are storing data in 2 places, dual writing. What is the risk regarding data consistency?
Answer: split brain at the application level. If your dual write logic has a bug and only writes to one place, your tables will drift. You must implement reconciliation scripts that verify the data in both the old and new columns matches before you perform the final contract phase.
Senior Follow-up 3 The Day 2 Migration Reality. You need to perform a destructive change on a table with 500 million rows. A standard alter table will lock the table for hours. How do you do it?
Answer: we use an online schema change tool like GHOST or PT Online Schema Change. These tools create a ghost table, copy the data in small chunks in the background, and then perform a fast atomic swap to replace the old table without ever locking it for the users.
Senior Follow-up 4 Curveball. You have a safe migration. No columns were dropped. Yet the rollback to v1.0 still fails. You check the logs and see serialization error. Version 2.0 started saving data in a new JSON format that version 1.0 cannot parse. How do you roll back data shapes?
Answer: hidden cause. This is data poisoning. Even if the schema is the same, the data shape inside the columns changed. A senior engineer knows that rollbacks are only for code, not for data. To fix this, you must deploy a version 1.1 which contains the old logic, but adds a compatibility parser to handle the new data shapes created by the failed version 2.0.
Pro tip: the point of no return check.
Add a manual checkpoint in your deployment process called the Migration Sensitivity Audit. If a release contains a database migration, it cannot be an automated autopilot rollout. A senior engineer must manually verify that the migration is non-destructive before clicking Approve. If a destructive change is absolutely required, the team must acknowledge that they are entering a no-rollback zone and prepare an emergency recovery plan before they push the button.
Category 5 Wrap-up. The Delivery Engine Reality.
Category 5 has taught us that a green pipeline is often a dangerous illusion. We have seen that unit tests and mocks are merely theories, and that real-world data and network latency are the ultimate judges of code quality. A senior engineer understands that artifact immutability is non-negotiable, and that rebuilding code for different environments is an invitation for disaster. We have learned that the synchronization of code, secrets, and database schemas is a complex dance where a single misstep can turn a standard rollback into a total system failure. The mission of the delivery engine is not just to move bits from Git to production, but to ensure that the operational context remains consistent and reversible at every single stage.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But even a perfect code delivery pipeline is useless if the underlying infrastructure it relies on is unstable or incorrectly defined. We are now moving from the software delivery layer to the foundation itself. We are entering the world of infrastructure as code and GitOps.
Category 6. Infrastructure as code and GitOps.
Focus when the code that manages the infrastructure causes the outage. In this section, we treat infrastructure with the same rigor as application code. We will explore the nightmare of environment bleed where automation scripts accidentally nuke production data, the infinity loops of GitOps controllers fighting for state, and the circular dependencies that can paralyze your disaster recovery. This is where we see the double-edged sword of automation. It allows us to build at incredible speed, but it also allows a single line of misconfigured HCL or YAML to destroy a global infrastructure footprint in seconds.
The IAC and GitOps incidents.
We will perform reference-grade deep dives into these 4 critical automation failures. 19. The environment bleed when Helm hooks accidentally flush production caches due to logic leakage. 20. Argo CD infinity loop, the catastrophic fight between GitOps desired state and in-cluster controllers. 21. Terraform state ghosting, recovering from dangling state locks and corrupted CI runner executions. 22. Circular dependency, breaking the Route 53, ALB, and ACM validation deadlock that stalls infrastructure rebuilds. Let's begin with the silent danger of automation scripts, the environment bleed.
The Senior DevOps Incident 19. The environment bleed.
It is 10 a.m. on a Tuesday. You are deploying a routine update to a microservice using Helm. The deployment is for the staging environment. However, 10 seconds after the pipeline starts, the production monitoring dashboard turns red. The production Redis cache hit rate drops to 0, and the production database CPU spikes to 100%. You are deploying to staging, but your automation has just reached across the network and nuked your production environment.
Symptoms, the panic moment.
Here is the behavior of the system during this cross-environment failure. 1. Trigger event, a GitLab pipeline for the staging branch is currently in the deploy phase. 2. Production impact, Redis keyspace underscore misses are skyrocketing across all production clusters. 3. Database state, production DB is struggling under a thundering herd of requests that should have been cached. 4. Environment isolation, VPC peering exists between staging and production, which was intended only for database replication. The automation script is executing in the staging context, but is physically connected to the production endpoint.
Hypothesis, thinking like a senior.
A junior engineer might suspect a random hardware failure in Redis. As a senior, I analyze the correlation of the deployment. Hypothesis 1, production traffic spike, ruled out. Ingress logs show a normal request volume. Hypothesis 2, Redis OOM, ruled out. Redis memory usage is low because it is empty. Hypothesis 3, leaky automation logic. A Helm hook or a post-deployment script is using a hard-coded endpoint or a shared secret that points to production instead of staging. Decision tree signal. If a deployment in one environment causes a catastrophic cache or data loss in another means, then always suspect leaky automation logic or hard-coded endpoints. Investigation. The 6-step debugging masterclass.
Step-by-step automation forensics.
We must find the line of code that crossed the environment boundary. We execute these steps. 1. Audit the Helm hooks. We check the template/directory for pre-install or post-upgrade hooks. 2. Inspect hook logic, we find a shell script hook designed to flush the cache so the new version starts with clean data. 3. Trace variable injection, we check how the RIDIS endpoint is passed to this script. It uses a variable called RIDIS_URL. 4. Check secret decryption, we realize the SOPs or sealed secrets decryption failed for the staging secret and the script fell back to a default value. 5. Verify the default. The default value in the Helm chart was hard-coded to the production RIDIS endpoint by the original developer. 6. Root cause identified, logic leakage via default values. The Helm hook executed in the staging pipeline but used a fallback variable that pointed to production. Because the network had a VPC peer, the script successfully connected and executed a flush all command on the production cache. Let's look at the toxic Helm hook that caused the environment bleed. The proof, the leaky Helm hook. This is the disaster. If the RIDIS_URL environment variable is missing or empty, the script defaults to prod RIDIS.internal. During the staging deploy, the variable failed to load, and the script nuked the live production cache.
The fix, strict environment isolation.
We must remove all hard-coded defaults and implement network-level deny rules between environments. Senior warning, never allow your automation to have a default that points to production. It is better for a script to fail with an error than to fail open and execute against the wrong environment. Furthermore, VPC peering between staging and production should be prohibited by default. Here is the YAML implementation, enforcing secure automation logic via explicit environment checks. Disclaimer, always test code in a non-production environment. By adding an explicit check and an exit code, we ensure the script can never fall back to a dangerous default. If the configuration is missing, the deployment fails, and production remains safe.
Prevention and guardrails, the post-mortem.
To prevent environment bleeding forever, we implement these guardrails. 1. Network segmentation. We delete the VPC peering between staging and production. All cross-environment traffic is now strictly routed through an authenticated API gateway or a private link. 2. IAM scoping. We use IAM roles for service accounts, URSA, to ensure the staging CI/CD runner has zero network permission to reach production resources. 3. Linting for defaults. We use kubelinter to scan Helm charts for any hard-coded production strings in shell scripts or environment variables. A senior engineer builds walls between environments that no script can climb. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why are Helm hooks particularly dangerous for environment bleed compared to standard deployment manifests?
Answer, Helm hooks run as independent jobs outside the standard rolling update logic. They often execute with elevated permissions to perform cleanup or migrations. Because they are often one-off shell scripts, they rarely have the same level of validation or error handling as the main application code.
Senior follow-up 2, the scale and trade-off trap. You decided to delete VPC peering and move to private link for safety. What is the trade-off regarding latency and cost?
Answer, complexity and cost. Private link is highly secure, but it requires managing endpoint services and creates a processing fee per gigabyte of data. Furthermore, it adds a small amount of latency compared to native peering. The trade-off is paying for architectural safety to prevent million-dollar outages.
Senior follow-up 3, the Day 2 migration reality. You are moving to a multi-region setup. How do you prevent a global bleed where a change in US East 1 accidentally affects EU West 1?
Answer, regional sharding of state. We ensure that Terraform state files and CI/CD runners are regionalized. A runner in the US region should physically lack the credentials or network path to reach the EU region's secret store or database. We treat regions as completely separate islands of infrastructure.
Senior follow-up 4, curveball. You have perfect network isolation. No VPC peering. No private link. Yet a staging deploy still nuked a production table. You check the logs and see the script used an external DNS name. How did the traffic cross the boundary?
Answer, the public internet. If your database or cache has a public endpoint enabled, even if protected by a password, a script can resolve the DNS and connect over the internet. A senior engineer ensures that production data stores are internal only and lack any public DNS records or IGW routes making them invisible to the outside world.
Pro tip: the bash fail fast rule.
Every shell script used in a Helm hook or CI pipeline should start with set-UO pipe fail. The -U flag is the most critical here. It forces the script to crash immediately if any variable, like redis_URL, is undefined. This prevents the script from ever falling back to a dangerous, hard-coded default that could reach across environment boundaries.
The Senior Dev Ops Incident 20, the Argo CD Infinity Loop.
It is Wednesday at 2 p.m. You open the Argo CD dashboard and notice the sync icon for the core API is spinning rapidly. Every 5 seconds it turns green, then immediately turns yellow. You check the Kubernetes pods and see a rolling update is happening endlessly. New pods are being created and killed in a perfect loop. You haven't touched the Git repository in hours. Your Git Ops controller is now in a deathmatch with the cluster itself.
Symptoms: the panic moment.
Here is the behavior of the oscillating Git Ops state. 1. Argo CD state: the application status is constantly flipping between synced and out of sync. 2. Diff view: Argo CD shows a difference in the spec.replicas field or a specific container image tag. 3. Pod churn: kubectl get pods shows dozens of pods in terminating state and dozens in pending. 4. API load: the Kubernetes API server CPU usage is spiking due to the constant stream of patch requests from Argo CD. The desired state in Git and the live state in the cluster are drifting, being fixed, and drifting again in a recursive loop.
Hypothesis: thinking like a senior.
A junior might try to force sync or restart Argo CD. As a senior, I analyze the conflict of authority. Hypothesis 1: Git repository flapping, ruled out. The Git log shows no recent commits or automated pushes. Hypothesis 2: Argo CD cache corruption, ruled out. Hard refreshing the cache does not stop the oscillation. Hypothesis 3: Dual write conflict. An in-cluster controller, like an HPA or a custom operator, is modifying the same field that Argo CD is trying to manage from Git. Decision tree signal: if Argo CD is endlessly syncing without Git changes and pods are churning means, then always suspect a conflict between Git Ops and an in-cluster controller. Investigation: the 6-step debugging masterclass.
Step-by-step Git Ops forensic work.
We must identify who is fighting Argo CD for control. We execute these steps. 1. Analyze the diff. We open the diff tab in Argo CD. It shows Git wants 3 replicas, but the cluster has 10. 2. Check for HPA. We run kubectl get HPA. We find an autoscaler is active for this deployment. 3. Inspect HPA logic. We see the HPA has scaled the deployment to 10 replicas because of high traffic. 4. Audit the manifest. We check the Git repo and see replicas. 3 is explicitly defined in the deployment.yaml. 5. Observe the fight. We watch the logs. Argo CD sees 10 replicas, thinks it is drift and patches it back to 3. The HPA sees 3 replicas, thinks it is under-provisioned and patches it back to 10. 6. Root cause identified, split authority. The HPA and Argo CD are both trying to manage the replicas field. This causes a rolling restart every time Argo CD fixes the drift, killing the very pods the HPA just created. Let's look at the manifest conflict that triggered the infinity loop. The proof: the split authority conflict. By explicitly defining the replica count in Git while also using an HPA, you have created 2 masters for the same field. Argo CD will always win the battle momentarily, causing a catastrophic rolling update during peak traffic.
The fix: delegating authority.
We must tell Argo CD to ignore fields that are managed by in-cluster controllers. Senior warning: never define replicas in your Git manifests if you are using an HPA. If you must define it for the first time deployment, you must immediately configure Argo CD to ignore any future changes to that field. Failing to do this turns your autoscaler into a weapon against your own availability. Here is the YAML configuration for Argo CD to delegate replica authority to the HPA. Disclaimer: always test code in a non-production environment. By adding this JSON pointer, we tell Argo CD, if the replica count changes in the cluster, do not consider it drift. This allows the HPA to do its job without Argo CD interfering.
Prevention and guardrails: the post-mortem.
To prevent Git Ops infinity loops in the future, we implement these guardrails. 1. Removal of replicas. We update our Helm charts and customize bases to remove the replicas field entirely from deployment manifests when an HPA is present. 2. Admission controllers. We use Kyverno to ensure that any deployment created with an HPA must also have the Ignore Differences annotation in Argo CD. 3. Drift detection alerts. We set up alerts for argoct_app_sync_total rate spikes. If an application syncs more than 10 times in 5 minutes, it triggers a potential loop notification. A senior engineer knows that GitOps is the source of truth for structure, but the cluster is the source of truth for scale. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. Why does Argo CD default to overriding and cluster changes, even if they were made by a legitimate controller like HPA?
Answer: GitOps philosophy assumes that the state in Git is the absolute desired state. Argo CD has no native way of knowing if a change in the cluster was made by a human, which is drift, or a controller, which is dynamic state. Without explicit ignore rules, it treats all differences as unauthorized deviations that must be corrected.
Senior Follow-up 2 The Scale and Trade-off Trap. You removed replicas from Git. Now, when you deploy a brand new microservice, it starts with 1 replica by default, even if it needs 10 to handle the initial load. How do you handle this cold start problem?
Answer: we use the min replicas field in the HPA as the baseline. The deployment starts at 1, but the HPA controller immediately sees the min replicas is 10 and scales it up within seconds. The trade-off is a brief 30-second window of under-provisioning during the very first deployment.
Senior Follow-up 3 The Day 2 Migration Reality. You are using Istio, and it is injecting sidecars. Argo CD sees these new containers in the pods that are not in Git and tries to prune them. How do you fix this without disabling pruning?
Answer: similar to the replicas fix, we use ignore differences for the spec.containers array, or we use the sidecar.istio.io/inject annotation. Most modern GitOps tools have built-in support for Istio, but for custom injectors, you must explicitly ignore the metadata and container fields they modify.
Senior Follow-up 4 Curveball. You have ignore differences set for replicas. But the loop continues. You look at the diff, and it is now the image field flapping. You are using an image updater tool that pushes new tags directly to the cluster. How do you stop the fight?
Answer: the write back failure. If you use a tool that updates the cluster but does not write back to Git, you are violating the core principle of GitOps. You have 2 choices: either tell Argo CD to ignore the image field, not recommended for security, or configure your image updater to commit the new tag back to Git. This ensures that the desired state and live state are always in sync.
Pro tip: the controller sync window.
When using Argo CD alongside external controllers, always monitor the argoct_app_sync_total metric in Prometheus. A healthy app syncs once per commit. If you see a spike in sync events without a corresponding Git commit, you have a controller conflict. Use the sync window feature in Argo CD to block automated syncs during peak business hours, to prevent an infinity loop from crashing your API server during high traffic.
The Senior Dev Ops Incident 21 Terraform State Ghosting.
It is Thursday at 4 p.m. You are running a Terraform applied to update a critical production database. Halfway through the execution, the GitHub Actions runner crashes due to a host-level OOM error. The pipeline fails. You try to run the pipeline again, but it immediately errors out with error acquiring the state lock. You try to run it from your local machine, but you are blocked. The infrastructure is in an unknown half-finished state, and the lock is held by a runner that no longer exists.
Symptoms: the panic moment.
Here is the state of the paralyzed infrastructure automation. 1. Pipeline status: the last run shows internal runner error and a red exit code. 2. Terraform error acquiring the state lock. Lock info ID UUID operation type apply created timestamp. 3. Infrastructure state: some resources were created like the new DB instance, but others like the security group rules were not. 4. Backend state: the S3 state file is present, but the DynamoDB lock table entry is stuck in a held state. The automation engine has lost its mutex. It cannot move forward because it thinks another process is already working on the infrastructure.
Hypothesis, thinking like a senior.
A junior might try to delete the DynamoDB table. As a senior, I analyze the distributed lock state. Hypothesis 1, concurrent pipeline run, ruled out. No other pipelines are active in the GitHub Actions dashboard. Hypothesis 2, S3 backend outage, ruled out. We can successfully read the state file with Terraform state list. Hypothesis 3, orphan state lock. The previous process was killed violently before it could execute its defer function to release the DynamoDB lock. Decision tree signal. If Terraform apply was interrupted and subsequent runs fail with a state lock error, then always suspect an orphan lock from a crashed runner. Investigation. The 6-step debugging masterclass.
Step-by-step state forensic work.
We must safely break the lock and reconcile the ghost resources. We execute these steps. 1. Extract lock info. We read the error message to get the lock ID, UUID, and the created timestamp. 2. Verify the ghost. We search the GitHub Actions logs for the failed run to confirm that the process is definitely dead and not just hanging. 3. Audit the cloud. We manually check the cloud console to see which resources were partially created. We find a database v2 temp instance that is not in the current state file. 4. Break the lock. We execute the Terraform force unlock command using the UUID we extracted. 5. Refresh the state. We run Terraform plan to see the delta. Terraform thinks it needs to create the database, but the database already exists in the cloud. 6. Root cause identified, state reality mismatch. The crash happened after the resource was created in AWS, but before the state file was updated in S3. Terraform now has amnesia about the resources it just built. Let us look at the command that broke the deadlock. The proof breaking the state lock. This is a high-risk operation. It manually deletes the entry from the DynamoDB table. We only do this after verifying the previous runner is 100% dead. Because the state file was never updated before the crash, we must manually import the resource that was created. If we do not, the next apply will fail because the resource name already exists in AWS.
The fix, atomic state management.
We must ensure that our CI runners are resilient and that we have a recovery runbook for state corruption. Senior warning, never delete a lock without verifying the who and created fields. If you force unlock a running process, you will cause state corruption. 2 processes will write to the same S3 file simultaneously, and you will lose your entire infrastructure map. Rebuilding an entire cloud environment from a corrupted state file can take days. Here is the YAML configuration for GitHub Actions to harden the Terraform runner via execution timeouts and detailed logging. Disclaimer, always test code in a non-production environment. By wrapping the apply in a timeout, we ensure the runner does not hang forever. If it hits the limit, it fails cleanly, allowing us to investigate before the lock becomes ancient.
Prevention and guardrails, the post-mortem.
To protect our infrastructure state from future ghosts, we implement these guardrails. 1. State backups. We enable S3 versioning on our Terraform state bucket. If a crash causes a corrupted state file, we can roll back the state file to the version from 10 minutes ago. 2. Smaller state files. We break our monolithic production state into smaller, decoupled modules like network, RDS, and EKS. This limits the blast radius of a lock failure to only one component. 3. Runner resource limits. We ensure our CI runners have at least 8 GB of RAM and dedicated CPU to prevent host-level OOM crashes during heavy Terraform providers like Kubernetes or Helm. A senior engineer does not just manage the infrastructure. They manage the state of the management tool. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How does the Terraform DynamoDB lock physically work?
Answer: when you run Terraform apply, Terraform writes an item to a DynamoDB table with a primary key based on the state file path. It includes a digest of the operation and a UUID. Before any write to S3, Terraform checks if this item exists. If it does, it aborts. This provides mutual exclusion for distributed teams.
Senior follow-up 2, the scale and trade-off trap. You broke the state into 50 small modules to reduce risk. What is the operational trade-off?
Answer: dependency hell. If the database module needs the VPC_ID from the network module, You must use Terraform_remote_state or external data sources. This makes the total plan time much longer because you are fetching data across dozens of state files. You trade deployment speed for failure isolation.
Senior Follow-up 3, the Day 2 Migration Reality. You are moving from Terraform to Pulumi or CloudFormation. Do these tools suffer from the same lock issues?
Answer: yes. Every declarative tool must solve the multiple writer problem. Pulumi uses its service backend for locking. CloudFormation uses internal AWS stack locking. The mechanism changes, but the senior principle of protect the mutual exclusion remains the same.
Senior Follow-up 4 Curveball. You have broken the lock and imported the ghost resource. But when you run plan, Terraform still wants to destroy and recreate the resource. The SHA 256 matches, the ID matches. Why does it want to destroy?
Answer: the force new trap. You likely missed a small, non-importable attribute like an encrypted flag or a KMS_key_ID in your HCL code. Terraform sees the live resource is encrypted, but your code says it should be unencrypted. Because encryption cannot be changed on a live DB, Terraform's only choice is to destroy and recreate. You must update your HCL to match the live reality before applying.
Pro tip, the lock timeout flag.
To prevent local machine deadlocks and runner hangs, always run Terraform with the -lock timeout equals 20 seconds flag. By default, Terraform will fail instantly if the lock is held. Giving it a 20-second timeout allows for transient network blips or overlapping pipelines starts to resolve themselves without requiring a manual force unlock, and the high-risk forensic work that follows.
The Senior Dev Ops Incident 22, the circular dependency deadlock.
It is Monday morning. You are rebuilding the infrastructure for a disaster recovery test. You run your Terraform apply, and it hangs for 10 minutes, then fails with a dependency cycle error. You have a Route 53 DNS record that needs an ALB that needs an ACM certificate, and an ACM certificate that needs a Route 53 record for DNS validation. Your automation is stuck in a chicken and egg deadlock, where no resource can be created, because every resource is waiting for the other.
Symptoms, the panic moment.
Here is the behavior of the deadlocked infrastructure graph. 1. Terraform error cycle. Route 53 record validation to ACM certificate validation cert to LB listener HTTPS to Route 53 record alias. 2. Status. The infrastructure build is 0% complete. Not a single resource has been provisioned. 3. DR pressure. The business is watching the clock. The 4-hour RTO is ticking away while you fight a YAML dependency tree. 4. Manual attempt. You try to create the ALB manually, but the Cloud Console asks for the SSL certificate, which does not exist yet. The directed acyclic graph of your infrastructure has become a circle. The automation engine is mathematically paralyzed.
Hypothesis, thinking like a senior.
A junior might try to delete the entire project and start over. As a senior, I analyze the validation logic. Hypothesis 1, Terraform bug, ruled out. The graph logic is working correctly. It found a real logical loop. Hypothesis 2, circular HCL references, ruled out. The code looks clean, but the physical cloud requirements are circular. Hypothesis 3, DNS validation deadlock. The SSL certificate cannot be issued until the DNS record exists, but the DNS record cannot exist until the load balancer has a DNS name, and the load balancer cannot exist without the SSL certificate. Decision tree signal. If an infrastructure build fails with a cycle error involving DNS, load balancers and certificates then always suspect a DNS validation to ALB deadlock. Investigation, the 6-step debugging masterclass.
Step-by-step graph debugging.
We must break the circle into a linear path. We execute these steps. 1. Visualize the cycle. We use Terraform graph command to see the physical loop in the resources. 2. Isolate the certification. We find the ACM certificate resource. It is using DNS validation. 3. Analyze the ALB. We find the LB listener for port 443. It is hard-coded to require the certificate ARN. 4. Analyze the DNS, we find the AUS_Route53_ record. It is an alias record pointing to the DNS_ name of the ALB. 5. Identify the weak link, we realize the alias record is what closes the loop. It needs the ALB, which needs the CERT, which needs a DNS record. 6. Root cause identified, improper DNS record type selection. By using an alias record for a certificate that needs DNS validation, we force the ALB into the middle of the validation chain. Let us look at the HCL code that created the circular deadlock. The proof, the circular HCL. This is the problem. You are trying to create the final application DNS record in the same step as the validation record. Terraform sees that API.company.com is involved in both, creating a logical loop.
The fix, decoupling the validation.
We must separate the certificate validation DNS from the application DNS alias. Senior warning, do not fix this by manually creating the certificate in the console. That is a tainted fix that will break your next Terraform run. You must fix the dependency graph in the code so the DR test is repeatable without human intervention. Here is the HCL implementation to decouple DNS validation from load balancer creation and break circular dependencies. Disclaimer, always test code in a non-production environment. By using the specific validation CNAME provided by ACM, we break the dependency on the ALB. The certificate can now be issued and validated before the load balancer even exists.
Prevention and guardrails, the post-mortem.
To ensure we never hit a circular deadlock during a real disaster, we implement these guardrails. 1. Multi-stage apply. We update our disaster recovery script to run Terraform apply target certificate first. Once the identity layer is stable, we run a full apply for the traffic layer. 2. Module separation. We move certificates and DNS zones into a global foundation repository and load balancers into an app infrastructure repository. This physically prevents the code from being in the same graph. 3. Pre-provisioned certs. For critical DR domains, we maintain pre-validated certificates in the standby region so the chicken and egg problem never occurs during the actual failover window. A senior engineer does not fight the graph. They flatten the graph. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does Terraform use a directed acyclic graph for its internal engine?
Answer, Terraform must understand the exact order of operations to build infrastructure. A DAG allows it to identify which resources can be built in parallel and which must be built sequentially. The acyclic part is the most important. If a cycle exists, there is no mathematical starting point, and the engine must abort.
Senior follow-up 2, the scale and trade-off trap. You decided to use Target as a fix. What is the risk of using Target in a large, shared production environment?
Answer, state inconsistency. When you use Target, Terraform ignores the rest of the graph. If someone else changed a security group or a variable, those changes are not applied and not verified. This can lead to partial state where your certificate is updated, but your network is now 10 versions behind. It should only be used for emergency cycle breaking.
Senior follow-up 3, the day 2 migration reality. You are migrating from DNS validation to email validation for a CM to avoid this loop. What is the operational trade-off?
Answer, human latency. Email validation requires a human to log into an email account and click a link. This makes your infrastructure automation non-deterministic and impossible to run in a fully automated CI/CD pipeline. You trade a chicken and egg HCL problem for a human in the loop bottleneck.
Senior follow-up 4, curveball. You have broken the loop. The ALB and CERT are created, but the DNS alias record still fails with no such hosted zone. You check the console, and the hosted zone exists. Why is your IAC failing to see it?
Answer, the namespace propagation delay. If your Terraform code creates a new Route 53 hosted zone and a record inside it in the same run, the DNS record creation might hit the AWS API before the hosted zone name servers have propagated across the global AWS fleet. You must implement an explicit depends_on or a retry logic to account for eventual consistency.
Pro tip, the dummy listener maneuver.
If you are trapped in an ALB to CERT deadlock and need a fast fix, create the ALB with an HTTP-only listener first. This allows the ALB to get a DNS name and pass its health checks. Once the ALB is alive, use that DNS name to validate your ACM certificate. Finally, use Terraform to upgrade the listener from HTTP to HTTPS. This incremental evolution strategy allows you to build complex stacks without ever hitting a circular dependency.
Category 6 wrap-up. The double-edged sword of automation.
Category 6 has demonstrated that infrastructure automation is a double-edged sword. We have seen that without strict network boundaries, a simple shell script inside a Helm hook can become a cross-environment weapon. We have learned that GitOps requires a single, undisputed source of authority to avoid catastrophic logic loops, and that state files are the most fragile part of your management stack. A senior engineer treats infrastructure code with more caution than application code, because the blast radius of an IAC failure is systemic and often manual to recover. The goal is not just to automate, but to automate with guardrails that protect the state of the universe.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
With the foundation of the cluster and the automation engine secured, we must now address the logic of change itself. We are moving from the tools that manage servers to the strategies that manage how software evolves without breaking its distributed dependencies.
Category 7. Release engineering and contract safety.
Focus, safely changing how the application behaves. In this section, we look at the failures that occur when the code is technically functional but architecturally incompatible. We will explore the silent breakage of API contracts that take down downstream services, the point of no return database migrations that paralyze your ability to roll back, and the hidden traps where 2 independent feature flags create a logical deadlock. In a microservice architecture, every release is a negotiation between services, and a failure to respect the contract is an invitation for a system-wide outage.
The release and contract incidents.
We will be performing reference-grade deep dives into these 3 critical release failures. 23. Backward incompatibility, how poor API contract design and versioning flaws break downstream microservices. 24. Schema migration failure, solving the nightmare of non-atomic database changes with no safe rollback path. 25. Feature flag coupling, identifying and fixing hidden logic dependencies between multiple feature flags. Let us start with the silent killer of microservices, the broken API contract.
The Senior DevOps Incident 23. The silent contract break.
It is Wednesday morning. You deploy a minor update to the user profile service. The metrics are green and the service is healthy. However, an hour later, the mobile engineering lead reports that 100% of Android users are crashing on login. You did not change the authentication logic, and you did not change the mobile app code. You changed a single field name in a JSON response, assuming it was deprecated. You have just broken a distributed API contract, and there is no way to patch the millions of devices already in the wild.
Symptoms, the panic moment.
Here is the data that revealed the architectural mismatch. 1. Service metrics. The user profile service shows 200 OK for all requests with normal latency. 2. Client metrics. Mobile crash reporting tools like Firebase show a spike in null pointer exception errors. 3. Log analysis. Ingress logs show successful requests, but the response body length is decreased by 40 bytes. 4. Blast radius. Only specific legacy versions of the mobile app are crashing, while the web frontend remains stable. The server is succeeding in sending the wrong data, and the client is failing because it was told to expect the old data.
Hypothesis, thinking like a senior.
A junior might blame the mobile team for bad error handling. As a senior, I analyze the API evolution strategy. Hypothesis 1, mobile app bug. Ruled out. The mobile code has not changed in 3 weeks. Hypothesis 2, edge cache invalidation. Ruled out. Bypassing the CDN still results in client crashes. Hypothesis 3, backward incompatibility. The API response removed or renamed a field that legacy clients consider mandatory, causing a deserialization failure. Decision tree signal. If the server is green but specific client versions are crashing with deserialization errors, then always suspect a broken API contract. Investigation, the 6-step debugging masterclass.
Step-by-step contract forensic work.
We must identify the exact delta in the communication layer. We execute these steps. 1. Capture live traffic. We use a tool like KSniff to capture the raw TCP traffic entering the user profile pod. 2. Compare payloads. We compare the JSON response of the new version against a captured trace from the previous version. 3. Identify the missing field. We find that user_ID was changed to ID to follow a new company-wide naming standard. 4. Reverse engineer the client. We check the legacy mobile source code and find the JSON parser is set to strict mode. 5. Trace documentation. We check the internal API documentation and realize the user_ID field was never marked as deprecated. 6. Root cause identified, breaking change in a minor release. The developer assumed that because the web frontend used the new field, all clients were updated. They failed to account for legacy mobile binaries that cannot be force updated. Let us look at the JSON mismatch that crashed the mobile fleet. The proof, the contract violation. The developer renamed the field to be more consistent with modern standards. In a monolith, this is a simple refactor. In a distributed system, this is a grenade thrown at every legacy client.
The fix, implementation of the expand and contract pattern.
We must immediately restore the old field while keeping the new field to support all client generations. Senior warning, never rename a field in a public-facing API. You must follow a multi-month deprecation cycle where you support both fields simultaneously. If you must change a schema, you add the new field first, wait for client migration metrics to hit 100%, and only then remove the old field. Here is the JavaScript implementation for a backward-compatible API response, supporting legacy and modern clients. Disclaimer, always test code in a non-production environment. By duplicating the data into both field names, we satisfy the legacy parser while allowing modern clients to use the new naming convention. This restores availability instantly, without requiring a client-side update.
Prevention and guardrails, the post-mortem.
To prevent silent contract breaks in the future, we implement these guardrails. 1. Consumer-driven contract testing. We implement packed tests. The mobile team provides a contract file to the backend team. If the backend change breaks the mobile team's requirements, the CI build fails before deployment. 2. API versioning. We enforce strict URI versioning, for example, /v1/user and /v2/user. Any breaking change requires a new endpoint, leaving the old one untouched. 3. Post-deployment shadowing. We use Diffie to compare responses from the old and new service versions during the canary phase, alerting on any missing JSON keys. A senior engineer knows that the API is a legal contract with the user that cannot be unilaterally changed. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. Why is it safer to add fields rather than rename or delete them in a JSON-based microservice architecture?
Answer: most modern JSON parsers use a permissive model where they ignore unknown fields but crash on missing mandatory fields. By adding a field, you are providing extra information that legacy clients will safely ignore, while providing the necessary information that modern clients require.
Senior Follow-up 2 The Scale and Trade-off Trap. You decided to support both user_ID and ID forever to be safe. What is the trade-off regarding network bandwidth at high scale?
Answer: payload bloat. If your API serves 1 billion requests a day and you add 20 bytes of redundant data to every response, you are transferring an extra 20 gigabytes of data daily. Over a year, this increases egress costs and slightly increases latency for users on slow mobile networks.
Senior Follow-up 3 The Day 2 Migration Reality. You have 5 versions of the mobile app in the wild. How do you track which versions are still using the legacy user_ID field so you know when it is safe to delete it?
Answer: header-based telemetry. We mandate that every client sends an X-client version header. We log this header in our observability stack. We create a dashboard showing the percentage of traffic coming from legacy versions. We only contract the API and delete the old field once legacy traffic drops below 0.1%.
Senior Follow-up 4 Curveball. You used URI versioning /v1 and /v2. You deployed /v2, but suddenly the /v1 endpoint starts failing too, even though you did not touch its code. Why?
Answer: shared internal state. Even if the API endpoints are versioned, they likely share the same underlying database or cache. If the /v2 code performed a destructive database schema migration, it killed the /v1 endpoint's ability to read the data. A senior engineer knows that versioning the code is useless if you do not also version the data access layer.
Pro tip: the permissive parser rule.
Always build your clients to be robust and your servers to be conservative. In your mobile and front-end code, never use strict JSON mapping that throws an error on missing fields. Use optional types or safe navigation operators. This architectural resilience ensures that if a backend engineer makes a mistake and removes a field, your app shows a blank space instead of a crash.
The Senior Dev Ops Incident 24 The Non-Atomic Schema Nightmare.
It is Thursday night. You are running a database migration to add a country_code column to a table with 100 million rows and set a default value of US. The migration script is a single SQL file. 10 minutes into the process, the database connection times out and the migration fails. You try to roll back, but the database is now in a zombie state. The column exists, but only 40% of the rows have the data. Your application is now crashing because it expects the data to be fully present or fully absent. You are trapped in a non-atomic failure.
Symptoms: the panic moment.
Here is the state of the corrupted data layer. 1. App logs massive volume of unexpected null errors from the backend service. 2. DB performance CPU is at 95% and I/O weight is skyrocketing because of massive row locking. 3. Migration state: the migration tool, Flyway or Liquibase, reports the version as failed but the schema has been partially modified. 4. Rollback failure. Running the down script fails because the database cannot drop a column while other transactions are still trying to update it. The database has lost its integrity. The migration was too large to succeed and too messy to fail.
Hypothesis: thinking like a senior.
A junior might try to run a manual update statement to fix the missing rows. As a senior, I analyze the transactional integrity. Hypothesis 1: insufficient disk space. Ruled out. The DB volume has 500 gigabytes of free space. Hypothesis 2: network blip. Ruled out. The application and DB are in the same AZ with stable connectivity. Hypothesis 3: non-atomic DDL. The migration script mixed schema changes, DDL, with data updates, DML, in a single massive transaction that exceeded the database's undo logs or lock timeout limits. Decision tree signal. If a migration fails halfway and leaves the schema inconsistent, Then always suspect a non-atomic mixture of DDL and large-scale DML. Investigation, the 6-step debugging masterclass.
Step-by-step data forensic work.
We must determine the extent of the inconsistency. We execute these steps. 1. Check migration logs. We see the error lock wait timeout exceeded during the update phase of the script. 2. Audit the schema. We run describe users and find the country_code column was added successfully before the crash. 3. Verify transactional DDL. We check the DB engine, MySQL. We realize MySQL does not support transactional DDL. The alter table committed immediately, but the update failed later. 4. Measure row progress. We count the rows where country_code is US versus null. We find 42 million updated, 58 million pending. 5. Identify lock contention. We find that the massive update held a metadata lock on the table, blocking all application writes for 10 minutes, triggering the timeout. 6. Root cause identified, monolithic migration. The script attempted to change the schema and backfill 100 million rows in one go. Because the DDL was non-transactional, the failure left the database in a state that matched neither version 1.0 nor version 2.0 of the code. Let us look at the SQL script that paralyzed the database. The proof, the monolithic migration. This is the fatal mistake. Updating 100 million rows in a single statement creates a massive transaction that locks the entire table. It is guaranteed to fail in a high-traffic production environment.
The fix, decoupled and batched migrations.
We must separate the schema change from the data migration and process the data in small, non-blocking chunks. Senior warning: never backfill data using a standard SQL migration tool for tables over 1 million rows. Migration tools are designed for schema, not for heavy data processing. Use a background worker or a specialized batch script to backfill data while the application is running. Here is the SQL and Bash implementation for batched, non-blocking data backfills. Disclaimer: always test code in a non-production environment. By defining the default value in the alter statement, the database engine handles the backfill internally. In modern versions of Postgres and MySQL 8.0+, which is often near instant and atomic. If a custom calculation is needed, we update in batches of 5,000. This ensures that each transaction is short-lived, releasing locks quickly so the application traffic can pass through.
Prevention and guardrails, the post-mortem.
Prevent data corruption during releases. We implement these guardrails. 1. Zero downtime migration policy. We forbid any migration that requires a table lock longer than 1 second. Large tables must use online schema change tools. 2. Idempotent migrations. We ensure all migration scripts are rerunnable. They must check for the existence of a column before trying to add it, allowing us to recover from a partial failure by simply clicking retry. 3. Separate DDL and DML. We enforce a rule in CI that migration files can only contain schema changes. Data backfills must be handled by application-level background jobs. A senior engineer treats the database as a live organism that cannot be stopped for surgery. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is transactional DDL, and why is it a holy grail for DevOps engineers?
Answer: transactional DDL, supported by Postgres, allows you to wrap alter table statements inside a begin/commit block. If the migration fails halfway through, the entire schema change is rolled back automatically by the database. In non-transactional engines like MySQL, a failed migration leaves the schema in a half-finished, corrupted state.
Senior follow-up 2, the scale and trade-off trap. You use the default value trick to add a column to 100 million rows instantly. What is the storage trade-off?
Answer: write amplification. While the schema change is instant, the database must eventually write that default value to the physical disk for every row. This can cause a background I/O spike for hours after the migration finishes, potentially slowing down other write-heavy operations.
Senior follow-up 3, the day 2 migration reality. Your migration failed, and the table is locked by a ghost process. You cannot restart the database. How do you kill the specific transaction to unlock the table?
Answer: we query the process list. In MySQL, we run show full process list to find the query status. We identify the thread ID of the migration and run the kill ID command. This forcefully rolls back the partial transaction and releases the metadata locks instantly.
Senior follow-up for Curveball. You are using an online schema change tool, GHOST. It is 99% finished. Suddenly, your master database fails over to a replica. What happens to your 10-hour migration?
Answer: constraint scenario. Most online schema change tools rely on binary log replication. If a failover occurs, the migration is aborted. Because the tool was working on a ghost table, your production table is safe, but you have lost 10 hours of work. You must design your migrations to be resumable or accept that at scale, high availability events can reset your maintenance windows.
Pro tip: the pre-flight row count.
Before running any migration, run a select the count function on the target table. If the row count is over 500,000, the migration should automatically be flagged for a senior review. Never let an automated tool run a monolithic update against a high cardinality table without an explicit architectural sign-off.
The Senior Dev Ops Incident 25. The feature flag coupling deadlock.
It is Friday afternoon. You are rolling out two independent features, a new premium checkout UI and a new fast track payment gateway. Each is controlled by its own feature flag, UI_flag and gateway_flag. You toggle the UI_flag to on for 10% of users. Suddenly, every one of those users gets a critical error when they try to pay. You toggle the UI_flag back to OFF, but the errors continue. You have just triggered a logical deadlock, where two independent flags have coupled in a way you never tested.
Symptoms: the panic moment.
Here is the behavior of the coupled logic failure. 1. Error pattern: 100% failure rate for a specific segment of users. 2. Toggling behavior: disabling UI_flag, the one you just changed, did not stop the errors. 3. Application logs type error: cannot read property gateway_config of null. 4. State mismatch: users are seeing the old UI, but the backend is trying to process them using the new gateway logic. The flags are independent in your dashboard, but they are hard-coded dependencies in your source code.
Hypothesis: thinking like a senior.
A junior might assume the payment gateway is down. As a senior, I analyze the logic combinations. Hypothesis 1: gateway provider outage. Ruled out. 90% of users, those on the old UI, are paying successfully. Hypothesis 2: cache poisoning. Ruled out. Clearing the user sessions does not fix the error. Hypothesis 3: coupled flag state. The new UI code assumes that if it is active, the new gateway must also be active. But the gateway flag is currently OFF, creating a logic void where the code asks for a configuration that does not exist. Decision tree signal: if toggling a flag causes a crash that persists after rollback, then always suspect a hidden coupling between multiple flag states. Investigation: the 6-step debugging masterclass.
Step-by-step logic forensic work.
We must find the intersection of the two code paths. We execute these steps. 1. Audit flag states. We check the feature flag provider, launch darkly or unleash. UI_flag is OFF. Gateway_flag is off. 2. Trace user sticky state. We realize the UI_flag has client-side caching enabled. Even though we turned it OFF on the server, the 10% of users still have UI_flag on in their browser's local storage. 3. Analyze the backend code. We find a line: if UI_flag, use gateway_v2_config. 4. Identify the dependency. The code assumes that if the UI is new, it must use the new gateway. It does not check if gateway_flag is actually enabled. 5. Simulate the combination. We test the state UI on plus gateway off. The app crashes instantly because gateway_v2_config is null. 6. Root cause identified: combinatorial explosion. The team tested UI on plus gateway on and UI off plus gateway off. They never tested the mixed state. The client-side cache made the failure sticky, preventing a clean rollback. Let us look at the code logic that created the coupling trap. The proof: the combinatorial bug. The developer coupled the UI experience to the data path. Because these two flags can be toggled independently, the system enters an invalid state where the new UI is asking for data that the backend is not yet allowed to provide.
The fix, implementation of dependency-aware feature flags.
You must refactor the code to handle all combinations of flags safely and disable client-side caching for critical path toggles. Senior warning, feature flags are distributed if statements. Every flag you add doubles the number of possible system states. If you have 10 flags, you have 1024 possible combinations. You must use defensive coding to ensure that if a flag dependency is missing, the system gracefully falls back to a safe legacy state. Here is the JavaScript implementation for defensive feature flagging with safe fallbacks. Disclaimer: always test code in a non-production environment. This logical and ensures that the new UI never attempts to use the new gateway unless both features are explicitly authorized. This eliminates the deadlock state.
Prevention and guardrails, the post-mortem.
To prevent feature flag chaos in the future, we implement these guardrails. 1. Flag prerequisites. We use our feature flag provider's prerequisite feature. We configure UI_flag so it physically cannot be turned on unless gateway_flag is already at 100%. 2. Short TTL for client cache. We reduce the local storage TTL for feature flags from 24 hours to 5 minutes, ensuring that a kill switch toggle is respected by clients almost instantly. 3. Automated flag cleanup. We add a stale flag alert in CI. If a flag has been at 100% for more than 30 days, the build fails, forcing the developer to remove the if statement and clean up the code. A senior engineer knows that every feature flag is technical debt waiting to happen. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between a release toggle and a business toggle in feature flagging?
Answer: release toggles ops are short-lived and used to hide unfinished code or perform canaries. They should be removed within days. Business toggles product are long-lived and used for things like premium versus free features. Seniors ensure these are handled in different parts of the architecture to prevent feature flag spaghetti.
Senior follow-up 2, the scale and trade-off trap. You move to no client-side cache for flags. What is the performance trade-off for your mobile users?
Answer: increased latency and API load. Every time the app boots, it must block the UI while it waits for a network call to fetch the flag states. On slow 3G networks, this can add 2 seconds to the app start time. You trade correctness for speed.
Senior follow-up 3, the day 2 migration reality. You are using flags for a database migration, dual writing. How do you ensure the consistency of the toggle across 500 different microservice instances simultaneously?
Answer: we use a streaming flag provider that uses server-sent events, SSE. Instead of the pods polling for changes, the flag server pushes the update to all 500 pods in sub-second time. This ensures that the entire fleet switches from the old DB to the new DB at the exact same moment, minimizing data drift.
Senior follow-up 4 curveball, you have perfect prerequisites. You toggle the flag. The backend is fine. The front end is fine. But your data analytics pipeline breaks because it is now receiving 2 different schema versions for the same event, and the data warehouse cannot merge them. How do you flag the data layer?
Answer: the downstream poison effect. A senior engineer knows that feature flags must propagate to the analytics layer. You must include the flag state as metadata in your event streams, Kafka, or segment. The data warehouse must be designed to schema on read or use a landing table that accepts both versions until the flag is fully rolled out and the schema is unified.
Pro tip, the flag audit log.
Never allow a developer to toggle a flag in production without a Jira ticket reference in the audit log. Feature flags are deployments. If you change a flag at 3 p.m., it should appear on your Grafana dashboard as a deployment event. This ensures that when the system crashes 5 minutes later, the first thing the on-call engineer sees is the exact flag that caused the logic coupling.
Category 7 wrap up, the integrity of change.
Category 7 has illuminated the high-stakes reality of distributed logic. We have seen that a release is not just about the code you ship, but about the contracts you maintain. A senior engineer recognizes that an API is a legal agreement with every client in the wild, and that breaking that contract is a systemic failure of leadership, not just a bug. We have learned that database migrations are the most dangerous operations in DevOps, requiring atomicity and the expand contract pattern to ensure reversibility. Finally, We saw that feature flags are powerful but introduce combinatorial complexity that can paralyze a system if dependencies are not explicitly managed. Mastering release engineering means ensuring that every change is backward compatible, state-aware, and logically isolated.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Now that we have covered how to build, automate, and release our systems, we must address the final frontier of the senior DevOps role. No matter how perfect your architecture is, the real world will eventually break it. We are moving from the engineering of creation to the engineering of observation and recovery.
Category 8. Observability and Incident Management.
Focus, the culture and tools used to detect and fix failures. In this final section of Part 1, we look at the eyes and ears of the platform. We will explore the observability gap where metrics are healthy but users are failing, the psychological toll of alert storms, and the technical debt of untested disaster recovery plans. We will also dive into the human elements of MTTR, knowledge silos, and the critical importance of blameless postmortems. This is where we transition from being operators to being detectives, ensuring that every incident is not just resolved, but used as fuel to build a more resilient system.
The Observability and Incident Management Scenarios.
We will conclude Part 1 with reference-grade deep dives into these 9 critical operational challenges. 26. Metrics healthy but users failing, solving the observability gap when your dashboards lie. 27. Alert storm, managing pager fatigue through grouping and intelligent threshold design. 28. Missing golden signals, identifying and monitoring the critical blind spots in your system. 29. Log sampling bias, understanding when and how log reduction hides the root cause. 30. The theory-only disaster recovery plan, why untested backups are a liability, not a safety net. 31. Slow mean time to recovery, improving debugging workflows and the quality of runbooks. 32. Wrong root cause analysis, overcoming bias to prevent recurring incidents. 33. Knowledge silos, breaking the bus factor and tribal knowledge traps during an outage. 34. No preventive action, solving the failure of the post-mortem process to drive real change. Let us start with the most deceptive failure in DevOps, the dashboard that stays green while the system is burning.
The Senior DevOps Incident 26. Metrics healthy but users failing.
It is Monday morning. You check the global monitoring dashboard and everything is a perfect, vibrant green. CPU usage is low, memory is stable, and the HTTP 500 level error rate is 0%. You are about to grab a coffee when the head of customer success bursts in. The support tickets are skyrocketing. Thousands of users report that the search page is completely blank. Your dashboards are telling you the system is healthy, but the users are telling you the business is dead. You have fallen into the observability gap.
Symptoms, the panic moment.
Here is what the traditional observability stack was showing during the semantic outage. 1. Infrastructure metrics, Kubernetes pod health and node resources are well within safe thresholds. 2. Load balancer logs, 100% of requests are returning a 200 OK status code. 3. Application logs, the logs show successful processing of search queries with sub-second latency. 4. User reports. Social media and support channels are flooded with screenshots of an empty white page. The system is successfully delivering a failure. Your metrics are monitoring the transport, but not the payload.
Hypothesis, thinking like a senior.
A junior engineer might suspect a CSS or front-end deployment bug. As a senior, I analyze the semantic integrity of the response. Hypothesis 1, CDN caching issue, ruled out. Bypassing the CDN and hitting the origin still results in a blank page. Hypothesis 2, front-end asset corruption, ruled out. The JavaScript bundles are loading correctly and have the correct hashes. Hypothesis 3, semantic logic failure. The backend is returning a 200 OK status, but the actual JSON body is empty or contains a logical error message that the frontend cannot handle. Decision tree signal. If app CPU is normal, DB is normal, and logs show success, but users report failure, then always suspect a semantic error wrapped in a 200 OK status. Investigation. The 6-step debugging masterclass.
Step-by-step semantic debugging.
We must look inside the payload that the metrics are ignoring. We execute these steps. 1. Manual request. We use a curl command to hit the search API directly and inspect the raw output. 2. Inspect response body. We find the response is an empty JSON array even for keywords that should have millions of results. 3. Analyze query logic. We check the search microservice logs again, looking specifically for database result counts. We find the result count is 0. 4. Trace database interaction. We enable debug logging for the database driver and find the SQL query has a malformed where clause. 5. Check recent changes. We find a feature flag was enabled that optimized the search algorithm but introduced a logical null pointer. 6. Root cause identified, semantic mismatch. The application was designed to return a 200 OK even if the search returned 0 results. Because the monitoring only tracked the HTTP status code and not the result count, the system appeared perfectly healthy while being functionally useless. Let us look at the code and logs that proved our dashboards were lying. The proof, the semantic lie. The load balancer sees a 200 OK and a content length of 2 bytes. It marks this as a success. This is why the dashboard stayed green. The empty array is the semantic failure. To the infrastructure, this is valid JSON. To the business, this is a total outage.
The fix, implementing semantic monitoring.
We must move beyond tracking success rates and start tracking business logic value. Senior warning, do not start returning 500 errors for 0 results just to fix your metrics. That breaks the API contract. Instead, you must export custom metrics that represent the internal state of the application logic. Here is the Python implementation for exporting semantic business metrics to Prometheus. Disclaimer, always test code in a non-production environment. By incrementing a custom counter when the business logic returns an empty state, we create a metric that can be alerted on. We can now detect if the 0 result rate spikes, regardless of the HTTP status code.
Prevention and guardrails, the post-mortem.
To ensure we are never blinded by green dashboards again, we implement these guardrails. 1. Synthetic user journeys. We implement Datadog synthetics that do not just check for a 200 OK, but also assert that specific text or elements exist on the final page. 2. Golden signal expansion. We add saturation and error metrics at the business layer, such as average items per cart or search click-through rate. 3. Structured logging. We mandate that every API response includes a result count header, which our ingress controller can parse and export as a standard metric. A senior engineer knows that monitoring the plumbing is not the same as monitoring the water quality. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why do modern monitoring systems fail to detect silent errors by default?
Answer: monitoring systems typically operate at the application and transport layers of the OSI model. They verify that the server is alive and the protocol is followed. They have no context of the domain layer. Without specific instrumentation of the business logic, the monitoring system has no way of knowing if a response is correct or just syntactically valid garbage.
Senior follow-up 2, the scale and trade-off trap. You decided to instrument every microservice with thousands of custom business metrics. What is the trade-off regarding your observability bill?
Answer: cardinality explosion. Every unique combination of metric name and label increases the memory usage of your metrics database. At scale, high cardinality data can cost more than the actual compute resources of the application. You must be strategic and only instrument the most critical business pivot points.
Senior follow-up 3, the day 2 migration reality. You are moving to a distributed tracing model, open telemetry. How does tracing help solve the observability gap?
Answer: tracing allows you to see the attributes of a request as it passes through the system. We can attach the query result count as a span attribute. This allows us to search for traces where the HTTP status was 200, but the result count was 0, providing a direct link between the healthy infrastructure and the broken logic.
Senior follow-up 4, curveball. Your synthetic tests are passing. Your custom metrics are green, yet users are still seeing blank pages in Australia only. Why?
Answer: the regional edge failure. A senior engineer looks at the last mile. Your synthetic tests might be running from US East 1. If the Australian CDN node has a corrupted cache or a localized routing issue, your global metrics will stay green while a whole continent is offline. You must deploy global probes that test from every region where you have users.
Pro tip, the zero value alert.
In Prometheus, use the absent or sum is equal to 0 function for critical metrics. For a high-traffic site, receiving exactly 0 orders or 0 searches in a 5-minute window is a mathematical impossibility. Alerting on the absence of value is often more effective at catching catastrophic logic failures than alerting on the presence of errors.
The Senior Dev Ops Incident 27, the alert storm and pager fatigue.
It is 3 a.m. Your phone begins to vibrate uncontrollably. It is not one alert, it is a relentless flood. Within 5 minutes, you have received 450 unique PagerDuty notifications. The database is down, but you are also getting alerts for every microservice, every internal API, and every front-end health check. You cannot find the root cause because the signals are being drowned out by the noise. Your monitoring system has become a distributed denial of service attack against your own engineering team.
Symptoms, the panic moment.
Here is the operational paralysis during the alert storm. 1. Information overload. The Slack alerts channel is moving so fast it is impossible to read. 2. MTTA spike. The mean time to acknowledge is skyrocketing because engineers are ignoring their phones in frustration. 3. Context loss. The alerts are fragmented. You have 50 alerts for high latency and 50 for connection refused, but no single alert for database master node down. 4. Redundancy. You are receiving the same alert for 10 different replicas of the same service. The monitoring system is working too well. It is reporting every single symptom of a single failure.
Hypothesis, thinking like a senior.
A junior engineer might try to silence all alerts. As a senior, I analyze the alert topology. Hypothesis 1, multiple independent failures, ruled out. The probability of 40 services failing simultaneously is near 0. Hypothesis 2, alert manager bug, ruled out. The alerts are valid, the services are actually failing. Hypothesis 3, missing alert dependencies. The monitoring system lacks inhibition and grouping logic. A failure in a downstream dependency, the database, is triggering an alert for every upstream consumer. Decision tree signal. If a single outage triggers hundreds of alerts across multiple layers of the stack, then always suspect a lack of alert grouping and dependency mapping. Investigation, the 6-step debugging masterclass.
Step-by-step alert forensic work.
We must trace the alert flood back to its source. We execute these steps. 1. Sort by timestamp. We look at the very first alert that fired. It was RDS CPU utilization 100% at 2:59 a.m. 2. Map upstream failures, we see the order service alerts started 10 seconds later, followed by the front-end alerts 20 seconds after that. 3. Inspect alert rules. We check the Prometheus Alert Manager configuration. We find that every rule is independent with no shared labels. 4. Verify grouping logic. We realize that grouping is set to alert name, meaning 10 pods failing the same test result in 10 separate notifications. 5. Audit pager duty escalation. We find that we are paging the general on call for every single service instead of specific team routes. 6. Root cause identified. Flat alerting hierarchy. The system treats a symptom, front-end latency, with the same severity and urgency as the cause, database failure. Because there is no inhibition rule, the secondary failures caused by the database outage created an unstoppable storm of noise. Let us look at the Alert Manager configuration that failed us. The proof: fragmented alert logic. By grouping only by the alert name, the system generates a new notification for every single pod or service that experiences the symptom. At scale, this is catastrophic.
The fix: implementing alert inhibition and grouping.
We must configure the monitoring system to mute symptoms when a known root cause is already active. Senior warning: do not just increase your alert thresholds to reduce noise. This creates silent failures. You must maintain sensitive thresholds but use intelligent grouping and inhibition to manage how those alerts are delivered to humans. Here is the YAML configuration for Prometheus Alert Manager to implement grouping and inhibition. Disclaimer: always test code in a non-production environment. By grouping by service and cluster, if 100 pods in the order service fail, you get exactly one notification saying order service is failing. This preserves your sanity. This is the senior level fix. If the database alert fires, Alert Manager will automatically suppress all critical alerts from any application API that depends on it. You get one alert for the cause and 0 alerts for the symptoms.
Prevention and guardrails, the post-mortem.
Prevent alert storms forever. We implement these systemic guardrails. 1. Alert to noise ratio audit. We perform a weekly review of all alerts. Any alert that is acknowledged but not resolved within 1 hour is either tuned, automated, or deleted. 2. Tiered severity. We enforce 3 levels: page for immediate action, ticket for next day action, and log for historical analysis. Only page triggers pager duty. 3. Symptom-based alerting. We move away from alerting on CPU or disk. We only page on symptoms that affect users: latency, errors, availability. We use internal metrics only for the investigation phase. A senior engineer knows that an alert you ignore is more dangerous than an alert you do not have. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between group_wait and group_interval in Alert Manager?
Answer: group_wait is the initial delay before sending the first notification, allowing multiple related alerts to be collected into one message. Group_interval is the minimum time to wait before sending a notification about new alerts added to an existing group. Correctly tuning these prevents rapid-fire notifications during a cascading failure.
Senior follow-up 2, the scale and trade-off trap. You implemented strict inhibition rules. What is the risk during a multiple root cause event?
Answer: signal suppression. If your database is down, triggering an inhibition, but simultaneously your DNS provider fails, the DNS alert might be suppressed if the rules are too broad. You must ensure inhibition rules are highly specific to the dependency chain to avoid masking unrelated critical failures.
Senior follow-up 3, the Day 2 migration reality. You are moving to an on-call rotation across 50 teams. How do you prevent alert leakage where Team A gets paged for Team B's bugs?
Answer: label-based routing. We mandate that every Kubernetes namespace and every Prometheus rule has a team label. Alert Manager is configured with a routing tree that matches the team label to the specific PagerDuty service for that team. This ensures accountability and prevents burnout across the organization.
Senior follow-up 4 curveball. Your alerts are perfectly grouped. But during an outage, you get one alert, resolve it, and 5 minutes later it fires again. This repeats 20 times. It is a flapping alert. How do you fix a signal that is hovering exactly on the threshold?
Answer: hysteresis or the for duration. A senior engineer never alerts on a single data point crossing a line. We use the for property in Prometheus, for example, for 5M. The condition must be true for 5 continuous minutes before it fires. This smooths out transient spikes and prevents flapping notifications from destroying your focus.
Pro tip: the silence of the maintenance window.
Integrate your CI/CD pipeline with your Alert Manager API. Whenever a deployment starts, the pipeline should automatically create a 10-minute silence for that specific service. This prevents false positive alerts caused by pod restarts or cache warming during a routine rollout, ensuring that when the on-call engineer's phone rings, it is always for a real emergency.
The Senior Dev Ops Incident 28, missing golden signals.
It is a high-traffic marketing event. Your dashboard shows CPU at 40% and memory at 60%. The error rate is a flat 0. By all traditional metrics, the cluster is coasting. However, the customer experience team reports that the checkout page is taking 30 seconds to load for every single user. You are blind. You are monitoring utilization, but you have completely missed the saturation of your underlying resources. Your golden signals have a massive hole.
Symptoms: the panic moment.
Here is the data that revealed the critical monitoring blind spot. 1. Infrastructure metrics, standard CPU and memory utilization are well within safe operating limits. 2. Synthetic alerts, latency probes are timing out at the 30-second mark. 3. Application logs show the request started, but there is a 29-second gap before the next entry. 4. Developer reports, devs suspect a database lock, but the DBA confirms 0 row contention. The system is not crashing, it is just moving in slow motion. You are lacking the visibility to see where the friction is.
Hypothesis: thinking like a senior.
A junior engineer might try to scale the pods blindly. As a senior, I look for the 4 golden signals: latency, traffic, errors, and saturation. Hypothesis 1, upstream network throttling, ruled out. VPC flow logs show no dropped packets at the network interface. Hypothesis 2, application thread starvation, ruled out. The JVM thread dump shows most threads are in a waiting state, not blocked. Hypothesis 3, invisible saturation. The system is hitting a hard limit on a non-primary resource, such as disk IOPS or kernel entropy, that is not currently being graphed. Decision tree signal. If CPU is low and latency is high, while errors are 0, then always suspect a saturation level bottleneck on a secondary resource. Investigation. The 6-step debugging masterclass.
Step-by-step saturation discovery.
We must find the resource that is full. We execute these steps. 1. Deep node inspection. We SSH into a worker node and run the top command, focusing on the WA column for I/O weight. 2. Identify disk bottleneck. We see I/O weight at 45%. The CPU is idle because it is waiting for the disk to respond. 3. Query cloud volume metrics. We check the AWS console for the EBS volumes. We find the burst balance for the GP2 volumes is at 0%. 4. Trace the origin. We use IOTOP to find which process is consuming the IOPS. We find a logging sidecar is writing debug logs to a non-mounted root volume. 5. Measure network saturation. We check the node exporter metrics for node_network_transmit_Q_length and find it is also backing up. 6. Root cause identified, saturation blindness. The team was only monitoring utilization, how much CPU is used, but not saturation, the queue of work waiting for a resource. The disk ran out of burst credits, causing every write to block for 200 milliseconds, cascading into a 30-second user-facing delay. Let us look at the Prometheus query that finally exposed the saturation. The proof measuring the queue. This is the real signal. It shows that for every second of real time, the disk is busy for 0.98 seconds. The disk is saturated, regardless of how low the application CPU usage appears to be.
The fix: implementation of saturation, aware monitoring.
We must upgrade our dashboards to follow the use method, utilization, saturation, and errors for every physical and virtual resource. Senior warning: increasing the size of your EBS volumes is only a temporary fix. If the application logic is performing synchronous logging to disk, you will eventually saturate even the fastest NVMe drives. You must decouple disk I/O from the request-response path. Here is the YAML implementation for a Kubernetes logging sidecar. using memory-backed volumes to prevent disk saturation. Disclaimer: always test code in a non-production environment. By switching the logging volume to an empty diar with a memory medium, we move the I/O load from the slow network-attached disk to the local RAM. This eliminates the I/O wait bottleneck and restores application speed instantly.
Prevention and guardrails, the post-mortem.
To ensure we never miss a golden signal again, we implement these guardrails. 1. The use dashboard. We build a mandatory Grafana row for every service showing saturation metrics like disk queue depth, TCP retransmission rate, and CPU run queue length. 2. Automatic volume scaling. We implement an AWS Lambda that monitors EBS burst balance and automatically increases volume size, or IOPS, before the balance hits 0. 3. Asynchronous observability. We mandate that all logging and tracing must be non-blocking and handled by a background buffer to ensure infrastructure blips do not affect user latency. A senior engineer knows that a resource is only healthy if it has no one waiting in line to use it. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is the mathematical difference between utilization and saturation in queuing theory?
Answer: utilization is the percentage of time a resource was busy. Saturation is the amount of work that could not be serviced immediately and was forced to wait in a queue. Utilization can be 100% without saturation if the work fits perfectly, but saturation can occur at low utilization if the work arrives in massive, instantaneous bursts.
Senior follow-up 2, the scale and trade-off trap. You moved logs to memory-backed volumes to save IOPS. What is the risk regarding pod restarts?
Answer: total data loss. Memory-backed empty diar volumes are ephemeral and wiped when the pod restarts. If your log shipping agent, like FluentBit, lags behind and the pod crashes, you lose the very logs you need to debug the crash. You trade data durability for system performance.
Senior follow-up 3, the day 2 migration reality. You are migrating to a serverless architecture like AWS Lambda. Do golden signals still matter when you do not manage the nodes?
Answer: yes, but the signals shift. Saturation is no longer about disk IOPS. It is about concurrent executions and account throttling. You must monitor the provisioned concurrency utilization to ensure you do not hit the regional limits that cause 429 too many request errors.
Senior follow-up 4, curveball. Your golden signals are all green. Latency is low, CPU is idle, saturation is 0. Yet the site is still slow for users in one specific ISP in Germany. How do you find the missing signal?
Answer: the network path saturation. Traditional golden signals stop at your load balancer. To find this, you must look at client-side telemetry, or RUM, real user monitoring. The saturation is likely occurring at a congested peering point or a faulty BGP route outside of your cloud provider. You must use network path probes to see the saturation of the internet itself.
Pro tip, the I/O wait heuristic.
When looking at TOP or IOStat, if the I/O wait mode is higher than 10% on a consistent basis, your application architecture is likely I/O bound. This means adding more CPU or RAM will not help. You must either move to faster storage or, more effectively, implement caching and batching to reduce the frequency of physical disk commits.
The Senior DevOps Incident 29, the log sampling bias.
It is Thursday afternoon. You are investigating an intermittent payment failed bug that only affects 0.1% of transactions. You have the trace ID for a failed request, but when you search your logging platform, it returns 0 results. You check the application code. The error is clearly being logged. You check the log agent. It is running perfectly. Your logging system is working, but it has been configured to ignore the very evidence you need. You have fallen victim to log sampling bias.
Symptoms, the panic moment.
Here is the frustration of debugging with sampled data. 1. Missing evidence. High severity 500 errors appear in metrics but are completely absent from the log search results. 2. Inconsistent traces. You find the start of a request trace but the error span at the end is missing. 3. High volume. Your logging platform is processing 50,000 logs per second, yet it cannot find the one log that matters. 4. Cost control. The platform shows that 95% of logs are being dropped at the ingestion layer to save money. You are paying for a security camera that only records one frame every 10 seconds. You are missing the crime every single time.
Hypothesis, thinking like a senior.
A junior engineer might think the logging agent is broken and restart it. As a senior, I analyze the data reduction strategy. Hypothesis 1, log buffer overflow, ruled out. The agent metrics show 0 dropped events due to backpressure. Hypothesis 2, wrong log level, ruled out. The application is confirmed to be running in info mode and the error is a critical level. Hypothesis 3, head-based sampling. The observability pipeline is using a random 1% sampling rule at the source. Because the error is rare, 0.1%, the probability of that specific error log being sampled is nearly 0. Decision tree signal. If an error is visible in metrics but the corresponding log or trace is missing, then always suspect an aggressive head-based sampling policy. Investigation. The 6-step debugging masterclass.
Step-by-step sampling forensic work.
We must find where the data is being discarded. We execute these steps. 1. Audit the collector config. We check the OpenTelemetry or Datadog agent configuration for sampling _ priority. 2. Verify head-based logic. We find a probabilistic _ sampler set to 0.055%. It is discarding 95% of all traffic at the start of the request. 3. Calculate probabilities. We realize that for a 0.1% error rate, a 5% sampling rate means we only capture 1 out of every 20,000 errors. 4. Check tail-based rules. We look for any logic that says keep if error equals true. We find null. The decision to drop is made before the error even happens. 5. Inspect ingestion drops. We check the Datadog/ELK usage dashboard and find that inbound filter rules are discarding logs based on string matching. 6. Root cause identified, random data reduction. The team implemented head-based sampling to reduce observability costs. However, they applied it globally, including to critical error paths. The rare, high-value signals were treated with the same priority as low-value heartbeat logs, making debugging impossible. Let us look at the configuration that was throwing away our production evidence. The proof, the destructive sampler. This processor makes a blind decision. It does not know if the request will succeed or fail. By dropping 95% of traffic at the head, you effectively delete 95% of your potential debugging data.
The fix, implementing tail-based sampling.
We must move the sampling decision from the head to the tail of the request, where we can decide to keep data based on its actual value. Senior warning, tail-based sampling requires the collector to buffer the entire trace in memory before making a decision. This significantly increases the RAM requirements for your observability pods. You must balance memory cost against data visibility. Here is the YAML implementation for an OpenTelemetry tail-based sampler that prioritizes errors and high latency requests. Disclaimer: always test code in a non-production environment. This policy ensures that 100% of traces that result in an error are preserved and sent to the backend, regardless of volume. This eliminates the missing evidence problem entirely. We also ensure that slow requests are kept for performance tuning. We only apply the aggressive data reduction to the healthy 200 OK traffic, where logs are less critical.
Prevention and guardrails, the post-mortem.
To ensure we never lose another critical log, we implement these guardrails. 1. Priority-based logging. We implement a priority field in our structured logs. Logs marked as critical or security bypass all sampling filters at the infrastructure level. 2. Dynamic logging levels. We use an internal API to hot reload log levels. If we suspect an issue, we can toggle debug mode for a specific user ID or tenant without restarting the pods. 3. Cost-value audit. We perform a monthly review of log volume. If info logs from a single service account for 80% of the bill, we force the team to move those entries to trace level or remove them entirely. A senior engineer knows that the cost of a lost log is often higher than the cost of storing it. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does tail-based sampling require a decision_wait period?
Answer: traces are distributed. Different spans of the same request arrive at the collector at different times from different microservices. The collector must buffer all related spans and wait, for example, 10 seconds, to ensure it has the whole story before it can evaluate if the trace contains an error or high latency.
Senior follow-up 2, the scale and trade-off trap. You move to tail-based sampling. During a massive outage storm, your error rate hits 100%. What happens to your collector and your billing?
Answer: collector crash and billing explosion. If your policy is keep 100% of errors and everything fails, your collector will run out of memory trying to buffer the volume, and your storage bill will skyrocket. You must implement a rate limit or a safety valve in your sampling policy to cap the absolute number of logs kept during an incident.
Senior follow-up 3, the Day 2 migration reality. You are using a managed service like Datadog that samples at the ingestion point. How do you ensure specific transaction IDs are never dropped?
Answer: user agent or header tagging. We configure the application to attach a keep trace, true tag to the logs of critical business transactions. We then configure the ingestion filters in the managed service to respect this tag as an always include rule, bypassing the global probabilistic sampler.
Senior follow-up 4, curveball. Your tail sampling is perfect. Error logs are kept. Yet, for one specific crash, the log message is simply segmentation fault with no context. Why did your senior level logging fail here?
Answer: hidden cause. A segmentation fault is a kernel-level event that kills the process before the application-level logging library can flush its buffers to the agent. A senior engineer knows that for violent crashes, you must look at the standout of the container and the node system logs, DMESG, not just the application-level trace platform.
Pro tip, the trace ID header.
Always propagate your trace ID to the client in the HTTP response headers, for example, xtrace ID. When a customer reports a rare error, they can provide that ID to support. Even if your logging samples 99% of data, you can configure your pipeline to force flush any trace that is explicitly requested by a unique ID, ensuring you always have a forensic path for customer-reported issues.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
The Senior Dev Ops Incident 30, the theory-only disaster recovery plan.
It is Monday morning at 4 a.m. A rogue automated script has accidentally deleted the production database of your primary accounting service. The CTO is on the call and asks for the disaster recovery plan. You confidently state that the recovery time objective is 4 hours and the recovery point objective is 1 hour. You start the restore from S3. 30 minutes later, the restore fails with access denied. You check the logs and realize that while the backup script was succeeding for 6 months, the files it was writing are 0 bytes. Your DR plan was not a plan. It was a theory that just collided with reality.
Symptoms, the panic moment.
Here is the catastrophic state of the recovery process. 1. Data state primary database tables are empty. 100% data loss on the live volume. 2. Backup registry. The backup tool reports 180 successful daily snapshots in the metadata database. 3. Restore failure. Every attempt to pull data from the cloud storage returns an empty file or a checksum mismatch. 4. CTO pressure. The 4-hour recovery window is shrinking, and you cannot prove that a single valid backup exists. The backup script reported success because the command executed without an error code, even though it moved 0 bytes of data.
Hypothesis, thinking like a senior.
A junior might try to find a local copy of the data. As a senior, I analyze the verification pipeline. Hypothesis 1, AWS S3 regional outage, ruled out. Other buckets are accessible and serving data normally. Hypothesis 2, IAM permission drift, ruled out. The restore role has full read access to the backup bucket. Hypothesis 3, silent backup corruption. The backup script was using a pipe command that masked failures, or the database was locked during the snapshot, resulting in empty dumps. Decision tree signal. If backup logs show success but restore files are empty or corrupted, then always suspect a lack of automated restore verification. Investigation. The 6-step forensic recovery work.
Step-by-step DR failure debugging.
We must find the last true backup. We execute these steps. 1. Inspect backup script. We find the command pg_dump pipe gzip s3//bucket/backup.gz. 2. Identify the pipe trap. We realize the script was checking the exit code of gzip, not pg_dump. If the dump failed, gzip still succeeded in creating an empty file. 3. Analyze file sizes. We use AWS S3 ls-recursive to check the history of backup sizes. We see a sharp drop from 50 gigabytes to 200 bytes exactly 6 months ago. 4. Trace the change. We check Git history and find an IAM policy change 6 months ago that revoked select permissions from the backup user. 5. Search for snapshots. We bypass the custom script and check for cloud-native snapshots, AWS RDS snapshots. We find an automated daily snapshot that was independent of our script. 6. Root cause identified, verification gap. The team relied on output-based monitoring instead of integrity-based monitoring. Because no one had performed a test restore in over a year, the silent failure of the custom script went undetected until the moment of crisis. Let us look at the shell script error that fooled the monitoring system. The proof, the masked failure pipe. This is a classic Linux pipe error. In a pipe, the exit code returned to the shell is usually the code of the last command. gzip successfully compressed nothing and returned 0, masking the pg_dump permission failure.
The fix, implementing automated continuous restore.
We must move from backing up to restoring. A backup is not a backup until a restore has been verified. Senior warning, do not trust cloud-native snapshots blindly. If your AWS account is compromised or a region goes offline, those snapshots are inaccessible. You must maintain cross-account, cross-region backups with automated integrity checks. Here is the bash implementation for a robust backup, script with pipe fail and size verification. Disclaimer, always test code in a non-production environment. This is the most important line. It ensures that if pg_dump fails, the entire command string returns a non-zero exit code, triggering our monitoring and preventing a false success message.
Prevention and guardrails, the post-mortem.
To ensure our DR plan is never theory only again, we implement these guardrails. 1. Automated recovery sandbox. We create a weekly Jenkins job that pulls the latest backup, restores it into a transient isolated database, and runs a select the count function to verify data density. 2. RTO/RPO drills. We mandate a quarterly game day. We intentionally delete a non-production database and time how long it takes for a junior engineer to restore it using only the documentation. 3. Air-gapped backups. We implement AWS backup with Vault Lock in a separate security-hardened account, ensuring that even if the primary account is deleted, the backups are immutable and preserved. A senior engineer knows that hope is not a disaster recovery strategy. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. What is the difference between an EBS snapshot and a logical database dump in a DR scenario?
Answer: an EBS snapshot is a block-level incremental backup. It is extremely fast to create and restore, but is cloud-locked and can sometimes suffer from file system inconsistency if not frozen during the snapshot. A logical dump, PG_dump, is a text-based representation of the data. It is slower but is cloud-agnostic and allows you to restore individual tables or move data across different database versions.
Senior Follow-up 2 The Scale and Trade-off Trap. You decided to run automated restores every night to verify integrity. What is the cost trade-off for a 10 terabytes database?
Answer: massive egress and storage costs. Restoring 10 terabytes every night involves spinning up large instances and provisioning expensive high IOPS volumes. To optimize, a senior would perform a sampling restore, restoring only a subset of critical tables or running the full drill only once a week while using metadata checksums for daily verification.
Senior Follow-up 3 The Day 2 Migration Reality. You are moving to a multi-cloud strategy, AWS and GCP. How do you synchronize your DR plan when the storage APIs are different?
Answer: abstraction via tooling. We use a cloud-agnostic backup manager like Velero for Kubernetes or a managed service that supports multi-cloud replication. We treat the backup bucket as a generic URI and use a service mesh or private link to securely transfer blobs between providers, ensuring that US East 1 on AWS can be recovered to Central 1 on GCP.
Senior Follow-up 4 Curveball. You have valid backups and a perfect restore script. But the secret key used to encrypt the backups was stored in the very database that was deleted. How do you break this deadlock?
Answer: the root key scenario. This is why senior architects use a managed key service, AWS KMS, with a key policy that is independent of the application database. Alternatively, for extreme security, you maintain an offline emergency kit, a physical or digital vault containing the master encryption keys and the bootstrap credentials required to access the backup account from a blank slate machine.
Pro tip, the 3-to-2-1-to-1 rule.
Modern SRE standards recommend the 3-to-2-1-to-1 rule. Keep 3 copies of your data on 2 different media types, with 1 copy off-site and 1 copy that is air-gapped and immutable. If you do not have an immutable copy that cannot be deleted by a compromised admin account, you do not have a ransomware-proof business.
The Senior Dev Ops Incident 31, the MTTR paralysis.
It is Friday at 8 p.m. A critical payment service is returning 500 errors. You acknowledge the alert in 2 minutes, but 2 hours later the service is still down. 15 engineers are in a Zoom room all talking at once, yet no one is actually fixing the problem. You cannot find the logs, the original developer is on a plane, and the runbook link in the alert leads to a 404 page. Your mean time to recovery is being killed not by the bug, but by the chaos of your organization.
Symptoms, the panic moment.
Here is the operational breakdown during the extended outage. 1. Mean time to detect MTTD 30 seconds. The monitoring worked perfectly. 2. Mean time to acknowledge MTTA 2 minutes. The on-call engineer responded instantly. 3. Mean time to recovery MTTR 145 minutes and counting. The process is failing. 4. Action pattern Slack storming. High volume of messages like who owns this? And does anyone have the SSH key? With 0 technical progress. The bottleneck is not the speed of the CPU. It is the speed of human coordination and knowledge retrieval.
Hypothesis, thinking like a senior.
A junior might try to dive into the code to find the bug. As a senior, I analyze the incident pipeline. Hypothesis 1, insufficient permissions, ruled out. The on-call engineer has admin access to all clusters. Hypothesis 2, obfuscated logs, ruled out. The logs are there, but no one knows which specific ELK index they are in. Hypothesis 3, high cognitive load. The complexity of the microservice graph has exceeded the team's ability to debug without a standardized service catalog and executable runbooks. Decision tree signal. If MTTD is low but MTTR is high, and the team is lost during the investigation, then always suspect a failure in operational readiness and runbook quality. Investigation. The The 6-step process forensic work.
Step-by-step MTTR debugging.
We must debug the human system. We execute these steps. 1. Timeline reconstruction. We look at the Slack timestamps. We find it took 45 minutes just to identify which microservice was actually failing. 2. Audit the alert. We click the dashboard link in the PagerDuty alert. It leads to a generic cluster overview rather than a service-specific view. 3. Verify runbook accuracy. We find the documentation in Confluence. It was last updated 3 years ago and refers to a legacy database that was decommissioned. 4. Check tribal knowledge. We realize the only person who knows how to debug the payment gateway is currently unreachable. The bus factor for this service is 1. 5. Evaluate tooling friction. We watch the on-call engineer struggle to log into the Bastion host because the VPN is lagging. 6. Root cause identified. Operational debt. The company optimized for shipping code but ignored running code. The lack of a centralized service catalog and automated, tested runbooks created a 2-hour delay in simple decision-making. Let us look at the gap between a bad alert and a senior-grade alert. The proof, the low-context alert. This is the primary driver of high MTTR. An alert without a specific, tested, and high-context link forces the engineer to start from zero. In a high-pressure outage, every second spent searching for documentation is a failure of the platform.
The fix, implementing high-context observability.
We must inject the solution directly into the alert. We will automate the correlation of alerts to specific owners and executable runbooks. Senior warning, do not try to write a runbook for every possible error. You will end up with thousands of out-of-date pages. Focus on general debugging paths and ensure the links to logs and dashboards are dynamically generated for the specific instance that is failing. Here is the YAML implementation for a high-context Prometheus alert rule with dynamic deep links. Disclaimer: always test code in a non-production environment. By using template variables in the alert, we provide the engineer with a single click that leads directly to the failing logs. This eliminates the 45-minute search phase and drops MTTR significantly.
Prevention and guardrails, the post-mortem.
To ensure we never suffer from MTTR paralysis again, we implement these guardrails. 1. The 5-minute rule. If an on-call engineer cannot find the failing code and logs within 5 minutes of acknowledgement, the alert is marked as low quality and must be fixed the next day. 2. Internal developer portal backstage. We mandate that every service must be registered in the catalog with a defined owner, Slack channel, and current runbook URL before it can be deployed to production. 3. Incident commander training. We move away from democratic debugging. Every outage must have a designated incident commander whose only job is to stop the Slack storming, delegate tasks, and maintain a clear timeline of actions. A senior engineer focuses on the path to resolution as much as the resolution itself. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between a playbook and a runbook in senior DevOps culture?
Answer: a playbook is a high-level strategic guide for responding to a class of incidents, for example, how to handle a data breach. A runbook is a low-level, tactical set of instructions for a specific service, for example, how to restart the Redis cluster for the auth service. Runbooks should be as close to automated scripts as possible.
Senior follow-up 2, the scale and trade-off trap. You want to implement auto-remediation scripts that fix the issue automatically. What is the risk regarding root cause analysis?
Answer: evidence destruction. If an automated script restarts a pod every time it hits 90% memory, you might fix the outage, but you are simultaneously deleting the heap dump you need to find the memory leak. You trade availability for debuggability. You must ensure auto-remediation triggers a background snapshot of the state before the fix is applied.
Senior follow-up 3, the day 2 migration reality. You have 2,000 microservices. How do you ensure that all 2,000 runbooks are up to date without manually checking them?
Answer: runbooks as code. We store the runbook in the same Git repository as the application code, for example, docs/runbook.md. We add a CI check that fails the build if the runbook has not been touched or verified in the last 6 months. This forces developers to maintain operational documentation as part of their standard workflow.
Senior follow-up 4 curveball. Your dashboards are perfect, your runbooks are current, and your incident commander is ready. Yet, MTTR is still high because the Cloud Console is currently down and you cannot manually scale the instances. How do you recover?
Answer: tool failure scenario. A senior engineer knows the difference between the cloud and the cloud API. If the AWS console is down, you must be able to use the AWS CLI or Terraform from a local machine via a pre-provisioned emergency credential. If the cloud API itself is down globally, you have hit a regional disaster, and you must follow your cross-cloud failover strategy rather than trying to fix the current environment.
Pro tip: the warm escalation.
In a truly senior incident response, the person paged should not be the fixer. They are the evaluator. Their job is to spend 5 minutes determining if this is a minor blip or a code red outage. If it is a code red, they immediately trigger a warm escalation to the service owner and the platform architect, rather than struggling alone for 2 hours. Knowing when to ask for help is the ultimate senior skill.
The Senior DevOps Incident 32, the Phantom Recurring Outage, wrong root cause identified.
It is Tuesday at 2 p.m. For the third time this month, the database connection pool in the core API has exhausted. Twice before, the incident was closed with the root cause identified as transient cloud network latency and resolved by simply increasing the connection pool size. But now, even with a pool size of 500, the service is crashing again. You realize that the previous root cause analyses were not technical findings, they were convenient guesses. You are fighting a phantom because you misdiagnosed the villain.
Symptoms: the panic moment.
Here is the behavior of the service that was supposedly fixed twice before. 1. Error pattern: application logs show could not get JDBC connection. Nested exception is SQL transient connection exception. 2. Metrics history: connection usage shows a slow, linear climb over 48 hours until it hits the hard limit. 3. Resolution history: previous incidents were resolved by pod restarts, which cleared the symptom but not the cause. 4. Database state: the database engine itself shows low CPU and high idle capacity, yet it refuses new connections. The system is leaking resources slowly. Previous investigations focused on the crash rather than the climb.
Hypothesis: thinking like a senior.
A junior engineer might suggest increasing the pool size again. As a senior, I analyze the logic of the resource lifecycle. Hypothesis 1: database throughput limit. Ruled out. The database is not saturated and disk IOPS are healthy. Hypothesis 2: network packet loss. Ruled out. VPC flow logs show 0 retransmissions or drops between the app and the DB. Hypothesis 3: logical connection leak. A specific code path, likely an error handler or a background thread, is opening a database connection but failing to close it in the finally block. Decision tree signal: if a resource exhaustion issue returns repeatedly after a restart, and the metrics show a linear climb, then always suspect a logical leak rather than infrastructure capacity. Investigation: the 6-step debugging masterclass.
Step-by-step root cause verification.
We must move past the transient network excuse and find the leak. We execute these steps. 1. Audit connection metadata. We query the database pg_stat_activity to see the state of the 500 open connections. We find 480 are in idle state for over 10 hours. 2. Enable leak detection. We update the Hikari CP connection pool configuration to enable leak detection threshold. 3. Trace thread stacks. We trigger a thread dump of the running Java application during the climb. 4. Identify the victim path. The leak detection log fires, pointing to a specific export to CSV service. 5. Perform code review. We examine the export service and find it uses a custom stream that bypasses the standard Spring Transaction Manager. 6. Root cause identified, unclosed resource in error path. When a CSV export fails due to a disk full error, the database connection is never returned to the pool. Because exports are rare, the leak took days to manifest, leading previous engineers to blame network blips since the timing seemed random. Let us look at the code logic and the leak detection logs that prove the misdiagnosis. The proof: the connection leak. The developer manually requested a connection from the pool, bypassing the automated lifecycle management of the framework. Because there is no finally block to close the connection, any exception in the business logic leaves the connection stranded. This is why increasing the pool size only delayed the inevitable.
The fix, implementation of TRI with resources, and automatic leak detection.
We must enforce a strict resource lifecycle and enable proactive monitoring within the connection pool itself. Senior warning: never accept transient error as a root cause without data. If you cannot explain why the error happened and why it stopped, you have not found the root cause. You have only found a coincidence. Here is the Java implementation for secure connection management and pool-level leak detection. Disclaimer: always test code in a non-production environment by using the try with resources pattern. The language runtime guarantees that the close method is called on the connection regardless of whether the block succeeds or fails. We configure the pool to log a stack trace if a connection is held for more than 2 seconds. This ensures that any future leaks are identified in the logs immediately, rather than after a 48-hour outage.
Prevention and guardrails, the post-mortem.
To prevent wrong root cause identifications in the future, we implement these guardrails. 1. Blameless post-mortem standard. We mandate the 5 whys technique for every P1 incident. We do not stop at the pool was full. We must answer why was the pool full, and why did the leak detection not fire. 2. Static analysis. We add SonarQuebec rules to our CI pipeline that explicitly block any code that manually opens a database connection without a corresponding close or a try with resources block. 3. RCA peer review. Every root cause analysis document must be signed off by a senior architect from a different team to ensure that bias and convenience are removed from the findings. A senior engineer knows that the first answer is rarely the right one. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why do connection leaks often look like transient network issues to junior engineers?
Answer: confirmation bias. In distributed systems, small network blips are common. If an engineer sees a connection failure and notices a tiny latency spike in the cloud provider dashboard at the same time, they assume causality. They fail to realize that the latency spike was a symptom of the connection queue backing up, not the cause of it.
Senior follow-up 2, the scale and trade-off trap. You enabled leak detection in production. What is the performance trade-off of this monitoring?
Answer: CPU overhead. To provide a stack trace of a leak, the connection pool must capture the current thread stack every time a connection is requested. At extremely high throughput, for example, 50,000 requests per second, this can add a measurable 1 to 2% CPU penalty. The trade-off is sacrificing a tiny bit of compute for the ability to prevent multi-hour outages.
Senior follow-up 3, the day 2 migration reality. You are migrating to a reactive programming model, like Webflux or Vert.x. Do connection leaks still occur in non-blocking code?
Answer: yes, but they are harder to find. In reactive systems, a connection might be tied to a stream rather than a thread. If the stream is never subscribed to, or if the operator chain is broken without a terminal signal, the underlying connection remains open. You must use specialized reactive profilers to track the lifecycle of the data buffers.
Senior follow-up 4, curveball. You fixed the code leak. But a week later, the pool exhausts again. This time, the stack trace points to the standard login path, which uses a transaction manager. How can a transaction manager leak a connection?
Answer: the hidden thread scenario. If your code starts an asynchronous background thread inside a transaction, the transaction manager might close the connection on the primary thread before the background thread is finished. Alternatively, if your database has a statement timeout that is longer than your transaction timeout, the connection can get stuck waiting for a slow query even after the application thinks the transaction is over.
Pro tip, the idle in transaction signal.
Always monitor the database state idle in transaction. This state means the database has allocated a worker and a lock to a connection, but the application is busy doing something else, like calling an external API, before finishing the transaction. This is the #1 killer of database performance at scale. Never perform a network call inside a database transaction block.
The Senior DevOps Incident 33, the knowledge silo trap.
It is 8 p.m. on a Saturday. A critical internal tool used for deployment has failed with an SSL handshake error. The on-call engineer checks the documentation, but it only says contact Steve for issues with this tool. Steve is currently on a camping trip with no cell service. You have 40 developers blocked, a production hotfix that needs to go out, and a technical solution that is locked inside the head of one person. Your organization has a bus factor of 1.
Symptoms: the panic moment.
Here is the operational paralysis caused by tribal knowledge dependencies. 1. Resolution delay. MTTR is infinite because the instructions to rotate the internal CA certificates were never written down. 2. Permission deadlock. The SSL certificates are stored in a private HashiCorp vault path that only Steve has the policy to read. 3. System mystery. The tool is running on a pet server in a legacy data center that is not managed by the standard Terraform modules. 4. Frustration spike. High-level management is calling every 10 minutes, but the team is literally incapable of taking action. The bottleneck is not a technical bug. It is the fact that the expertise required to fix it is not a shared asset.
Hypothesis: thinking like a senior.
A junior engineer might try to hack into Steve's account. As a senior, I analyze the ownership and portability of the system. Hypothesis 1, tooling obsolescence, ruled out. The tool is critical for daily operations. Hypothesis 2, permission over scoping, ruled out. Steve followed least privilege correctly, but he did not implement emergency break glass access. Hypothesis 3, undocumented legacy debt. The tool was built as a temporary script 2 years ago and became a permanent production dependency, without ever going through an SRE review or an onboarding process. Decision tree signal. If the documentation for a critical tool points to a specific person, rather than a process, then always suspect a catastrophic knowledge silo. Investigation. The 6-step forensic discovery work.
Step-by-step silo breaking.
We must reverse engineer the Steve method while he is offline. We execute these steps. 1. Search private channels. We use admin permissions to search the team's Slack history for SSL and Steve. We find a message from 6 months ago where he mentioned a manual cron job. 2. Identify the server. We scan the network for the IP address of the deployment tool. We find it as a standalone VM named deploytemp01. 3. Force access. Use a root-level AWS Systems Manager session to bypass SSH keys and gain access to the host. 4. Map the configuration. We run find/-name, CRT and grep-r to find where the tool is loading its certificates from. 5. Discover the secret script. We find a hidden bash script in /opt/script/rotate.sh that Steve was running manually whenever he got a notification on his personal phone. 6. Root cause identified. Operational heroism. Steve was acting as a human cron job. He built a critical system but never automated the maintenance or shared the credentials, making himself a single point of failure for the entire company's deployment pipeline. Let us look at the undocumented script and the manual certificate path we discovered. The proof: the undocumented legacy script. This is the knowledge silo in physical form. The critical system depends on a file located in a private user directory. When Steve is offline, the file is functionally non-existent to the company.
The fix: centralization and standardization.
We must immediately move the certificates to a shared vault and rewrite the tool's deployment using infrastructure as code. Senior warning: do not blame Steve. Hero culture is usually the result of a management failure to allocate time for documentation and automation. Your goal is to make Steve's knowledge redundant, so he can enjoy his camping trip without being the company's biggest risk. Here is the HCL implementation to move manual secrets into a shared AWS Secrets Manager and automate rotation. Disclaimer: always test code in a non-production environment. By moving the secret from a private home directory to a named AWS secret, we ensure that anyone with the correct IAM permissions can access it during an emergency.
Prevention and guardrails. The post-mortem.
To ensure knowledge silos are never built again, we implement these guardrails. 1. The bus factor audit. Every quarter, we identify critical systems and verify that at least 3 people can perform a standard maintenance task, like a certificate rotation, using only the documentation. 2. Game day. The wheel of misfortune. We run an exercise where we virtually fire a random senior engineer for 1 hour. The rest of the team must solve a simulated incident involving that person's systems without calling them. 3. Doc as code requirement. We add a documentation stage to our definition of done. No feature is considered complete until a runbook entry exists in the shared service catalog. A senior engineer is one who makes themselves unnecessary through automation and teaching. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. Why do knowledge silos naturally form in high-growth engineering teams?
Answer: the velocity trap. In early-stage growth, shipping is rewarded more than observability or documentation. Senior engineers who move fast often build systems that work perfectly but lack the abstractions and interfaces required for others to manage them. Over time, these speed hacks become structural silos.
Senior Follow-up 2 The Scale and Trade-off Trap. You moved all documentation to a central wiki. Now, developers complain they cannot find anything because there are 5,000 pages of old docs. How do you handle this trade-off?
Answer: metadata and decay. Documentation must have a liveness attribute. A senior engineer implements a freshness check where every documentation page must be re-verified by the owner every 6 months. If it is not verified, it is automatically marked as obsolete or archived. Quality is more important than quantity.
Senior Follow-up 3 The Day 2 Migration Reality. You are migrating from Steve's pet server to a managed service. Steve is against it because the new service is less flexible. How do you handle the technical and social friction?
Answer: the reliability negotiation. We do not argue about flexibility. We argue about availability and on-call burnout. We show Steve the data from the Saturday outage and explain that the new managed service provides 99.9% availability and automated rotation, which means Steve will never be called while camping again. We trade unlimited flexibility for unlimited peace of mind.
Senior Follow-up 4 Curveball. You have perfect documentation and a high bus factor. But during an outage, the internal wiki itself is down because it was running on the cluster that crashed. How do you access your recovery instructions?
Answer: constraint scenario. This is the bootstrap problem. Critical disaster recovery documentation must be stored in a survivable location independent of the production infrastructure. A senior engineer ensures that DR runbooks are stored as PDF or Markdown in an air-gapped S3 bucket or a physical safe folder that does not require the production VPN to access.
Pro tip: the README first rule.
Before you write the first line of code for a new infrastructure tool, write the readme.md and the on-call runbook. If you cannot explain how to troubleshoot the tool before you build it, your design is likely too complex for others to manage. Documentation is a design tool, not a post-project chore.
The Senior Dev Ops Incident 34 The Recurring Ghost. No preventive action.
It is Tuesday morning. The exact same memory leak that took down the order service last month has happened again. You check the post-mortem document from 30 days ago. The root cause was identified, and 3 action items were written down to prevent it. But when you look at the Jira board, those tickets were never even groomed. The incident was resolved by restarting the service, but the system was never fixed. You are trapped in a loop of operational insanity because your organization treats post-mortems as paperwork rather than engineering requirements.
Symptoms: the panic moment.
Here is the behavior of the recurring systemic failure. 1. Deja-vu metrics: the CPU and memory graphs look identical to the previous month's outage. 2. Alert pattern: the same PagerDuty rule fired at the same time of day under the same traffic load. 3. Team frustration: the on-call engineer says, "I thought we fixed this last time." 4. Trust erosion: product owners are questioning the reliability of the platform because the same bug keeps returning. The failure is not technical. It is a failure of the feedback loop between incident management and the engineering backlog.
Hypothesis: thinking like a senior.
A junior might just fix the leak again. As a senior, I analyze the post-incident life cycle. Hypothesis 1, incomplete root cause analysis, ruled out. The previous post-mortem correctly identified the leaking library. Hypothesis 2, failed automation, ruled out. No automation was ever implemented to catch the leak in CI. Hypothesis 3, abandoned action items. The engineering team prioritized new features over the reliability fixes identified in the previous post-mortem, leaving the front door open for the same failure. Decision tree signal: if the same incident happens twice with the same root cause, then always suspect a failure in the preventive action process. Investigation: the 6-step process forensic work.
Step-by-step backlog debugging.
We must find where the preventive logic died. We execute these steps. 1. Audit the postmortem. We open the document from last month. We find action item 1, update library version times to Y. 2. Trace the JIRA ticket. We search for the ticket number. We find it in the backlog column with 0 comments and no assignee. 3. Check code history. We run git blame on the project's dependency file. It is still using the vulnerable version X. 4. Interview the team lead. We learn that the preventive tickets were labeled as technical debt and were pushed to the next quarter to meet a feature deadline. 5. Evaluate error budgets. We check if the team tracks reliability. We find they have no error budget policy to stop feature work during instability. 6. Root cause identified. Decorative postmortems. The organization views postmortems as a check-the-box exercise for compliance rather than a fix-the-system exercise for SRE. Without a mechanism to force action items into the sprint, preventive work is always out-prioritized by feature pressure. Let us look at the gap between the plan and the reality of the preventive tickets. The proof, the ghost action items. The ticket was created but never prioritized. This is the definition of operational debt. The organization paid the cost of the incident but refused to buy the cure.
The fix, implementation of forced error budgets.
We must move from optional fixes to mandatory reliability. We will implement a strict error budget policy that halts feature development when service reliability targets are missed. Senior warning: postmortems are useless without executive buy-in. If the CTO does not empower the DevOps team to block feature releases until critical preventive actions are completed, you will continue to fight the same fires until the team burns out. Here is the YAML implementation for a Prometheus-based error budget. Alert to block deployments. Disclaimer: always test code in a non-production environment. By adding this label, we can configure our CI/CD pipeline to check the status of the error budget exhausted alert. If it is active, the deploy to prod stage is automatically disabled for non-hotfix code, forcing the team to focus on the preventive action items.
Prevention and guardrails, the post-mortem.
To ensure preventive action is permanent, we implement these guardrails. 1. Mandatory RCA reviews, weekly review of all postmortems with the engineering VP to ensure action items are correctly prioritized and assigned. 2. Auto-escalation. If a preventive action ticket is not moved to in progress within 7 days, it is automatically escalated to the department head. 3. Evidence-based closing. An incident is only considered resolved once the preventive code change has been merged, and the corresponding JIRA ticket is closed with a link to the PR. A senior engineer knows that if you do not make time for maintenance, the system will choose a time for you. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is the difference between a blameless and a root cause-focused post-mortem?
Answer: a blameless post-mortem focuses on how the system allowed a human to make a mistake, rather than who made the mistake. It assumes everyone acted with the best intentions and looks for psychological safety. Root cause analysis is the technical part that finds the single point of failure. You must have both to prevent the incident from returning.
Senior follow-up 2, the scale and trade-off trap. You implemented a feature freeze policy based on error budgets. The marketing team is furious because they cannot launch a new campaign. How do you handle this trade-off?
Answer: the business risk negotiation. A senior engineer explains that launching a campaign on a broken platform is a net loss. We use the cost per minute of the last outage to prove that fixing the reliability issue is more profitable than the potential revenue from the campaign. We trade temporary delay for long-term brand trust.
Senior follow-up 3, the day 2 migration reality. How do you handle external incidents, like a cloud provider outage, in your post-mortem process?
Answer: the resilience action. Even if the cloud provider failed, the preventive action is, how do we make our system survive the next provider failure? We focus on adding multi-region redundancy, circuit breakers, or graceful degradation. We never accept external provider as a reason for no preventive action.
Senior follow-up 4, curveball. You have perfect action items and budgets, but the engineer assigned to the fix says they cannot reproduce the bug because the observability data from the incident has been auto-deleted due to a 7-day retention policy. How do you prevent data amnesia?
Answer: hidden cause. A senior engineer knows that incident data must be exempt from standard cleanup rules. The fix is to configure your observability platform to pin or archive all logs and traces related to an incident ID the moment an alert is triggered, preserving the evidence until the preventive action is verified.
Pro tip, the Fix It Friday.
Implement a recurring 4-hour window every Friday where feature work is strictly forbidden. This time is dedicated purely to clearing the preventive action backlog from previous incidents. This creates a sustainable culture where reliability is built into the weekly rhythm, rather than being an emergency interruption.
Category 8, Wrap Up, the Vigilant Platform.
Category 8 has shown us that the most sophisticated monitoring tools are useless without a culture of accountability and precision. We have learned that dashboards can lie if they only monitor transport and not logic, and that alert storms are a failure of design, not a sign of diligence. We saw that a disaster recovery plan is merely a fantasy until it is tested under pressure, and that high MTTR is often a human coordination problem rather than a technical one. Finally, we recognize that the true end of an incident is not the resolve button, but the implementation of the preventive action that kills the bug forever. Mastering observability and incident management means moving from being a firefighter to being an architect of resilience.
Part 1, Wrap Up, Mastering the Internal Developer Platform.
In this first volume, we have journeyed through the 4 pillars of platform, delivery, and automation failures. We have mastered the internals of the Kubernetes orchestrator, secured the network edge, hardened our CI/CD delivery engines, and established the culture of observability required to survive at scale. We have seen how small errors in YAML, HCL, and shell scripts can cascade into million-dollar outages. But more importantly, we have developed the senior-level intuition to look past the symptoms and identify the architectural flaws that allow these incidents to exist. You now possess the foundation of a staff-level DevOps engineer, but our journey is only half complete. In Part 1, we focused on the tools we build and the pipelines we manage. In Part 2, we leave the world of the orchestrator behind and dive into the ghost in the machine. We are moving from high-level automation to low-level systems engineering.
Coming up in Part 2, Distributed Systems and Kernel Catastrophes.
In the next volume, we will perform reference-grade deep dives into these hardcore domains. 1. Networking and kernel abyss, contract table exhaustion, SNAT port depletion, and eBP FMAP limits. 2. Distributed data horrors, Postgres TZID wraparounds, Kafka rebalance storms, and HA split-brain scenarios. 3. High-scale performance cascades, thundering herds, cache stampedes, and the Linux CFSC PU quota trap. 4. Advanced cloud economics, cross-AZ cost explosions, and regional gray failures. If you want to understand how the internet actually breaks at the bit and kernel level, Part 2 is mandatory.
Final challenge, join the elite.
This concludes Part 1 of the Senior DevOps Incident Masterclass. If you can solve even half of the curveballs we threw at you today, you are already in the top 5% of engineers. But the hardest challenges are yet to come. Part 2 is where we separate the architects from the operators. Click the link in the description to watch Part 2 immediately and complete your training. Do not forget to subscribe.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.